Okay, so welcome back, and now we're going to kind of continue on with our discussion of circuit analysis. And we actually already have done voltage dividers, and we've seen them in a couple different examples. And the analysis that we just did, that big analysis, let's take a look at that. That's still up here. So we just did this analysis. We actually did a voltage divider. So this section here relative to this section is a voltage divider, and this section relative to this section is a voltage divider. So now what we're going to do is we're going to kind of formally take a look at this in a simplified way so that we can use voltage dividers as a tool. And you probably heard this term before, voltage divider, when people are talking about electronics or engineering. And they're a very simple tool, nothing that you don't know how to do already. But it's just a certain configuration of voltage and resistors that you can use to kind of, get an output or get a voltage that you want. All right, so you can go ahead and the notes, you have the notes that you can read here. So you can read through these if you like, but we're just going to kind of jump right into this and take a look closely at it. So one thing is that when we're doing voltage dividers, we're typically talking about just two resistors, all right? So we've got an R1 and we've got an R2. All right, and so the problem is say you have a voltage. Maybe that voltage is 10 volts, maybe it's 5 volts, maybe it's something else, and you want to reduce that down somehow, and so that you can use it in maybe a different part of the circuit, or maybe an amplitude of something is too high and you want to scale it down. That's what a voltage divider is for. So let's take a look at this circuit here, and let's see if we kind of can analyze what's going on here. All right, so we've got a voltage V and it's plus to minus, and we've got the nodes A, B, and C here. All right, we've got two resistors, R1 and R2. All right, so right away we know that we can compute what the current is. So V equals I times R, so I would equal V over the sum of R1 and R2. All right, so we could immediately compute what I is, and then we could compute what the voltage drop V1 is and V2 is by multiplying that I times R1 and R2. So that's very simple. That's just Ohm's law. So that just, we know how to do that. So that's what's kind of going on right here. We're just saying that I equals V over R1 plus R2, all right, because these are series resistors, all right. Then similarly, we have, again, we rewrite to Ohm's law here, and then we can say that the voltage over V1 is simply that current, right? And that the current is the V over R1 plus R2 times R1. And the voltage over R2 is simply that current, which is V divided by R1 plus R2 times R2. Everything is the voltage, the current times the resistance, current times the resistance, and that's it. So now if you look at this model here, right, and you've got these two resistors, R1 and R2, then it's kind of like, oh, you can kind of simplify this a little bit and kind of make up a little, rule of thumb for converting voltages and creating new voltages. And so when we do that, we can kind of simplify this and we kind of come up with these equations right here that says that V1, the voltage drop over this R1 resistor, and then V2, is simply R1 times V over R1 plus R2, and V2 is R2 times V over R1 plus R2. So that's it. So really we didn't do anything. We just observed, right? If we compute the current in a two resistor loop, and then we figure out what the voltage drops are over each of those resistors, then these simple equations can kind of tell us what's going on. So so you can write those down if you want. They're very easy to derive. So let's go ahead and let's see if we can use these equations to kind of solve for something, all right? So let's go ahead and see what we have here, all right? And let's see if there's anything exciting here. All right, so let's go ahead and let's do an example, and then I'm going to show you some other things about it. But let's do a couple examples and let's actually go and build something here. All right. So first thing is, let's take these and let's remember what these are. So this says the voltage drop 1 is simply R1 times V over R1 plus R2, and the voltage drop 2 is simply R2 times V over R1 plus R2. And this is just the current each time, right? Okay, so let's go ahead and let's go back to our drawing program here. Let's delete all that. And let's run through and see if we can actually do this in a real example. Okay, so the first thing is let's draw something, and let's draw with a voltage source this time. And let's be tangible. Let's call this 12 volts. Okay, and now let's say that we've got this 12 volt signal maybe, or this DC 12 volts, and we want to get, say, like a lower voltage off of this. All right, we need a like a 5 volts or something like that. So we say, hey, let's use a voltage divider. All right, and we go through here, and then we've got R1 here, and we've got R2 here. All right, and we know that we're going to have some voltage drops over here, V1, and we're going to have V2. And then, of course, we're going to have our current that flows through here, flows through both resistors. Let's not go through the symbols there. Let's try and get a little bit cleaner. And let's just call this I. And we could call this I, 1 or I2. They would be the same, right? So we'll just call it I. Okay, so now what do we know? Well, let's write down Ohm's law again. And let's compute what this I is in the circuit. And we can call it lowercase I or uppercase here. We'll just call it I. And it equals the total voltage, V, which is 12 volts, over the total resistance, which is R1 plus R2, right? R1 plus R2. Let's go ahead and let's put some values for this. So let's say that R1 is, let's say that this is 20 ohms. And let's say that R2 is 100 ohms. All right, so that would be 20 ohms plus 100 ohms. All right, that would be our current. So let's get out our calculator. So 12 divided by quantity, 20 plus 100 equals 100 milliamperes. All right, so we've got 100 milliamperes there. All right, 100 milliamperes. All right, so that's our I, and now we can figure out each of these voltages if we want. It's just 100 times 20 and 100 times 100. So 100 milliamperes times our 20, so if we just take that times 20, that's going to be 2 volts. So we know that V1 is 2 volts, and now we know that the voltage drops in a complete loop, sum up to 0, right? That's Kirchhoff's voltage law. So we could just say 12 minus 2 equals 10, or we could do it, right? So we know that that's going to be 10 volts, or we could just take the 100 milliamps times 100 ohms. That's going to also give us 10 volts. So everything is as it should be. So we just figured this out by kind of an analysis. Now let's see if the equations work themselves. So the equations say that V1 equals R1 over, or actually R1 times V over R1 plus R2. And V2 equals R2 times V over R1 plus R2. All right, so really all this really is if you think about this, it's just a ratio. It's just a ratiometric calculation. And if you have these two resistors, the voltage drop over this R2 is going to be the proportion of R2 of the total sum. That would just be R2 over R1 plus R2 times the total voltage. And the same thing is with this one. This would, the voltage drop over this would just simply be R1 over the sum R1 plus R2 times the total voltage, right? And that's all these equations do. So let's plug them in here. So V1, let's just do it right here if we can, is R1, which is 20 ohms, times V, which is 12 volts, over R1 plus R2, that's 20 plus 100, is just 120 ohms. And the next one is R2, which is 100 ohms times 12 volts. And again, over the same denominator, 120 ohms. So let's do the math. The first one is 20 times 12 equals, divided by 120 equals 2. So this equals 2 volts. So sure enough, that checks out. And let's do this one. 100 times 12 is, again, 100 times 12, we know that that's 1200 divided by 120 divided by 120, and that's 10 volts. 10 volts. And that checks out, right? And so both of these give the exact same results as the analysis. So these little modeling equations, right, if you have a circuit that looks like this, you can just use these to compute what these voltages are here, all right? And now, and then likewise, notice one thing that's kind of interesting here. No matter what the values of the resistances are, if the ratio of the resistances is the same, you're going to get the same voltages. So for example, let's go and let's change it to 200 ohms and 1000 ohms. All right, let's get rid of these and let's redo the calculation. We'll redo it over here. So let's go ahead and do it. Let's V1 equals R1. What's R1? 200 now. 200 ohms times V. What's V? Still 12 volts. Over the sum of these, which is 200 plus 1000. So let's just write it out this time. 200 plus 1000 ohms, or 1k ohm. All right. That equals whatever it equals. V2 equals, what is that? R2. What's R2? 1000 ohms. Times 12 volts over the same denominator, which is 200 ohms plus 1000 ohms. All right, so let's do the math. 200 times 12, 200 times 12, 200 times 12 equals 2400 divided by the sum of 200 plus 1000, which is of course 1200. So that gives us 2 volts. Again, let's do the bottom calculation here. 1000 times 12, 1000 times 12, of course, better be 12,000, divided by the denominator, which again is 1200, 200 plus 100, 1200, and that better be 10 volts. And again, notice that they are the same. Right here, there's our 2 volts, and there's our 10 volts. All right, and the exact same as we calculated. So the ratio doesn't matter. So, okay, so wait a minute. This should set off some red lights. So if the values of the resistors don't matter, then what's going on here? Why are there an infinite number of resistor values? The reason is the voltages will stay the same, but the current changes. So this current I does indeed change, but since that same current drops over each one of these or goes through each one of these resistors and generates a voltage, right? The voltages stay the same, but the current is actually less. Let's figure out what the current is. Now in the first case, when we had the 20 and the 100 ohms, right, we figured out that it was 100 milliamperes. So we increase the resistances by a factor of 10. Our intuition should tell us that V equals I times R is a linear equation. The current should now increase by 10 or decrease by 10. Decrease by 10, because we're going to increase the resistance. Let's see. So what is the current? Well, it's simply the voltage divided by the total resistance. What's the voltage? It's 12 volts divided by what's the total resistance? 1200 ohms now. 1200 ohms. And now when we do this, we have 10 milliamperes. So now when we do this same equation, I equals 12 volts over 200 ohms plus 1000 ohms, we get 10 milliamps. All right, so we had 100, now we have 10. So we decrease the amount of current. So what use is this? So obviously, if you have a large signal or a large voltage, you can use a voltage divider to decrease and scale the voltage. You can scale it down. You can never make it bigger, right? We have to use amplifiers or transformers to do that. So you can't make it bigger, but you can make it smaller. Now, when you pick your resistors to do this voltage divider, the question is, well, how do I pick them? Do I just pick one of them, and then solve for the other one? And then what scale should I make them? The answer to the question is, well, how much current do you want flowing in the circuit? All right. So one way to do this is to say for example, we wanted to set the current to, let's say that we wanted to set the current to 1 amp. Okay, so we want 1 amp of current in the circuit. So that's what we want, all right? And so let's just write that down. We want 1 amp is what we want. We know that V equals I times R, and we know that we have a voltage of 12 volts, so let's just figure out what the resistance would be. So 12 volts equals our current, which is 1 amp, times our resistance, and therefore divide both sides by 1 amp, and we have our resistance equals 12 ohms. So we know that the total resistance of R1 and R2 needs to be 12 ohms to set up the current of 1 amp. Now all we need to do is figure out what the values of R1 and R2 are. And there's a lot of ways to do this. We've got, some ratios here. We've got, a number of different ways that we can do this. And so, I'm not going to go through all of them. We'll just kind of look at the most obvious way. So, one way to do it is we can simply look at one of these equations here, right? Either one of these equations will do the job. And so the first equation says that V1 equals R1 times V over R1 plus R2. All right, so V1 is, we want to maintain the voltage ratio. So the voltage is going to stay the same. So we're going to get 2 volts equals R1. That's what we're looking for. What is the R1 that makes this true? Times V, well, that's just the 12 volts, over the total resistance R1 plus R2, but we actually know that that's 12 ohms, right? So we already know what that value is. All right, so now we can simply simplify this, and we have 12 volts over the 12 ohms, that's just 1, and then we've got R1, and then this is going to, this is 2 volts here, so R1 is going to end up being 2 ohms. All right, so so in this case we could run this through if we want, but regardless, the volts are going to cancel out and we're just going to be left with ohms here. All right, so R1 is going to equal 2 ohms. All right, then we can do the same thing over here, and we have V2. So what's V2? It's 10 volts, and that's what we want. And then R2 we're trying to find, and times V again, which is 12 volts, over the total resistance again, which is 12 ohms. And again, if you just move these things around, you're going to end up, the 12 and the 12 cancel out, the volts cancel out, and the ohms invert, and then we just get, this just turns to 1, so we just get R2 equals 10 ohms. All right, and that makes sense. If we had 100 milliamps, if we now just decrease the resistors again, instead of 20 and 10 ohms, 100 ohms like we did them, now they're 2 and 10 ohms. All right, so and again, you can look at these ratios and figure things out as well. So the whole thing here to remember, let's erase all this. Let's just erase all this so we can see here a little bit better. The whole thing to remember about voltage dividers is this simple little fact here. You've got 2 resistors like this. We've got a voltage V, which is the same voltage over here, right, to ground, right? This is V right here as well. And we're calling this R1, we're calling this R2. This is going to drop plus to minus. This is going to drop plus to minus. We call this V1. We can call this V2. The bottom line is this, is that the current through here is a function of the sum of these 2 resistors. So the voltage drop is linear. So whatever we have as the voltage over here, part of it's going to drop over R1 and part of it's going to drop over R2. The part of it that's going to drop over R1 is simply R1 over the total resistance, which is R1 plus R2. The total, the voltage that's going to drop over R2 is R2 over R1 plus R2. This is just very, very simple ratios. It's just R1 over the total sum and R2 over the total sum. And then we scale that times the voltage. V times that, right? And this whole thing here is going to equal V2, and this whole thing here is going to equal V1. So again, just realize that it's just simply the resistor over the total resistance, the other resistor over the total resistance, and times the voltage. That percentage of the voltage is going to drop over each of these resistors. Now, I want to bring your attention to something specific though, and that is the voltage at this node right here. You want to be a little bit careful about this. These voltages we compute, V1 and V2, they're the voltage drops over each one of these resistors independently. But they're not the voltage at the nodes. That's always relative to ground. Now, if you have a circuit like this where R2 ends up at ground, then V2, right, is identical to this node voltage, right? So whatever V2 is, say for example, that V2 ended up being, say 3 volts and V1 ended up being, say, 5 volts, then we know that there must have been a total of 8 volts here. 3 volts dropped here over R2, But since this is at ground, this node here must be at 3 volts. If this node is at 3 volts, and we know that 5 volts dropped over this resistor, then this node must be at 8 volts. And it has to be because it's the same as this node here, which always has to be at 8 volts relative to the ground here. So anyway, keep that in mind. If this voltage here is not ground, then you have to adjust these things so that your calculation is correct. Just be careful. All right, but very simply, it's just a ratio. It's the resistor that you're looking for the voltage drop over the total resistance times the voltage, and it's the other resistor over the total resistance times the voltage, and that's it. That's all a voltage divider is. Super simple. Now, one reason that you might want a voltage divider, let's get rid of this, is we may want to, so let's say, all right, so let's jump ahead of ourselves a little bit here, all right? Let's jump ahead of ourselves a little bit. Let's say that we have some signal here, all right? Let's say that we have some signal here. And and let's say that this is kind of a digital signal, all right? So let's say that this is a digital signal. In fact, let's do this. Let's kind of draw this sort of how this would kind of be. So say we have this digital signal here, all right? And let's kind of do a fun example, all right? And let's say that our digital signal is going to go up to 5 volts, and here's 0 volts right here, and 1, 2, 3, 4, 5, 6 onward. Let's say that this is time here, all right, the time axis T. All right, and then let's say that our digital signal is looking something like, and we don't care what the scale of it is, how fast it's going, but we're just doing this as an example. And let's say it's 0, then it goes up to 5 volts, and then it goes back down, then it goes back up, then it goes back down, then it goes back up, and so on. All right, it just does this. All right, and let's draw that a little bit better. Oops, well, let's do it again. All right, let's go up. These are totally flat. All right, even though I'm not drawing them totally flat. These graphics tablets are surprisingly difficult because you're looking at the screen and drawing on something else. You got to get really used to it. Okay. All right, so we have this scenario right here. All right, and then this signal, right, whatever this is, let's just call this, we'll call this signal, S1 for signal 1. And here it is here, it's S1. So here comes S1, and it's, coming down. And S1 is relative to ground. Okay, so it's relative to ground. We have this S1 signal, which represents, we don't know, we don't care. And now the problem is we need to scale this down because maybe the thing that we want to talk to is a 3.3 volt system. So this is a 5 volt system here, and we want to talk to a 3.3 volt system over here. All right, 3.3 volt system over here. And let's just draw that again, 3.3 volt system over here. All right. So we want to scale this voltage down. Now there's lots of ways to do this. There are things called level translators and all kinds of things, but we can do it with a simple voltage divider. All right, so here's what we're going to do. So when the voltage is 0, we want to get a 0 out. And when the voltage is 5, we want to get a 3.3 volt out. All right. All right, so let's see if we can do this with a voltage divider. All right, so we're going to take our circuit here, and we're going to put a resistor here, and we're going to put another resistor here. All right, and we're going to call this resistor R1, and we're going to call this resistor R2. All right, and again, we can label things here. We'll call this V1. We can call this V2. But the thing that we're really interested in is this node right here. All right, and I'm going to call this, we're going to make this another signal, and this output right here, and we're going to call this, how about we're going to call this, this is S1, so we're going to call this S2. And matter of fact, let's draw that in a different color so we can kind of see it better. And how about orange? Okay, so this is S2. So S1 is from a 5 volt system, S2 is a 3.3 volt system, and we want to make sure that if we send the signal in here, we get out 3.3 volt pulses and not 5 volt pulses, okay? So that is the statement of the problem. Now, one thing is we're going to connect this, say, digital I/O, right? So the term here is you might call this a general purpose I/O or a digital I/O, GPIO. You might hear that term when you start doing microcontroller stuff, general purpose I/O. All right. And one thing is these GPIOs can only source and sink so much current. All right. So typically their current limits are on the order of about 10 to 25 milliamps. All right. So whatever we do over here, we're putting a circuit to ground here, and we want to be careful that we don't draw too much current, right? In one case. In another case, we want to make sure that we can pull enough current from it so that it can be useful to drive something else maybe. But let's say we're going to make one kind of concession. We're going to say whatever S2 connects to has a really high resistance. So it's a lot of current is not going to go in this direction. So in other words, this IS2 is going to be very, very, very small. All right. So really all we care about is generating the proper voltage, and we don't care about how much current is going to go this direction because we know it's going to be very small. But maybe we want to get like 1 milliamp or 2 milliamps, something like that. So what we want to do is we want to set up enough current in this circuit so we can pull off some of this current without distorting this 3.3 volt voltage divider. So this is a very common problem that voltage dividers are used in. And if you want to do a simple kind of hack. If you want to do this correctly, there's other ways to do it with transistors or FETs and all that, but we're going to just do this. So again, we're not going to mull over this too hard. We're just going to say, all right, let's set this up so that we have a total of 10 milliamperes flowing through this, all right? So when this thing turns on, it's going to burn 10 milliamps. All right, so that's number one. So we're going to set it up for 10 milliamperes. All right. If we're going to set it up for 10 milliamperes, that's what's going to flow here. So our first problem is we need to find what the total resistance is to get 10 milliamperes out of the circuit. All right. So we have 5 volts here. So let's write down our equations here. Let's put our we'll put our Ohm's law up here for reference. And again, it's always nice just to have it. Okay. We want to compute R. So R total equals V over I. V over I. In this case, what's the voltage? 5 volts. What's our I? 10 milliamperes. This is going to tell us our R total, and R total is basically these two guys right here. And this is how you do circuit design. You kind of first figure out the big part of the problem, and then you kind of break it into pieces and drill down to what you want. So 5 volts divided by 10 milliamperes equals 500 ohms. Okay. Equals 500 ohms. So we know that our total is 500 ohms in total, all right, if we want to flow this 10 milliamperes right here, okay? All right, and let's see here. Okay, so now we can basically use a number of different techniques, but let's use the voltage divider equations to kind of see if we can solve for this, all right? So let's get a different color here. Let's get this color. All right, and what did our voltage divider equations say? So they said that V1 equals R1 times the total voltage, V, over R1 plus R2, and be careful, that's in parentheses. And it said that V2 equals R2 times V, and that's always V source of the source, over R1 plus R2. Okay, so, and these are our voltage divider equations. So voltage divider equations. All right. Okay. So we know that when the system is high, we're going to have 5 volts right here. All right. We're going to have we're going to have 5 volts up here at this node right here. Right. We're going to have 5 volts right there. And so that's our V. All right. And then we know that at S2 we want to have 3.3 volts. Okay. So now we more or less have everything we need to know. So this has got to be 3.3 volts when this is 5 volts. We also know that the total resistance has to be 500 ohms. So let's see what we know here. So what do we know? Do we know what V2 is? Yes. V2 is 3.3 volts because we want it to be 3.3 volts relative to ground, so that's easy. Do we know what V1 is? Yes. V1 must be 5 volts minus 3.3 volts, right? Or 1.7 volts, right? So we can say V1 equals 1.7 volts, all right? Okay, so now we have everything we need to know. Let's take a look at one of these equations. Can we use one of these to solve? So let's use the one that actually has R2 in it, because that's what we first want to find out, right? Let's figure out what R2 is. So this one right here. V2 equals R2 times V over the sum of R1 plus R2. So let's start plugging things back in. Do we know what V2 is? Yes, it's 3.3. 3.3 volts. Do we know what R2 is? No, that's what we're trying to find. Okay. Do we know what V is? Yes, we do. V is the total V of the voltage divider, which is 5 volts. All right. Do we know what R1 plus R2 is? We don't know what R1 is. We don't know what R2 is, but we know their sum needs to be 500 ohms. All right, and I think you can see where we're going with all this. Okay, so 3.3 equals R2 times 5 volts divided by 500. All right, so all I'm going to do is I'm going to do this algebra and then figure out what R2 is. All right, so we're going to take 5 divided by 500. All right, and then I'm going to take that number and then I'm going to invert that. And I'm going to multiply that times 3.3, and that's 330 ohms. All right, so equals 330 ohms. So R2 is 330 ohms. 330 ohms. We could do the same calculation and use this equation here, but we don't need to because we know the total is 500. So we know that R total equals R1 plus R2, right? Which we know that 500 equals R1, which we're trying to find, plus R2, which is now 330 ohms. Therefore, R1 must be 500 minus 330, right? 500 minus 330. And again, just play dumb when you're doing arithmetic. You'll make mistakes. Let the calculator do it in your head, and then let the calculator do it also. And that way, you'll usually, between the two of you, you'll be right. 170 ohms. So where are we here? We'll write it right here, 170 ohms. So that's it. So if you build this circuit and you put a 5-volt signal oscillating like this through the circuit, and you put a 170 up top and you put a 330 resistor in the bottom, you're going to get pulses. Instead of 5-volt pulses, you're going to get 3.3-volt pulses. So you've in essence did a level translation from a 5-volt system to a 3.3. So this might be 5-volt TTL to low power TTL, 3.3 volts. All right. So I think now, and then one little, let's talk about one little thing here, and I think we're ready to go on the bench and play around here. We've done enough theory. One thing I wanted to talk about was we said that the current going through this node here, going out S2, was going to be very, very small. In other words, and I want to use some terminology here. In other words, whatever we connect here, this resistance to ground, and that's a horrible ground. This resistance, I'm going to call it RL for R load, okay, or R load. The whole idea here is we've created a voltage divider, but if we put another resistor in parallel with R2, we're going to change what R2 is. Now, R2 is 330 ohms. So if we put another resistor that's 10 times larger than R2, then the effect this RL will have on R2 will be very, very small. So in other words, it's not going to change its resistance too much. So we're not going to load it too much. So this voltage isn't going to change too much. All right, let's do an example. So let's just use common sense here. So if I, for example, use a 10 times larger resistor, so say that our load resistor was 3.3 K ohms. So what's the parallel combination of 330 and 3.3 K? Let's do it. So 330 parallel with 3.3 K. So remember, it's the product over the sum. So the product, 330 times 3.3 K over the sum, 330 plus 3.3 K. Let's get our calculator and let's do this. Now watch this. 330 times 3.3 K divided by, make sure you use your parentheses, 330 plus 3.3 K equals 300 ohms. So the result of adding this impedance, this load resistor, over here of 3.3K modifies this resistor and decreases it to 300 ohms as the equivalent resistance. Therefore, the voltage drop over it's going to be a little bit less than 3.3 volts. It's going to change. It's going to be 3.2, 3.1, right? It's going to decrease because the voltage divider action is going to change because the voltage divider, instead of seeing 330, is now going to see 300. But this is tolerable. It only changed it by 10%. So that's okay. 10% we're fine. However, what if we made this, instead of 3.3K, what if we made it 100 ohms? Okay? What if we made it 100 ohms? Well, let's do that calculation. So now we have 330 in parallel with 100 equals 330 times 100 divided by 330 plus 100. Let's do the math. So 330 times 100 equals, divided by quantity, 330 plus 100. 76 ohms. So that equals 76 ohms, all right, 76 ohms. So, hopefully you can see this is not getting covered. 76 ohms. The point is, when we add the 3.3K, we get a resulting impedance or total R2 with a load of 300. But if we change the load to 100 ohms, this drops down to 76 ohms. In other words, we don't have 330 anymore, we have 76. This voltage is going to radically drop, and we're not going to have what we want anymore. So the point is that when you do these voltage dividers, whatever the load is you're going to put on it, make sure that the load is at least an order of magnitude larger so that the voltage divider maintains its voltage divider action or its stiffness. And it's called stiffness, like a spring, because if you add something to it, it doesn't change it that much. Ideally, you want it to change 0. That would mean you'd have to have an infinite impedance here, right? So we can't really do that. But anyway, we set the current up, and these resistors are pretty low so that this thing, does what it does. Now, if we needed this to be stiffer, we could increase the current to 100 milliamps and turn the total resistance to 50 ohms. Then we could change these two resistors to 17 and 33 ohms if we wanted to. Then it would be 10 times stiffer. Then if we added smaller resistors, it would still maintain the voltage divider action, but we're burning 100 milliamps every time the GPIO turns on, right? So we don't really want that. Okay, so now that we've kind of done this, we've talked about voltage dividers, we've done the math, let's actually do an experiment right now. Let's get onto the bench and let's build a little voltage divider and let's put a voltage to it and let's do something very similar to this right here, and we can see if we can find a 330 and something around a 170, and we'll do a 5 to 3.3 divider, right? So meet me over on the bench and let's go do that. Okay, so we're over here at the bench, and what our goal is to kind of mimic what we did over there. We're going to have a 5-volt supply. We're going to have a voltage divider with 2 resistors, and we're going to try and turn 5 volts into 3.3 volts with magic. All right, so let's go ahead. And so I've looked around, and I wasn't able to find 170 ohms, but I think I found 180 ohm. So first, here is our 330 ohm. So let's take a look at that under the zoom camera. All right, let me zoom in there. And that's orange, orange, brown. And let's, let's sanity check ourselves here. All right, so that's going to work. And let me get the meter there so you can see it. All right, and there we go. We've got on resistance and 0.3 K. And let's just, this particular meter, yeah, I think it has a maximum range of 200 ohms, so you have to put it to the K range. Yeah, so this kind of sucks. You have to put it to the K range. I don't really like that. Let's use a different meter. And like I said, a lot of times these meters have ranges, and if something's in between the range, you got to go to the next range, and you may not like it. So again, that's another reason why I have many meters. All right, so now it's in auto range mode. So let's go here and let's measure this. All right, and it's auto ranging, and there we go, 327, 330 ohms is supposed to be what it is. So, okay, all right, so we got that, and then now we've got our other resistor right here, and this is 180 ohms, supposedly. Let's take a look at it. And 180, this would be brown, like gray brown, I believe. All right, and let's measure that. Let's measure that over here. Okay. and get our meter here again. Okay, and we're looking for 180 ohms. Perfect, 180, 178. Okay, so the circuit that we're trying to make here is we're going to come in from the power supply, all right, and the power supply is going to be up top here, and that's going to be where we're going to bring in our 5 volts. Then we want to have our smaller resistor, our like our 180, all right, and we're going to put that right there. And then we want to have our larger resistor, which is like our 330, okay, and then we're going to take that and we're going to go to ground, okay. So all right, so that's as simple as it is. All right, so we're going to get our meter here, and so we're going to apply 5 volts to here, and then the question is, will we have 3.3 volts over our resistor? So let's give it a try. So we'll put the meter into voltage mode. All right, I'm going to turn the power supply on. The power supply is on, and all right, so first let's verify that we have 5 volts coming into the system. We have 5 volts, good. And we should have 3.3 volts, or roughly 3.3 here, and we sure do, 3.25 volts. Okay, now let's go ahead and let's load this. So let's load it with, say, let's find a 10K resistor. Let me find a 10K resistor. Here's one right here. All right, so say we want to take this signal and we want to send it someplace in our circuit, and that impedance of that, wherever that's ending up, is say 10K, all right? So now we're going to take that signal, and let's use this right here. All right, so now remember, this is the node. This is the output right here. Be careful. All right, so there's the output right there. All right, so now we still want to maintain this 3.3 volts here. So let's see what it actually is. So is it 3.3 volts? We know that it's not going to be. We know that it's going to be slightly less because we've loaded it, but we loaded it with a very large resistor, and the resistor is 30 times larger than the R2 resistor of 330. So we're loading it basically by 3%. So we should see very, very little deviance from the 3.25 volts, but let's check it out. So here we go. We're going to go from ground here, and we're going to go right here. It's the same node. And sure enough, it's 3.21 instead of 3.25. So the 10K load is just fine, no problem. So 10K load is just fine. Now let's go to a 1K load. 1K load. Here's a 1K load, brown, black, red. On the zoom camera there, brown, black, red. There we go. And we'll just move our load and put our new load in here. All right. So we've got that. Let's put our meter back so we can see what's going on here. Now we expect to have much, much greater deviance. The reason why is this load is only 3 times bigger than the R2 resistor in our voltage divider, so it's going to destabilize this quite a bit. So let's see what it does. So here we go, and now we've got 2.9 volts. So almost 3 volts. Now, if this is a 3.3 volt system, we'd still be fine. It would still register as a digital high, so we would be okay. All right, now let's go and really load it. And let's go ahead and put a 100 ohm resistor here, 100 ohms. Now we're done. This is just going to brutalize it. Now we're going to load it all the way. So 100 ohm resistor, and our poor little voltage divider is going to give in. All right, so again, let's take a look. So what's the total voltage of the system? Again, and my meter is not cooperating with me. There we go. Something happened there. Okay, there we go. 5 volts, all right, and now let's check out what our voltage is. It's 1.48, 1.5. That's it, we're done. So now we've completely loaded the system way too much. So in essence, we've learned that 1K or higher is probably okay if we're going to do a 5 to 3.3 volt system. Okay, so now let's go ahead and let's put back our load resistor, our 10K load resistor. And let's have a little bit of fun and end this out, all right? Okay, so the first thing that I'd like to do is we are going to undo the power here. So let's undo the power, and instead, let's go ahead and let's inject a signal from our signal generator, right? So let's inject a signal from our signal generator. Now here's our signal generator. And so we've used this before, so let's go ahead and grab channel 1 here. All right, we're going to grab channel 1, and each one of these channels has 2 clips, right? And alligator clips, and so the signal plus and the signal minus is going to be right there. So we're going to plug this into our circuit. So this is going to go into our circuit. So back on the other camera here, we're going to go ahead and we're going to put that. All right, now on our signal generator, here's the output button. We're not going to turn this thing on. So it's on channel 1 right now. It's at 60 hertz and 20 volts peak to peak. Well, we don't want that, do we? That's way too much voltage here. All right, so what we want to do is we're going to lower this down to 5 volts. All right, we're going to lower it down to 5 volts. And let's go ahead and let's just increase the frequency to make it something fun. Instead of 60 hertz, let's make it a kilohertz. So 1 kilohertz. All right, so it's 1 kilohertz. It's a 5 volt signal. All right, and let's do a square wave. So we're going to do a square wave. So this is modeling exactly kind of what we had. All right. Now, to confirm that we have this, I'm going to turn this on, but what we really need is the oscilloscope so that we can see what the signal is, right? So what we can do is we can go and we can connect up the oscilloscope to the input, and we can monitor and make sure that we're getting this 5 volt signal. So let's go over and set up the oscilloscope as well. All right, so let's go and take a look at that. Okay, so now we see the oscilloscope here, and I'm going to go grab channel 1 here. All right. And these probes are always someplace where they shouldn't be, but all right. And the probe looks like this. All right, and it's got, this is the ground, and then this is kind of what we grab things with. So we're going to hook this to the plus and this to the ground over on our board. All right, so I'm going to do that right now, so you should be able to see that process going on the other camera here. So let's do that. All right, so that's going to be our input signal. Okay, good. Now, let's go ahead and let's kind of set up our oscilloscope to kind of read what we think we're doing here. So the first thing is we are looking at channel 1, that's good, and then let's put the amplitude as 1 volt per division, and then the sweep, let's put it at, we want to look at a 1 kilohertz, so let's put this, say, at 40 microseconds per division. We should be able to see it. All right, so now what we're going to do is we're going to turn on the signal generator. That's going to generate this 5 volt square wave, which we should see on here, and then we can start measuring on the actual board. All right, so we got a lot of things going on here. So here we go. So we're going to turn it on. All right, so I've turned it on. Now you can see the square wave on the oscilloscope. So let me change the horizontal timing a little bit. Okay, let's look at its amplitude. We'll press the measure button. The frequency is 1. All right, and then the, let's see here, let's go to cursors, and let's measure voltage. All right, we're going to measure channel 1. Let's move this one up here, and then let's move this one down here. And, you know, every time you get a new oscilloscope, you got to figure out how it works. All right, and so we've got our 5 volts here. Oops. All right, we've got our DV of 5 volts here. All right, now one thing is we want to make sure of is, let's do this, get rid of this. We're going to go to channel 1 here. We've got DC coupling, and what this is showing, so this is important. Right now, what's happening here is this is ground, and it's showing that half the signal is going high and the other half is going low. This is actually an AC signal. We want ground to be 0. This is a digital system we're trying to simulate, so we don't want anything going below 0. So the oscilloscope is actually telling us we're going below 0. So that means our signal generator, we've got the offset incorrect. Not incorrect, but we just have it set for an AC signal. We need to up the offset so that we're going from 0 to 5 volts and not negative 2.5 to 2.5. So I'm going to go over and fix this right now. So I'm going to go over and fix this. You can probably see it getting changed over there. Okay. And now I'm increasing it to 5 volts with an offset of 0. So that's what I want. Now let's move this back into position here. Okay. And now we've got our 5 volt signal. We've got 1 volt per division. So if you count this up, 1, 2, 3, 4, 5, it's 5. We can also press measure. All right, and we're getting our 1 kilohertz, and then we can press this little button right here, and we can kind of measure different things. And we want let's see here, peak to peak, maximum, all right, is 4.64 volts, all right? So that's good enough, close enough for what's going on here. Okay, so we've got our signal. We've got our signal generator. We're looking at it with the oscilloscope. And now we want to see what's the signal coming out of the other node. All right, so this is where the power of the oscilloscope comes into play. So what we're going to do is look back here at our circuit. And we know that here's our load, so we're going to put another oscilloscope probe on here, channel 2, and we can look at them simultaneously. That's why you want to have many, many channels on your oscilloscope, all right? So let's go ahead and let's get the other channel of the oscilloscope, and let's snake it through here. Bear with me. All right, so I got this. Okay, here we go. And here it is right here. So now what I'm going to do is we have to attach it here and then common the grounds, all right? So we'll connect the ground up here, getting messy, just the way it is. Okay, now there we are. So we're all good. Let me just zoom in a little bit on that so you can kind of see that. Okay, so we're looking at the load resistor, the voltage at the load resistor, which should be about 3.3 volts. We've got this 10K resistor. Now, back on the oscilloscope, you're looking at the oscilloscope. We're seeing channel 1 right here. So let's go ahead and let's add channel 2. So there's channel 2. And now let's change the scale to 2 volts per division. Let's move channel 1 up a little bit. Now, here's channel 2. And now we're going to put channel 2 at the same, we're going to put it at the same 2 volts per division. All right, and we'll move it down vertically here. Now we see that what's happening here is we're losing tracking here. All right, and then now we have it back. And there we go. So the tracking works, or the triggering, is based on an edge of the signal or the high or the low, and we can set it up here. It's on channel 1 right now, and we have to make sure that channel 1 has a rising edge so it can lock onto it. Okay, so now we see that we have both signals on here, and the top signal is our, of course, 5-volt input signal, and our output signal is our voltage divided signal, which we are hoping is about 3.3 volts. So let's go ahead and let's measure them with, and another thing, take a notice, take a look. They're identical. So in time, there's no lag, all right? Because there's no capacitance or inductance. These are just resistors, so there's going to be no lag. So if we keep, going like this, these edges will be dead on each other. Now, if there was capacitance and resistance, that wouldn't be the case. All right, let's measure these values and let's see if we're getting this 3.3 volts out. So what we're going to do is we're going to turn cursors on. Let's go to channel 2. We already know that channel 1 is okay. All right, and we're going to move the top cursor here. And when you have all this noise, it's like, where do you do this? Well, you can kind of do it in the middle. You can kind of do it at the top. You just come up with a convention and kind of stick to it. All right, and then we'll go to the bottom here. All right, and so we're looking at about 3 volts. All right, so considering that remember, our signal generator is not actually putting out the full 5 volts. Why? Because we're loading it. Since we're loading it with these resistors, so see the resistors here, we're loading it. And remember I told you it can't tolerate driving a lot of current. And because of that, we're not actually getting the full voltage that we would expect. We're getting less. So if we go and look at channel 1 here, and we look at what the voltages are on channel 1, all right, okay, we're getting like only 4.5 volts out. So the voltage divider action is working correctly, but we're getting less. So what we could do is we could adjust this a little bit to offset this. So what we could do is let's make sure that we get 5 volts. So what I'm going to do is I'm going to actually increase this artificially over here. All right, about there. And then so on the signal generator, I just increased the amount of voltage a little bit. And now let's measure. So now, okay, now we're a little bit better. So now that probably went over a little bit. Let me go down. Okay, so I think now we're good. And if we put that in the center there, it's saying about 5.2. Let's go down a little bit more. All right. And there we go. So now that's 5 volts. So now we should have about 3 volts, 3.3 volts for our other channel. All right. And again, this is a process. It's not quick and dirty. You're going to be here. So, set some time aside because this is going to take you a long time to do this and run these experiments and get everything to work right and all that. All right, and it's a slow, tedious process. But now look at that, 3.36 volts, almost perfect. All right, so I had to adjust the signal generator and put it up to 5.5 volts so that we got a clean 5-volt square wave out of there because of the loading of this circuit right here. So now, so that's it. And so now now let's do something here. So what I'm going to do is keep you on the oscilloscope. I'm going to turn the frequency up now. It's at 1 kilohertz right now, and let's start turning it up. And the ratio should stay the same. There's 2, right? And then you can see right here, and let's actually put measure on here so you can keep an eye on this. So this is channel 2 here, and it's saying it's 3.5. And again, you got to take this with a little grain of salt, the way that it's doing things, but it's going to roughly stay the same. All right, 6 kilohertz, 10 kilohertz. All right, and again, you see that it's not wavering at all. And the reason why is because there's no reactance. And now it's going so fast, we can open this up and sweep at a higher frequency. All right, and we're at 310 kilohertz, and now we're at 400 kilohertz, 500 kilohertz, 600. Now we're at a megahertz, and again, it's totally identical. And the reason why is because we don't have any impedances or reactances, so nothing is happening weird here in the AC with this signal changing, because we have pure resistive circuits. Now, in reality, these resistors are actually have a little bit of capacitance and they have a little bit of inductance. So if we keep cracking this frequency up, we're going to start to see those effects. But we'll see the probes will probably degrade far before the resistors do. So just for fun, I'm just going to go crazy here. And there's 30 megahertz, 40 megahertz, and that's it right there. So with this signal, the best I can do is 40 megahertz, and the square wave is degraded into that. All right, it just cannot maintain the square wave, but I can put it back into a sine wave, and that's kind of what's left of it. But you can see again, we're still at about 3 point something, right? So the voltage divider is maintaining operation even up into these high megahertz ranges, okay? So anyway, so that's a voltage regulator, That's a voltage divider, and a very useful device, but you have to take into consideration your loading, how much current it's burning when it's turned on and turned off, or if it's always on, and what the stiffness of it is, and so forth. And we saw that the equations are very, very simple to do the calculations, and it's a really, really useful device. So next we are going to, in the next lecture, we're going to do some simulation, very little. It's really not part of what we're going to be talking about. It's an advanced topic, but I want you to at least see it and kind of we'll play with some simple circuits. Actually, these voltage dividers will play with simulation so you can kind of see what those are all about. So that'll be a lot of fun, totally on the computer, and kind of an easy lecture. Okay, so I'll see you in the next lecture. Bye-bye. Now, one thing I just want to put in your brain is that the voltage divider action is going to be the same whether it's a resistor as the element or an inductor or a capacitor. And then a little bit later, we're going to learn that we generalize these things and we call them impedances. And these impedances can be real or reactive or a mixture of the two. And so the resistor is a completely real impedance, whereas the capacitor and the inductor, these are reactive impedances. So again, we don't want to get into too much of the analog theory and that kind of material. We just want to know how to use them. But the idea is that whether it's a resistor, capacitor, inductor, these techniques will still work as long as you do the math correctly. Okay. All right. So in this lecture, I wasn't going to do this at first, but I thought that I really do want to show you this material, is we're going to talk about SPICE. And SPICE is a simulation technology used for circuit analysis. All right, so if you look at over all the notes, here we are in some of the voltage regulator material, and we kind of went over all this, and we talked about loading and even how to make a little voltage regulator. We can pull current from something and so forth. So if you can read through all these notes yourself in this chapter, and let me just scroll through here until we get to the point that I want to get to. And so we did basically all of these things we did on the bench and with our example on the Blackboard, the computer virtual Blackboard. All right, so we are going to just skip down to this coverage of SPICE. And SPICE is it's an acronym. And honestly, I don't know. Sometimes when I hear acronyms, I'm like, they reverse engineered this after the fact. Simulation program with integrated circuit emphasis. I don't know. I don't know. Anyway, but that's what they say it is. So simulation program with integrated circuit emphasis, SPICE. And so originally developed at UC Berkeley in California. And it's a simulation technology, and it's a language so that you can describe circuits, and then you can run a DC analysis, transient analysis, you can sweep voltages, you can do AC analysis, and at the end of the day, it's a very, very complex piece of technology. So, if you look at some of the history of it, SPICE has been around since 1973, and here's the Wikipedia page. 1973, that is just crazy. And I probably started using SPICE in the 80s, so probably this version, this 2G6 version. Anyway, so SPICE is a technology, and you can read about it here and all the different information about it. There are books and courses just on SPICE. And unless you use SPICE all the time, what most engineers tend to do, and I don't want to generalize too much, but I think this is probably true. If you don't use it all the time, you use it once in a while, then you kind of forget about it. And, and that's how it is. So, what's happened, over the past, I don't know, 2 decades or so, is lots of SPICE engines have had Windows or GUI applications put on top of them to make them a lot easier to use, because no one really remembers this language, right? It's like you could make a website with a text editor and HTML, right? But who would want to do that these days? And some people still do, but it's too graphical. It's dragging and dropping is more, what people do these days, and then maybe writing some behaviors and adding some code. And if you're a software engineer or a web designer, you know that that's kind of how you do it. You wouldn't want to sit and write you wouldn't want to write Amazon.com with a text editor. And the same thing with SPICE. You have these complex circuits. You don't want to type out a description of the circuit. You just want to draw the circuit like you would in schematic capture. So typically what we're looking for are SPICE simulators or programs that allow us to draw our circuits. Now, most big CAD programs, schematic entry and PCB layout, and again, in the second part or in the latter part of this course, we're going to start playing with Circuit Maker, which is an Altium free product, right, which you know about. But it does not have simulation in it. Now, the big Altium product, of course, has simulation in it, but they don't have that yet in Circuit Maker. But I hear that it's going to be put into it at some point, so that'll be cool. However, many high-end CAD programs, PCB CAD programs, do have built-in simulation and built-in SPICE. And in fact, not just SPICE, but they simulate entire microprocessors and microcontrollers. And one of the pieces of software that I use is called Proteus by a company called Lab Center in the United Kingdom, which is one of my favorite pieces of software. I've used it for many years. And we're going to actually take a look at that to kind of look at the high end of simulation. So what I thought we would do is I want to look a little bit at the language. Then we're just going to go and try some random SPICE applications. And many of these I've not played with at all, or at least just momentarily. So you'll see, how I go about kind of figuring it out and working with them. Just like anything, piece of software, you got to read the manual, you got to experiment with it and figure out its little quirks. One thing I will say is, so I am going to make a generalization now. Software engineers and hardware engineers think completely differently, I believe. And so since I do both, it's kind of like I bridge the gap between my right and left side of my brain. And one thing is that software engineers like really slick pieces of software. They like really nice, developed, graphical pieces of software that do what needs to be done. And when you point at something and click or drag it, it should point and click and drag. Electrical engineers don't like computers so much. They use them as tools, but they like building computers. They like building circuits. So they don't tend to use a whole lot of software, right? So they're comfortable using things that really have bad Windows paradigms. In other words, a lot of the software you're going to see in engineering for hardware development, you're going to look at it and go, this looks like it was made in the 80s or the 90s. It looks like it's a DOS program ported to Windows. What is going on here? The graphics are horrible. The keyboard control, the mouse control, nothing seems to do what it should do for a modern Windows application or Mac application, right? And that's just because they just don't seem to care. So they get it working and they're like, good enough, I can get it done. And so what you're going to notice is you're going to use these programs. They're going to be painful to learn because they're going to be the opposite of everything else. When you use a nice application like a Adobe application, or use a Microsoft Word application or a PowerPoint or whatever, these things seem smooth. They seem user tested. But engineering applications are different, especially when it comes to hardware development stuff. So brace yourself for things that just don't work as clean as you would expect, and you got to figure them out. So I'm warning you about that. And it's almost kind of funny because it's 2016, 2017, and you look at these programs and you really do think they're from the 80s or 90s. It's just like, wow. So anyway, just little words of caution there. All right, so the SPICE language. So what I want to show you here in the SPICE language is just some syntax. And since we're all software people here, ideally, it should be pretty easy for you to kind of put this together. So, I would assume you're a C programmer or JavaScript or Java, some C-based language, and so this will be very, very easy. So looking at the screen here, what we see is a simple circuit. And what you do when you're developing a SPICE program is you draw your circuit like you would with all of your components. And you've got your voltage sources, you've got your passive components, your capacitors, your inductors, your resistors, you've got your transistors, your active components, your FETs, and whatever, right? But at the end of the day, all of these have to be referenced to some points of reference that we can have contextually to relate to each other, and those are nodes. So I draw the circuit here, then I just randomly go place nodes on it. So typically ground we'll call node 0. So you can see right here, there's a node, right? And then here's a node right here, here's a node right here, and then I say that this is another node right here. All right, so now then once we have these nodes, then we can, using the SPICE language, describe what the circuit looks like, right? All right, so if you take a look at this, one thing that you'll notice, and let me get rid of these, one thing that you notice is our rule is a node is, if you can draw a surface over it, it's the same node. So if you take a look at here, I can go like this, and I can go like that, and I can draw a surface containing both node 0 and node 3. But that's okay. I mean, you can have redundant nodes or aliases, all right? So, okay, so here's our circuit. We've got a 12-volt source. We've got a 24-ohm resistor. We've got a 17-ohm resistor. These things are in series. And then we have a current source here, which is 50 milliamperes. And that's our circuit. So that's all there is to it. So now we say, hey, we want to put this in the SPICE language. And now there's different versions of SPICE, there's variations of it, and there's proprietary versions of it as well, but they all kind of follow the same syntax more or less. And then depending on whoever the vendor is or the version, you might have to do some little things to figure out how to get it to work the proper way. But anyway, let's just jump right in and let's take a look at the syntax. So the numbers here are just decoration. You wouldn't actually put these line numbers here. All right, and this first line right here, this is not included. So the comments are with the asterisk. All right, so The first voltage source goes from node 0 to 1 and it's 12 volts. So then the syntax is V1 goes from 1 to 0, it's DC and it's 12 volts. So if we look back here, node 1 to 0, it's DC, it's 12 volts. All right, so that makes sense. So that's what that line is right there. All right, next line is we say, and we can, let's skip this, this right here. We say resistor R1 goes from node 1 to 2, it's 24 ohm. All right, R1 goes from node 1 to node 2, and it's 24 ohm. So we can see here syntactically, and if you're a compiler designer like myself, you're starting to parse this already, and you're starting to see, okay, we have an identifier, and then we have a node list, right, and then we have a value, right, and that looks like that's the format of these. So R1 from node 1 to node 2, 24, R2 from node 2 to 0, and it's 17. And let's go take a look again here. And sure enough, from node 1 to node 2 is that 24, and then from node 2 to 3 is this 17, or node 0, which is an alias for node 3. All right, okay, and now let's go back up. Now we have this I load from 2 to 0 DC 50 milliamperes. Okay, so now here's this current source here, 50 milliamperes from 2 to 0, right? 3 and 0 alias. And so again, it looks like it's the, when you do this, it's the label, the nodes, and then the value, it's DC, and then the actual value of it, all right? So again, this language is not hard, and it's a little bit quirky, but it's not hard. You can learn it in a weekend, you know, a lot of it in a weekend, and then you can just copy and paste things and kind of make some tweaks. So it's not very difficult, and you kind of code it pretty quick if you wanted to do it. The hard part comes with knowing the directives. You got to look those up. Like here's a directive here. We want a DC solution. So this is called .op or operating point. And this solves the circuit. It uses iteration, solves the circuit for DC. So, and that's what we want to do. So we say, okay, we want a DC solution. Then you have to do some little tricks to get things to print with a print statement. So we have to do this, all right? Then you have to use this is because we're plugging this into WinSpice, which is a Windows GUI on top of this in this particular code here. So just ignore that. All right. And then down here, now we're saying print these things out. So print DC at node 1, node 2, and then print the current R1 through R2. All right. And then again, at the end, you have to put a dot in and so forth. So if you read through all this, this kind of goes over this in more detail. But that's it. So, you know, it's not rocket science. It's just like any computer language. And actually, it's very, to me, it's like basic-ish. It's very basic-like, and just with parameter lists that after each one of these little kind of commands or whatever. So very simple language. All right. So now what I'd like to do is, and then here's some of the prefixes that it uses. So when you're trying to write giga or tera or kila or micro or milli, it uses these. For example, meg, you might think is M, but it's meg. And then milli uses the M. So things like that might get you thrown off if you didn't know it. You might just say M for meg and think it's mega, but it's actually milli. So, you know, you got to read about that stuff. And again, just I'm going line by line here, and then that's that. Okay, so now, and I think that's about it. All right, so now what I'd like to do is, again, we just use the book just kind of as an anchor for things that we're talking about, but what I really want to do now is I want to go through some actual programs, and we are going to try and build some circuits and see what we see. All right, so first thing is you've got your SPICE Wikipedia entry here. You can read up more on it. There's many free SPICE books, lots of classes on it and all that, so you can do that. Now, if you go to Google, for example, and you type in SPICE Girls, simulation software, all right, you will see countless pages and pages of different programs, right? And for example, here's one here. It's just a list in Wikipedia. And this is actually a very, very short list. This isn't a good list. There's probably 200-300 of these. But mixed signal, analog, and digital simulation, which is what we're interested in, and then simulators with proprietary licenses, which we're not really interested in. And then, you know, you can go through here and you can check out some of these. But, you know, take an afternoon and download some of these things, try them out, play with them and all that. Now, what I've done is I have actually played with a few of these, and then the ones that I've used before, and I'm going to show you. And we're going to kind of go through building the same circuit with all of them, and just so you can kind of see the workflow and kind of get it. All right. So the first thing is let's start off with there's one of these that's online, and it's called Circuit Cloud or Circuits Cloud. All right. And so you have to just go to the website, and then I believe you might be able to use it, and he spelled register wrong, register. And you might be able to use it without signing in or creating an account. But anyway, so I've created an account on here, and just put your name and your email and all that, and that's it. It's this web-based simulation. So we're just going to say sign in, all right, and we'll log in here. All right, and a couple things that I built right here that I was playing with to try and figure this out. So what we're going to do is we're just going to go straight to the circuit editor, all right, and it's going to load this thing up. All right, now typically, so again, we're going to have a couple different kinds of technologies. If we have our full big CAD program, our PCB schematic layout and PCB design, simulation is integrated into it. So as you design the circuits, you can simulate those circuits. Now, these standalone simulators typically are there's no PCB layout part of it. It's just schematic entry, and it's usually simplified schematic entry, because what we're trying to do is just figure out the response of our circuit, analog, digital, or mixed, with our components. All right, so typically it'll be an interface like you see here, and you will draw your circuit like you would in the PCB or schematic entry, big CAD program, and then you'll simulate it. And then simulation can be complex, the kind of simulation, but we'll get to that. All right, so again, I just played with this right now and kind of figured it out a little bit. So we're just going to do this right on the fly. So again, the web-based programs are a little bit more familiar than some of the desktop ones. The desktop ones kind of have their own personalities, but the web-based ones are all using the same technology, HTML5, JavaScript, Java, etc. So they kind of sort of feel the same. All right, so what we're going to do is we're going to draw the circuit where we have our voltage source, our 5 volts, and our 2 resistor voltage divider, and we just want to see the outputs. That's all we're going to do, right? Let's keep it simple. All right, so there's a resistor right there. All right, and already I don't like the way it is, so I just I right-clicked. Let me press escape. So I right-clicked and I can say rotate clockwise. All right, now I'm going to say, can I copy and paste this? Nope, that doesn't work. Let me get another resistor. All right, let me rotate that. And let me put it up there. Okay, so far so good. We'll change the values first. Now let's get our sources. So we look down here, and we've got a DC current source, a voltage dependent source, AC current source, and a DC source. That's what we want, like a battery. So I'll put that right there, and that's kind of already what we want. Good. We're going to put some wires here. We're going to put a load resistor. So let's get another resistor here, and we'll put it over here. And actually this time we do want to leave it in this direction. We'll leave it like that. All right, and let's see what else here. And let's get can we get a ground? Yep, there's a ground, so that's always nice, so we can have some ground reference. Now we got to connect this thing together. All right, so we're looking for a wire, and typically if there's no wire, then you can usually, you see how it's highlighting? Usually just drag. Yeah, so I'm going to go like that, and okay, so I don't like that. I like to be able to control that. And I'm sure you probably can, but we just don't know how to. All right, and let's see what this does. All right, see how it's deciding what it wants to do instead of us telling it what to do. So that's all right. And then right here, it's only letting me highlight to that. So I got to kind of do that. See, that's messy. I don't like that already. Now though, I bet I can maybe grab this and I can, yeah, pull that up. All right, so that's some saving grace, huh? Okay. All right. And hey, you know what? I mean, these programs, these are very difficult to write, these simulators. Again, be glad it's even graphical. All right. Be glad it's even graphical. All right. So now we want to put a ground over here. And again, I can't seem to copy and paste. No, I can't seem to do anything. So we just got to drag another one. All right. Let's put it here. Connect our wire. Okay. We're going to leave that for a second. Let's put our values. V1 was 5 volts, so it's already 5 volts, so that's good. R1 here, and okay, so I can't, let me see if I can, it's probably edit parameters. So if I double click on it over here, this will come up. So let's make that, what, 180 ohms, right? That was 180 ohms. And then this one was 330 ohms, right? Okay. And then this one we're going to make different values, but let's go ahead and let's start it off at the 10K. All right. Okay, so far so good. So that's it. Now, what we want to do is we want to be able to measure the voltage here. So the simulator or the solution finder will have all these different voltages and currents, but we need to label them somehow. All right. And again, your guess is as good as mine. So let's take a look here. So label, title label, these are measurement tools. Okay, so there's probably a better way to do this, but for now, I think the voltmeter will have to do. So put a voltmeter right here. Okay, all right, and this voltmeter has 2 points here. So it's the voltage from one point to another point, not relative to ground, so we can give it a ground. All right, so what we're going to do is the voltage over, and this is our voltage divider, so we're going to look at the voltage over this resistor right here. This is the one we should get that 3.3 volts out of, right? Okay, so we're gonna basically, let's move this over a little bit, all right, and then we're gonna do our little wiry thing here. All right, and just let it do what it does. And then we need to hook the other side to ground. So let's go grab a ground. Okay. All right, there we go. So there's our circuit. And so hopefully you kind of followed along. Now, again here, you could go through all of this, and you should go absolutely through it, look at the help, read it, look at the examples, the tutorials. But like I said, you've seen one. It's like driving a car. You've seen one, you've seen them all. You get in it, you kind of figure it out. But don't do that. Please go through the tutorials, go through the documentation, so you're not doing something the wrong way your whole life. You see, there's a misconception about a lot of things, and people think because you've been doing something a long time, you're good at it. No, it just means you've been doing it a long time. If you've been doing it a long time and you know everything about it, you've read everything about it, you've learned everything about it, then you're probably really good at it. But you can do the wrong thing for 20, 30, 40 years, right? And someone says, hey, why don't you do it this way? Oh, I've been doing that my whole life. Well, you're doing it wrong your whole life, right? So make sure you learn this stuff. It's really, really important. Okay, so right now we're probably doing a lot of things wrong. All right, so I'm going to run this. Now I know that when I run this, it should ask for some kind of, what do you want to do? Do you want to do a DC analysis, an AC analysis, a transient analysis? I don't know. So let's click it and see what happens. All right, so we're going to say create new simulation. That worries me, like it wants to create something new. All right, you have to save your circuit first. Okay, so all right, let's go do that. Let's just say save as, and okay, can I type here? Click to save the circuit. You have to save your circuit first. Okay. All right, and all right, I don't like that. All right, so we're going to call this voltage divider 01. All right, no circuit description. Let's save it. Okay, all right, now we're going to open in the editor. Okay, so I'm not quite sure what happened there, but I guess you can't simulate it unless you open it again. All right, so all right, let me close that window, and we've got it right here. All right, so now let's do run. No, we don't want to do that. Let's go to simulation. And there's no simulation. So we've got the editor here. All right, so last time I was able to do this, create a new simulation. Okay, so now when I do it, after I saved it, now it says you can do this. Okay, so the first thing is someone cannot spell. Transient is spelled wrong here. This is S-I-E-N-T. But anyway, we won't hold them to it. We don't really want a transient response. We want a DC response. So, all right, well, let's just say create and run. Let's see what happens. And breaking connection R3. All right, so it didn't like this right here. Okay, so let's go ahead and let's just connect this. All right, we'll connect it right here because this is where we're going to load it anyway. All right, so we're going to connect it right there with our load. All right, so let's try that again. And let's see, file doesn't do anything for us. Selection simulations, these are different kinds of simulations. All right, and let's go ahead and let's run this again. And all right, so we don't need to create a new simulation. We want to edit parameters maybe. All right, we don't want to do transient response. I can't type in that, so that concerns me. All right, let's do create and edit. All right, so it's showing it right here. And all right, so we don't know what we're doing, but right now it's showing 3.198 volts at this node with this 10K load. And it's just kind of showing the currents flowing through here and all that. So let's go ahead and stop the simulation. Now let's go change this resistor. Now let's make it a much smaller resistance so it loads the circuit. So right now we're roughly getting our 3.3 volts. We're getting 3.2, we're okay. But now if we change this to 1K, we know we're gonna load it a lot more. So we should just be able to run the simulation, all right? And we don't care about all this right here. Let's just close this and then just look here. We're kind of looking at the DC, which this voltmeter is showing us. And now it's at 3 volts, all right? And now let's stop simulation. And one more time, let's go here and edit it, click. All right, let's make it 100. All right, and hit enter. Okay, and you see what I mean? You can see I'm having trouble with this, right? It's not kind of doing what you would think it would do, and this and that, and again, the hard part is the simulator under all this, and this GUI is just dressing to make it easy for you. But again, you got to work with it. It's kind of a pain. All right, so let's go to simulation, run simulation. But anyway, this is working and it's doing just fine. All right, so now if we have a 100 ohm load, you can see our voltage is 1.495, 1.5. It just kills our voltage divider. All right, so that's it. So we did it. We figured out how to use it, and so here's an option for you. There's many of them. Circuits-cloud.com. Circuits-cloud.com. All right, so that's cool. All right, so let's go ahead and it's opened up multiple windows here. Let's see, leave that window, and let's leave this window. I want to leave that, and we'll just leave this one on here. Okay, now let's go and let's take a look at another program. So this one's called Circuit Lab. This is circuitlab.com. This one's pretty cool, circuitlab.com. And but the problem, and you got to create an account. It's free. Just create the account. But this one is a paid program. And if you look through it down here, I think there's pricing and plans, and student, hobbyist, engineer. And you kind of look at these, and here's the guy who made it, and I guess he made it as a challenge of himself in JavaScript to figure it out. Anyway, so $24 a year or student edition, and I'm not sure what this is all about. I think you can get it if you've got an EDU, and then I don't know, read about that. And then it's $79 a year or $16 a month for a Circuit Lab Hacker Lite. And then you read the features. In any event, it's not that expensive. And if you like this, then great, use it. All right, so let's go ahead and let's just give this a try. And again, this one's web-based. All right, and I've already done this actually. So this is a bug. All right, so it's a bug. I've already done this. All right, so first thing is I noticed that the scrub wheel definitely is not very friendly. So here's a circuit right here, and you can see you can have text here, and it's telling you to do stuff, and this is the kind of a demo circuit, all right? So this circuit kind of loads in here. So let's just say simulate. Let's just see what happens, all right? Now, when I said simulate, when I click simulate, up here in the left, you see that there's a number of different drop downs or fly out or whatever you want to call these things. And each one of these is a different kind of simulation. So a DC simulation, a DC sweep, a time domain, frequency domain. So there's all these different ones. So we just want to do a DC. So let's just do this, and we'll run the DC solver. And that's typically what it's called, run the DC solver, DC solution. All right, operating point solve done in 0.03 seconds. Okay, cool. And then now it solved this circuit. So then if we were to look here and let's see, run DC solver, and that doesn't tell us anything. So somehow, yeah, so if we click on this, yeah. So when I hover over things, I don't know if you can see this. Let me zoom in a little bit. And all right, so now let's see here. And again, you got to figure these things out. So I cannot grab this. Now, typically with a lot of these CAD programs, you can left click or right click, all right? And you can drag something. So, or maybe you can hold shift and do it. I want to be careful what I press because who knows what it'll do. I already tried it and I found that this little button right here allows me to drag it. Then I click this little button and it puts this back up. And then I click this little button and it puts the simulate back up. All right, so whatever. All right, so now let's go. We've ran the DC solver. Now we have this little pen. It turns into a little pen or a little probe. Now if I hover over, now watch what happens. I click and it doesn't do anything. All right, let me run the solution again. All right, there we go. Now if I go and I click, all right, and if I click, it's showing V in, V out. It's showing what these different values are in DC. Now, because this is a sine wave here, the DC solution, these voltages are going to all go to zero when this thing is because there is no DC. This is an AC. All right, but the whole point is you kind of hover and then you can kind of click here and then these are these labels. All right, so all right, great, great, great. We know, okay. So we know that, and it's flying around. That's really cool. And again, don't get too upset at how bad these GUIs are. Okay, and I'm not saying this in a negative way. These, these are the last things that everyone works on, and they're just trying to get the circuit simulation to work, which is really, really hard. So a lot of these things are really, really quirky. Okay, so I think, let's see here. Let's go maybe this. All right, so there we go. There's my little circuit selector. All right, great. Okay, and again, we're presented with a bunch of components. So we have ideal sources, passive elements, signal sources, diodes, FETs, and all kinds of stuff. So this is great. This has got a lot of cool stuff in here. Digital electronics, digital gates, and then things that just don't go anywhere. All right, so let's build our circuit again, okay? So here we go. First, let's start off with our voltage source. So we're going to put that right there. All right, and let's zoom in here. And let's get this at about 150% maybe. And I've got to grab this and figure out where it went. Okay. All right, and let's go back to this one. Yep. Okay, and now passive elements. Oh, there's a resistor. So, okay, let's get our two resistors in here. Can I get another one? Can I copy it? Okay, that's nice. Can I copy that? Okay, there we go. There's our load resistor. Okay. Okay, now I want to rotate this. Rotate is R. Okay, cool. So that's working. And I need a ground. So I go over here. And let's put this ground here. And we need the ground here. So I'm going to copy that. Can I do that? Yep, I did that. So that's nice. So this one's, I'm liking this one. This is not bad. Then we've got some node names here. We're going to do that in a minute. But let's wire it up. So we'll grab wire right there. And again, okay, so this one now you can kind of have a little bit of control on, and it lets you do what you want to do a little bit better. So again, it feels like, a Windows or a web application should work. So that's good. All right. And now we're going to, let's move this just down just a little bit. And then now we're going to go here and connect this. And this is a mistake. I don't want this. So, okay, so now, let me escape. All right, let me see, delete that, and let me delete that. Okay, and let me delete this little piece. Can I delete the, oh boy. All right, no, I can't do that. Can I move this over here? All right, I can move this over here, and let me grab this whole thing and move it over. Okay, and let's go back to this. I want this wire gone. Okay, that worked, and now, all right, here we go. Let's see, can I move that? There we go. Okay, there we go. All right, now, this is going to be our load, right? And we're going to put that right here. Okay, but first what I want to do, let's make this a little more symmetrical, and let's hook this up here. Okay, now let's put our values here. So first, double click here. Okay, so V2, good, that's fine. And we're going to call that 5 volts. And then this is R1, great. And then this should be 180. And I'm just clicking on, I'm just doing what you would think you would do, 330. Great. And this one, we're going to start this one off at 10K ohms. All right. And then now I need to add some labels here. So I'm going to get this node name thing here. And I'm going to put that right there. And why don't I drag that down? Yep, it likes that. Okay. And we can call this whatever we want, but let's go ahead and let's call this V2. We'll call this V2. All right. Because that's a voltage going to be over V2 to ground. Right. All right. And that's good. And then this right here, let's just rename this for fun. Let's just call this our load. All right, it's 10K. It's not connected. Now, a good simulator will ignore anything that's not connected. It may warn you that it's unconnected, but as you simulate, you might want to disconnect something and try the simulation. You shouldn't have to connect everything, right? Let's see what the simulator does. I don't want to connect this yet. We're looking for about 3.3 volts out of here. So here's a simulate button. Here's run up here, DC simulation, DC sweep. So run last simulation. Let's just try DC simulation. It solved it, all right? And now we're going to take our little pointer here, and there we go. Okay, so when I hover over V2 and I click it, V2, there it is, 3.235 volts. So it worked. That's good. And I wonder if I can find a current here. And so, yeah, well, that tells me the voltage on this line. All right, so it said 5 volts, so that's good. To find current, I'm sure there's a way to do it. If I right click, I'm not sure. All right, now what do we want to do? Let's add our load here. So let's go back to, I believe, this mode here. Yep, and we'll get our wire. And let's go like this, and like this. All right, now see what the tool did here? It made this little half moon indicating these are not touching, and then when they do touch or they're connected, it puts the little dot there. So that's a nice little feature. So now with this 10K load, we're expecting about maybe 3.1, right, volts, 3.2. Let's run it. Okay, we run it, and we're done. And it has a V2 up there, and I'm not sure. Yeah, so same V2, and there you go, 3.2 volts, 3.198, right? So that worked. Cool. All right, so now what happens? Can I do this? I can actually change this in this mode. So let's go ahead and let's just go right for the money. Let's make it 100. Let's run the simulation. Let's try this button. And that looks like it worked. No, not really. That started off a new simulation, so now I have to say run the DC solver. Okay, great. Run the DC solver, and again, it shows V2 is 1.495 and V unlabeled, which is this wire right here, is 5 volts, which it should be, and we expected the 1.5 volts out of here with this big load. All right, so there you go. So here's Circuit Lab, great little program, and looks like it has a lot of functionality. So you might want to play with it a lot before you commit to paying for it or buying it or whatever. But it definitely did the job, and the graphic editor is not bad. Okay, all right. So let's move on. Let's take a look at this. So now what I want to do is I want to show you kind of the big dog. All right. So this is Linear Technology. And Linear Technology is one of the foremost analog companies in the world. And from Silicon Valley, founded in Silicon Valley. And one of the founders of Linear Technology actually was one of my professors when I was doing my electrical engineering degree at San Jose State University a long, long, long time ago. And he was funny because he'd always come in, and he was a brilliant analog expert, and he'd come in with his golf outfit because that's all he did was play golf, right? His company was doing so good, he would just come teach a class and go play golf. Now, he was an expert at analog design, engineering, all that, and he did marketing. So the guy who actually did the analog design was like a god at analog design. So the guy that knew enough to be a professor of electrical engineering and teach analog, he just did the marketing. So imagine how good the guy who did the analog design at Linear Technology when they founded the company. So anyway, why I bring you here is they make a program called LT Spice, and it's version 4 right now, LT Spice. And you can download this program right here. Download LT Spice, and then this version right here. There's different versions of it, and you can download this program, and it's free. And this is an awesome piece of technology. So this is hardcore, ultra advanced simulation, Spice simulation. It's just the simulator and Spice under it. But through a graphical kind of user interface. So you can download this and install it, and it runs on your computer. And let me show you what that looks like. So I'm going to run it right here. So let's see, this is 10. So this is LT Spice, 17 XVII, right? Roman numerals. So I've already downloaded it. I've installed it. Okay. And here it is here. And we can go and we can say new schematic. All right. Now what I want to bring your attention to is look at this interface. This seriously looks like a Windows 1 program, right? And it probably is. They probably have not really done a lot of updating since the first, Windows 3, kind of level of technology. They've just recompiled it and got it to work because it's the core of the GUI that they just care about working, and then the underlying engine that drives everything is really what they care about. So again, you're going to see this when you get these tools from these big engineering companies. They just do not look like what you would expect. They're not slick at all. And I mean these icons, for example, wow, I don't even know where to begin. All right, this one right here, I haven't used this in a long time, and this is fairly complicated to get going here. And I'm going to try. Let me see. I think, yeah. So I'm going to try and let me see here. And I don't want to spend too much time on this one if I cannot get this to work. And I'm going to try and remember how to get this to work here. But right click and then let's see, select resistor. We do that. We can do that. I'm trying to figure out how to rotate this thing, and I cannot remember how to rotate that. Let's get a ground down here. Let's get a ground. Let's move this here. All right, so the scaling's working at least. So we got that, and we're going to get a source here. Let's see, that's a label. And then I'm trying to remember how we do a source here, and I am not being able to remember how to do a source. And it's been such a long time since I played with this. And I purposely, I want to show you, I purposely want to show you, you know, me fighting with this and just looking at it, right? And so I would go into the help here and, look around and see if we can say, a source, or we could say DC, all right, and then we could say source, DC source, all right, and then a lot of this is going to be for the language itself, all right. We'll do a search and we'll say battery, okay, voltage source, all right, voltage source, here we go, okay, voltage source. So constant, okay, voltage source, syntax. So this is to do the syntax of it, right? And you would read through here, and then again, this is not showing us how to do it with this interface here. So again, it's like I'm up here in this interface. I see a ground, I see wires, so we can do that. So we can wire this thing together. So and now we got another problem here. We do not. So again. And again, so this is not acting like you would expect a Windows program to act. And if we go to Edit here, Spice Directive, Capacitor, Resistor, Component, Draw Wire, Component, Resistor, Delete. Let's see here, Component. Maybe it's under Component. So Component, and let's see if we put Battery. Yeah, yeah, just horrible, 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 horrible. All right, so there's the battery. So you got to look for it under Component. All right. So yeah, we knew that. Okay, and then now what we're trying to do is we're trying to rotate. What's this? Undo, these are undos. Mirror, there's rotate. So let's see, if I click this and I click this and I click this, so I can't select it somehow. All right, so, and now I can't even grab it. So let's see here, delete net, that's not doing anything. Okay, so these two things right here, we've got move and we've got drag. Okay, so if I grab this guy, so I just click it and then it allows me to move it. Okay, all right, so you click it. So this is a very old, so I'm going to tell you right now, if you used the early Windows programs, right, the very first Windows 1 or on a Mac, this paradigm is kind of how you would have to put it into the drag mode, the move mode, and then grab it and move it. And this is why this is not easy. All right, so now let's see here. If we go to this mode here, all right, so that's that. And okay, and now, whoa. All right, okay, let's put that thing back right there. And I want to be able to rotate it. And okay, so there's rotation here, but I can't seem to, get the rotate to rotate. So I'm getting frustrated at this point. All right, in any event, under this horrible graphical user interface is a very, very advanced simulator. So, and then you could use the simulator without the graphical user interface. But I wanted you to see this is very painful if you do not know what you're doing, and you would have to, and look at this. So it only allows straight lines. It can't figure anything out. So you have to kind of go like that, and then you got to go like that. Yeah. So anyway, we'd be able to design the circuit like we did the other ones, and then run it. But this right here is a very, very powerful piece of software, and you can just run the software version of everything and just run code and create code for components and all that. You don't have to use this, but this is 30 years old at least, this type of technology, this GUI tech, all right? So I wanted to show it to you. I purposely did not figure it out, and I used this many, many years ago, but I wanted you to see, kind of what you have to do, all right? So let's just get rid of that. Okay, now, let's see, what else did I want to show you? Okay, so now there's another nice little graphical user interface, this one. It's called 5-Spice .com is the website, fivespice.com, and let me zoom in a little bit here. And this is not bad. This one is pretty intuitive, and you can kind of draw things pretty quick in it. All right, and it's not bad. Now I believe this one has got a free version and a paid version. All right, so you just go here and you download the thing. All right, and then you install it, which I did. And again, I don't use these typically. I use Proteus, which we're going to do at the very end here. All right, but let's run this one again. And I just want to show you these different versions, and so you can kind of see someone that's used these things before, kind of, deal with them and painfully go through them. All right, so okay, so here we go right here. And all right, so zoom in, again, the scrub wheel doesn't do what it should do. This is the most bizarre Windows program I've ever seen because it's very, very old. They made this thing probably in the late 80s or early 90s, and they just kept updating it, recompiling it to get it to work, and then updating the engine, but the GUI just kind of stays like this. All right, so it says up and down. All right, so maybe it's up and down arrow here, I don't know. And let's see, let's go back to project tools. Let's go right here, zoom in, zoom out. All right, so let's see, zoom in. All right, so I don't know what they mean by up and down because I pressed up and down, and that maybe they mean page up and page down. Let's see, page up and page down. Yeah, that's what they mean, page up and page down. Okay, great. Over here to the right are the components. Okay, so now we can start drawing something here. Okay, so here's a resistor and then different kinds of resistors, and it's a little bit small components, but resistor, there's a potentiometer and so forth. We just want a resistor. Okay, so there's our resistor. So we're going to put that one there. We're going to put that one there. We're going to have our load resistor there. Right click, that gets rid of it. Okay, that kind of does what it should do. I see a test point, so we're going to need that in a minute. I see something that looks like a battery, and then there's all kinds of different sources here. Dependent sources, independent sources, current sources, voltage sources, constant voltage source. That's what we want. Okay, so we're doing pretty good. So already you can see the perception of, so, and this is a very important piece of knowledge here. And this is why Apple is the most successful computer company in history. It doesn't matter what's under everything. If it doesn't look good, if it doesn't work good, if it's not easy, no one will use it. And so if you make things hard, it doesn't matter how good they really are under it, you can't use the thing. And again, when it comes to this CAD software and engineering programs, they are really hard to use for no reason. What they need to do is have an artist come and look at it and say, are you kidding me? This is horrible, right? So anyway, keep that in mind when you do your work. Engineers think in a certain way, especially hardware engineers, and they don't think about the beauty or the art or the accessibility of something. So when you start building things, let someone artistic take a look at it and make sure things are reasonable. Okay, so we got to rotate these resistors. All right. Okay, that was easy enough. Right click and then rotate. All right, and I can drag them. All right, I'm getting really happy now. Okay, now we need some wire. So let's see, what's this? So this is wire, and these are lines for drawing. So we want wires. All right, so let's wire this up. And okay, all right, that does kind of what I expect it to do. And then we're going to kind of go about here, and we can kind of go there. Cool. There's our ground. All right, let's now let me escape. Oh, that worked. Control. Oh, I can copy things. All right, I'm getting super happy. All right, now I need to go back to wire mode. Okay, good. We're going to leave this open for now. Okay, now let's change the values of the resistors. Let me drag this over here a little bit. Okay, can I do this? Okay, it doesn't like that, so let's fix that wire. All right, cool. Press escape, good. All right, now let's change the values of everything. So B1, can I double click? I can double click the body of it. All right, so 5.0 volts. All right, the reference, we'll leave it as battery 1, that's fine. Okay. Click the body, 180 ohms, click the body, 330 ohms, good. This, we're going to call this not R3, we've been calling it R load for fun, R load. All right, we're going to leave it open. And okay, there's our circuit, and we're ready to simulate, but we need some labels, right? We need some labels here. And label relative to ground. Okay, so here's a voltage label. So this is kind of fun. So let's do this. There's one, there's another. Okay, so now I got to connect them with some wires, right? So let's do that. Good. Good. And this is test point V1, test point V2. I'm okay with that. I like that. All right. And then we'll connect this in a moment. First, let's run the simulation, and we'll probably have to save it. I don't know. Let's find out. Okay, analyze. So let's do run. All right. And schematic, unconnected schematic pin. All right. So there's probably a way to say I'm okay with that, but let's just connect it and not fight with it. Okay. All right. So we did that. And let's go back to tools here, analyze. There we go. Run. Okay. And there we go. All right, now there's nothing on the screen. So if you look here, there's some tabs. There's notes, there's reports, there's DC bias. Aha. If we go to reports, this is where it shows all the analysis, and you can see it's saying the source, this, that, it explains everything, how many variables, and then it shows all the things it computed, and here they are right here, and then it shows all the values of them in the order of this table. So this voltage, which it just gave an identifier to, then V1, V2, and then this branch, and then it shows all the values. Okay, that's a little bit, we have to decrypt that a little bit, so let's look at the DC bias. So test point 1 is 5 volts as we would expect, and test point 2 is 3.198. And if you remember, all of our simulators are giving us the same answer with that load resistor, 3.198. And then we see a current here, and this current is 10 milliamperes and some change. I going through B1. It's got a negative sign on it, and that's just showing that the current is going out of it. It's leaving it, right? Remember, you have to have a convention. That's the convention the simulator has. All right. Let's go back to our program. Let's go change this resistor and make it 100 ohms. And we know from our other simulations we should get about 1.5 volts over this load now, because we're just going to wreck this voltage divider. Okay, ready? Let's go for it here. And run is F9. Let's go ahead and let's use a shortcut key. Let's throw caution. Do it again. Okay, I don't know. Is it not working? Okay, so I don't know what happened there. So let's go back and let's just say analyze run. So it didn't like the F key. All right, so now we've got green on the DC bias. That means it was able to find a solution. We come back and sure enough, we've got 5 volts for our voltage 1, which we should. That's a battery. But test point 2 or voltage 2 is 1.49, which is what the other ones also had, 1.498 or whatever. And there we go. So anyway, there are a number of different simulators, and I want to finish. And these are either most of these were free or web-based or very cheap. Now I want to finish and show you something that's state-of-the-art. And there are a lot of state-of-the-art simulators, but the one that I use a lot for schematic capture and what I do, and we would use this, but the program is very expensive. The cheapest version, it's I don't know, $200 or $300. $200 or $300 you can get this, but it can go up to thousands of dollars. And this is a pretty big CAD program. And this does schematic capture, PCB layout, and it does a simulation. All right. Okay. And so it's actually asking for a project. I'm going to cancel that. I'm going to just, so this is Proteus. Now, you know what? Before we even start this, let's take a look where we get this. If you go to labcenter.com, and then we can back out of this. And let me show you this. labcenter.com. All right, and then you can read all about it. And then what the thing is about this, it does full simulation of processors, and it does SPICE and processor simulation. It's just amazing. And then you can go to this order pricing thing and kind of figure out what it is you want here in commercial price lists and educational price lists and all that. And it's a little bit difficult to figure out the pricing, but you can get going for about $250 up to $6,000, right? So the $250 version will definitely get the job done, but if you want all these advanced features, you're going to pay thousands of dollars. So that's why we're using Circuit Maker for the course, because it is free. All right, but Circuit Maker does not have these features, these simulation features, which are crazy, and I'm going to show them to you, and you're just going to be like, wow, that is cool. So if you go directly to labcenter.com downloads, and then you can download the program and you can use this version, but you can't print the schematics, you can't save your work, and you can't simulate your own microcontroller designs, but you can do simulations of not your own microcontroller designs. So you can download the software right there. So it's labcenter.com downloads. You can download it and play with it and see if you like it. Okay, let's go back. Let's just load this recent project here. And so just to save a little bit of time, it's the exact same kind of paradigm. You grab components, you put the components down, and you do whatever you want to do. So now what I'm going to do is let's just go in here and let's just change these values though, and for our system that we're doing. So 180 ohms, 330 ohms, all right, and let's make our battery 5 volts. All right, and now what I'd like to show you, and this has a current, so we've got a current meter in line here, and then we've got these test points here showing us what the voltages are at each one of these points. All right, so let's go ahead and run this, and then down here is where the run is. All right, so we'll run this. All right, and the simulation is running, and sure enough, we've got 4.9 volts here, all right, which is 5. And right here we've got 3.23, which is exactly what we expect. And we've got about 9.8 milliamperes running through the circuit. So we go ahead and hit stop. Let's add our load resistor, all right? So over here is some of the components I've loaded in to the little library. So there we go. Grab that, and then we'll rotate clockwise, all right? And then we can put this, you know, wherever, but why don't we put it right here, all right? And then we're just gonna connect a wire. Actually, you know what? Let's just put it. We'll put it right here, like we've been doing the other ones, and we'll connect a wire. And see how it goes around the object for me. All right. So there we go. And then we'll drag this down a little bit. Okay. There we go. And then let's get a ground. And then here to copy it, you do this little icon up there, and that copies it. And again, I don't like that, but you know, you deal with it and you learn it. Okay, so we've got our circuit here, and again, we could double click that. We could change it to our load. All right, we got our 10K, so we know we're going to get very little loading. Let's go ahead, let's run it. And there we go, we've got 3.23 volts now, right? 3.23 volt, but we made a mistake, We connected this right here. This is not where it needs to go. It needs to go right here, right? Easy as that. Boom, run it. 3.19, so now we've got that little load on there, so we're hanging about 3.2 volts. Let's go ahead and stop the simulation. And let's go to our 100. Let's just jump to the end here. 100, run it. We should get about 1.5 volts. And we do, 1.49. There you go. So all the simulators show the exact same values, and they all have their own idiosyncrasies. And depending on your budget and what you want to do, you can get to a different piece of software. Why I like this is I do my PCB layout, I do my schematic capture, and I do my simulation all in one thing. Now, what I want to show you right now is the advanced simulation. So I just want to load something, and let's see here. So let's open a sample project. I don't want to save this. All right, so now over here we have all these different things. We can simulate an entire Arduino. All right, so let's type in game maybe. Let's type in game. Let's type in video maybe. And there was a fun thing here. Space Invaders. So this is take a look at this. So what am I looking at here? So there's a PIC18F 452 processor. There's an entire model of it inside of this simulator. Then there's this LCD, which is this manufacturer right here. It's a 128 by 64. So source code has been written and compiled, and the binary has been loaded into, via the interface here, into this virtual chip. The connections have been made properly so that you can drive this LCD. Someone looked up the LCD driver specifications and wrote a driver and wrote all that software and got it all to work. And then basically said, hey, I want to build a simulation of, say, a product that I'm going to build. And here it is. So now watch this. So now I can go ahead and I run the simulation. And Space Invaders. So press fire to start. So let's see, 1 is left, 2 is right, 0 is fire. So 1, 2, and 0 is fire. Or I guess I could probably click it on that. All right, press fire to start, and there we go. And I'm playing, and there it is. Boom, boom, boom. How crazy is that? A full simulation. All right, and that's why I say, you know, this is a very powerful program, and there are other CAD programs that do this kind of simulation as well. But Proteus definitely does it. So Proteus, we are not going to use Proteus in the course and learn it because it's just too much to learn. We're going to learn just one circuit maker. when we get to that point, when we finish up with more of the electronics theory and hands-on. But this is definitely something that you on your own should go and explore, is a Proteus, Lab Center Proteus, because the simulation alone is amazing. And then as a CAD tool, it's a great CAD tool if you can afford it, if that's in your price range. But if you need free, then you just have to wait for a rainy day to do it. All right, so that's it. So I hope you like the lecture on simulation and SPICE. So when you're doing your designs, it's a great way to verify what you think you're doing, and also just to experiment in a quick way, so that you don't have to go to the bench. And then once you kind of figure out roughly what you want to do, then take it to the bench and actually build it, because in the real world, things are always going to be slightly different. There's a lot of other variables that SPICE doesn't take into consideration that the real world does, just because it's the real world, all right? So remember, you can SPICE simulate, but always build the thing, and then just make sure that it does what you think it's going to do. All right, so that's it. So I will see you in the next lecture. Bye until then. All right, welcome to the next lecture, and actually we're in the next section now. So we're making up, a lot of ground, and we're now starting to get into kind of wrapping up a lot of the analog stuff that we've been talking about. So in this section, which is going to be composed of a lot of lectures, we are going to go through the material that you see on the screen right here loosely, and probably add a bunch of different stuff. But like we've been doing, we've been roughly following my book, just as an outline, so that we have something kind of to look at for notes, and then something for me to follow, because this is kind of our general plan for the analog material. But after we get past, maybe I think we're going to go another chapter, maybe 2 chapters, then we're going to kind of go off on our own and do material just that we want to do about this subject. So, but first we got to kind of do the fundamentals. So we're just going to keep doing this. Anyway, so in this section, we're going to talk about mechanical components a little bit more. We've been talking about this, and again, we're going to repeat ourselves, all through the course. So we'll talk about things more than once, which is, how we learn them. We're going to talk about capacitors again. We're going to talk about inductors. We're going to look at charging and discharging of capacitors, inductors, a little bit more of how they work, from a physics model point of view, and to kind of hopefully give you a little bit more insight into them. We're going to talk about filter design, which is going to be fun. We're going to do low pass, high pass filters. We're going to build a lot of different little things. Let's see. Another thing that we're going to do, which is not on here, we're going to play around with some AC circuits. So we are going to plug into the wall voltage, the 120, and hopefully I don't blow anything up or start on fire, but that's going to be fun. And we're going to kind of come up with a model. We'll test it and build it, and then we'll plug it into the 120 carefully, and I'll show you how to safely do these kinds of exercises and circuit design. We're going to do some more simulation. So again, we're not using Circuit Maker yet to design any circuits. We just don't know enough to do anything interesting yet. We're going to get there. But we're going to use another tool for simulation, Proteus, and we're going to use that to simulate some of the stuff that we're going to work on. We're also going to play with MATLAB, which you probably have heard of it. If not, it's a matrix laboratory. It's one of the biggest mathematics packages in existence, and it is super awesome. You can basically figure out anything you want with it. So we're going to play with that a little bit, which will be a lot of fun. And let's see here, what else? We're going to go back to diodes again, talk about those just a little bit more in the context of building power supplies. We'll talk about half wave and full wave rectification. And let's see, we're going to design some power supplies. We're going to do, we'll do a 3.3 volt power supply, a 5 volt power supply, and we won't build it, but we'll talk about buck boost power supplies, buck and boost supplies that are, require inductors so that you can increase voltages or decrease voltages used in battery systems, or when you have a higher voltage, you need a lower voltage, or you have a lower voltage, you need a higher voltage. So we'll talk a little about those. And let's see here. We've already talked about transistors, so it's not really going to be an introduction to transistors. We're going to talk about them again, but we are going to kind of jump into using them as building blocks for digital logic. So we'll build a couple circuits to show how to do some logic stuff, so that'll be fun. And let's see. And then we're going to talk about just some random topics about generating clocks and some things like that that you need kind of in digital circuits, and just some other things that we'll just make up as we go. All right. So anyway, so let's go ahead and finish up this. We'll just do this like a little intro lecture, and then why don't you meet me in the next lecture, and then we'll start into some more mechanical components. Okay? So I'll see you then. Bye. All right, welcome back and welcome to the next lecture. So what are we doing? We're going to talk about some mechanical components, and we've seen lots of things as we've been working. So we've seen some momentary switches and some different things. Now we're just going to take a look at some photos, and then I've got some parts over here on the bench that we're going to take a look at. So just so we can see them, their scale and whatnot, and then we'll play around with them a little bit on the bench so you can kind of check them out. So anyway, so let's follow along here inside of the notes. So, okay, so the first thing is, boy, how to describe the unlimited supply of mechanical components for electronics. There are, and I'm not even going to exaggerate right now, there are probably millions of different kinds of switches, millions of switches. There are at least hundreds, if not thousands, of manufacturers around the world that manufacture types of switches. Switches for small electronic devices, big electronic devices, switches that can switch, 1,000 amps, or switches that can switch, milliamps, right? There's just every kind of variation. And it's interesting, do we need them all? Probably not. But, like anything, there's both an industrial design aspect, cosmetic aspect, and then a functional aspect. So there's just a lot of switches. And so there's some mechanical components that make up a switch and some terminology. We'll talk about that in a second. But one thing that you definitely want to do now in electronics is all kinds of components. There's inductors, capacitors, diodes, all kinds of diodes, transistors, FETs, and then chips, countless chips and integrated circuits. But in the mechanical stuff, there's just as many cool things. But if you don't see them, you never really get a good feel of it. Now, what is kind of disappointing is it's the early 21st century, and this is not the 80s and the 90s or the 70s anymore. And up until about the 90s, there were stores that you could walk into, electronic stores that you could walk up and down the aisles and find really cool parts. And they still exist. I mean, if you live in Silicon Valley, there are a few stores there in Silicon Valley. And I'll even mention there's Halted Specialties, Halted, Halted Specialties. There's Weird Stuff Warehouse, but there used to be many, many more. And where I am here in Austin, there's none now. There's none. There was one, I believe, called Howard's. Now, depending on what city or what state or what country you live in, you may have a place, but it's really hard to find. So the problem is you can't just walk into a place and look at things anymore. And this is what we used to do. We just go up and down the aisles looking at things. You can look online in a catalog. Sure, you can look at all the countless switches in DigiKey or Mouser or Element 14 or Newark or whatever distributor you like, but you just don't get the feel of things. And what happens is you have to order them to try them out. And a lot of times their specifications will say, this much voltage, this much current. They may talk about how much force it requires to push the switch or move it or whatever, but you really do need to see it, touch it, feel it, look at its manufacturing, look at its quality. And that's just switches, right? And so just in general, you can do worse things than try and find an electronics store near where you live, go there and just go up and down all the aisles. And if they have components, just look at stuff. Just pick it up, look at it, and get a feel for it and connect with it. They're like building blocks. They're like paints and brushes and easels and that a painter uses. So anyway, But these days, these things are very hard to find in stores. You know, stores are very hard to find, right? Soon it's just going to be the Amazon store. That'll be it. Okay, so the picture that you see here is a picture of just some random switches and kind of a low resolution. This is a company called Switchcraft, switchcraft.com, and there's many companies that make. This is just one that I use, but it shows just different switches, and you can see some things here. Some things that you know look very large, and some things that are smaller and whatnot. All right, and what I want to talk about when it comes to switches is there's some words here, some vocabulary that we kind of want to learn when we're talking about switches, just so we have an idea. All right, so let's take a look here. So poles is the number of switch contact sets that conduct current. So the number of switch contact sets that conduct current. So for example, then you know we're going to come down here in a second here, and I'm going to show you some drawings. But what this means is in a switch, typically you've got, you know, let's make sure we can see this. You know, say here's one contact and here's another contact, right? And we want basically to connect this contact to this contact, all right? And through a switch. That's one pole. That's just one conductive path. That's one pole. And so we could have one here, and then we could have another one, we could have another one. So each one of these conductive paths, that's called a pole, all right? So that's what that is. That's a pole. All right, throw and weigh. The number of conducting positions for a single or double throw is used. For 3 or more, weigh is used. Okay, so what this is talking about is when you have a switch, and as a matter of fact, let's you know, let's take a look. Let me. I'm going to grab a couple switches, and I'm going to go to the Zoom camera, and let's take a look as we're talking about these things a little bit, so that we can kind of make a better connection with it. All right. Okay, so taking a look here now, we're going to look at a lot of switches in a second here, but this for example is a good example of kind of a big switch here. So in this case, this is a two pole, and the reason why it's two pole is on one side of the switch there's all these contacts, and on the other side there's all these contacts. So this is one current path here. All right, so current's going to flow from maybe here to here, here to here, here to here, and then you can have a separate current flowing from here to here, here to here, here to here. All right, so pole is a bad word because typically we think of pole as one thing, but it means a set. So these are one set of conductors, and these are one set of conductors. All right, now, so inside of this switch now, it's basically got kind of two switches. There's one armature that slides over these contacts in some way. And it can be pretty funky, like you could move it and then these two could be connected and these two are not, then you move it again and then these are connected and so forth. So if you open these things up, a lot of times they can have weird mechanical construction. All right, but it's two pole, all right, so we got two separate circuits. Okay, now it can go, in this particular switch has more than one position that it can be placed in. So there's all the way to the right, then here in the middle, and then all the way to the left. Okay, so this is the throw or position. Okay, so that right there, that's what that is talking about when we're talking about that word. Now we see throw away, the number of conducting positions, you know, for single or double throw is used, for 3 or more weigh is used. So all this really means is that if the switch has got a lot of different positions, 3 or more, typically they use the word weigh, and then if it's just got a couple, they use just single or double, meaning it moves in a couple different positions. So again, when you see these words, you know, they all can be confusing. It's like 2 pole, 3 weigh, 2, you know, 5 throw, etc. Just that's what these mean. All right, momentary switch, we've seen these before, all the momentary switches, it turns on, it turns off. Now sometimes it can be normally open or normally closed, right? And open, the switch is in the off position, contacts not conducting. Close, the switch is in the on position, contacts are conducting, all right? And so these are just some words: poles, throw away, momentary, open and closed, all right? And just to kind of help you when you see these things, right? And a lot of times these switches are having codings because the companies make thousands of variations, and then they'll say how many poles, how many throw, how many weigh, and you're just like, what is this? You got to go to Wikipedia to decode it. All right, so let's keep looking here. So there's a momentary switch. We've seen these, and this is kind of a schematic. So this would, close it. So this would be normally open. So it's normally open. It's not conducting. You press down, it closes it. All right. So that's kind of the representation of that. And then this would be normally closed. So it's normally closed. Springs holding it closed, and then you press it open, and then the switch opens up. And a lot of times, if you see these red switches right here, they're kind of got plungers and some little nuts on here. You kind of screw them down, and you solder wires to them and that kind of thing. These are typically normally open. They're called single pole, single throw. So single pole because there's only one conducting set. Single throw because you just can move it in one position, right? That makes sense. Now you can find red ones that are normally closed, but typically the normally closed are black, right? And of course you can find exceptions, so never take anything with 100% fact. Everything's got exceptions. But the black ones are typically normally closed, single pole, single throw. All right, so you'll use these a lot if you're going to build something with a front panel. Typically you'll use these guys because they're pretty robust, and you can press them, many tens of thousands of times probably before they would fail. All right, okay, and just a little circuit. You got a circuit, right? We know battery symbol, switch 1. This is normally open. Close it. It creates a conducting path, and then the current flows through the resistor, lights the LED. All right. Now, a couple things that you want to concern yourself with when you're dealing with switches is what is the maximum current that can flow through the switch? The switch is made out of metal, so a lot of times they'll have current ratings, okay? And they'll be either AC or DC switches. So either they're designed for a DC direct current, or they can handle an AC current. Now this is very important. The switch itself is, an electromechanical assembly, and sometimes the switches themselves have inductance, they have capacitance. Well, they always have inductance and capacitance and resistance. You put an AC signal through there, and things are going to happen, right? Inductors, capacitors are going to do what inductors and capacitors do. And if you're running an AC signal through there, this could damage the switch if it's not designed for AC. Likewise, the switch is made out of metal, but metal does not have zero resistance. It has very low resistance. But again, it has some resistance, and if you run too much current through it, you heat the switch up, which could cause the metal to fatigue or the plastic to melt or whatever. So you have to look at the current ratings and make sure you're okay when you design something. All right, just another little picture here. And so this is a double pole single throw. And again, remember the pole means how many conducting paths. So there's circuit 1, and then here's circuit 2. And then it only goes in one position, so that's that single throw. That's the ST, so DPST. Another thing, so typically they'll put the number of poles first, so it'll be double pole or triple pole or single pole, and then it'll be how many throws. So it'll be poles, then throws. But that doesn't mean someone's not going to make it, throws, then poles, right? So it could be STDP. Although I don't think I've ever seen one, doesn't mean someone's not done that. All right. All right, and then these are called slide switches, and we just saw that one on the zoomed in camera. Slide switches, different size here, and a couple things. So a couple things to notice is these are top mount. So these go into a printed circuit board, but the switch actuator is a vertical, right? So it's up and down vertical. Now, these guys are right angle, so they go into the circuit board right angle, and then the actuator is on the side, right? So this is a right angle. And then this would be considered a micro switch, this teeny tiny one, and so would this one. All right. Now, say like you've got a lot of current, and say you're using this micro switch, and say this one's got 2 different poles, 2 different conducting paths, like this little picture. And say each one only takes, say, 200 milliamps. That's its max. You can parallel them together. You can parallel them together and not have 2 circuits, just have 1 circuit and double the current to 400 milliamperes, right? So that's a completely valid thing to do, and you do it all the time. In fact, that's why they make these switches like this, Because typically you're thinking, well, why do I want to switch 2 different circuits or 3 different circuits or 4 different circuits? Yeah, you probably don't. There are cases when you do, but many cases they just give you the flexibility, so they break the switch up into 2 or 3 poles. You can solder them all together and just put them in parallel if you want, and then get a current gain, you can put more current through the switch, or maybe you do have 2 or 3 circuits that you want to use. All right. Okay. Um, just some schematic symbols here. And again, so here's a situation where this has got it's a double throw switch, right? So we can be in 2 different positions, right? And in the way that it's drawn right here, this would be single pole, right? There's only one kind of set of conductors here, but we can move the switch in 2 different positions. So this would be single pole, double throw, right? And if you don't get it, don't worry about it. A lot of times you'll see switches drawn like this. We have kind of this representation of an armature, and typically this would be a slide. It could be something that rotates so. You don't know, it's just a representation. But you'll have kind of the common, and then you'll have 1 and 2. Sometimes you'll see switches drawn like this. And again, this is just different schematics will do different things. Right, there's just a double pole, double throw, right? We got 2 different poles here. There's one, there's the other, 2 different circuits, and then in this case right here, it can be in 2 different positions, all right? Okay, now dip switches. So so here's kind of representation of a dip switch, but that doesn't really do it justice. So a dip switch, and let's see if there's some pictures of it here. And so these are really cool. So what does a dip switch stand for? It stands for dual inline package. And the word dip also applies to integrated circuits or just anything that's got a dual inline package. And all that means is dual to inline, meaning something is in line, and package is in a package. So in this case, there's 2 rows of conductors that make up the switch, and then each one of these is a little switch inside of here. So it's basically just a bunch of little single switches all put in one package. And you can see they can be very small, and here's just a 1 switch version, a one dip, and there's a 4 dip, another 4, and and some of them you slide, some of them you rock, some of them you click, some of them, all kinds of different variations. Now, why would you want this? Well, if you're a software person, immediately I'm sure you've got an idea. Say you design some piece of hardware and you want to set up some kind of flag or something, or some kind of control or user setting through hardware. You just put one of these little switches, and then each one of those little switches could be a 1 and a 0 that represents some kind of setting. All right, so let's take a quick look at a couple of these on the zoomed in camera. Okay, so before we do that, and so there's one of our just momentary switches, right? One of those big mechanical ones. Now we've been using, if you recall, in lots of our circuits, we've been using these little guys right here. These are pretty cool. And you can see the size differential, right? And so this one will plug into our solderless breadboard, where obviously this is not going to, because it's designed to be soldered and put through a panel, a front panel, all right? So anyway, and then here's one of those micro switches, right? And just to give you, look at that size differential, right? So that's, big difference, big difference. This thing right here, you could probably run a lot of current through, and this right here is just 100 milliamps or 200 milliamps, I think. All right. Now, so let's take a look at these 2 things, these 2 guys, and these are the dip switches, right? Obviously. Okay. And now let's kind of get this to lock in here. I want you to see this up close. So that's what it looks like, and this is C&K Industries is the manufacturer. Now, turning these things on, obviously this is not easy. You can do it with your thumb or your fingernails if you have any, right? But typically what you do is you'll use a tip of a pen, and so you'll just get a pen and you can just kind of click it like that, and see if you can hear the click. I don't know if you can, maybe. All right, and so on means it's closed, and then that's it. So this might be the flag for something, and then again, this will go right in your solderless breadboard, or this will go into a PCB, and these are 0.1 inch spaced, and this is a dual inline package, and this is a 8-bit or 8 switch dip, and that's it. And they have them in every color, every style, anything you want, someone's made, I guarantee it. Okay, now here's another one. And this one's a lower profile, so take a look here. And you can see the profile, right? So that's if you want to make something small. And I use these all the time. When I design circuit boards for products, and maybe we want to have a couple little settings that do something, that's what you'll use one of these little dip switches there. And you know, maybe you only need 3 different settings or something or whatever, or maybe you need, you know, 8 different possibilities, right? There's 3 bits, right? 2 to the third is 8. And again, you know, just kind of go in here and click, 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 click. And then that's that. And again, this will go on your solderless breadboard or your printed circuit board. So those are you know, some examples of some dip switches right there. All right. Okay, so moving on here, and this is just a common circuit, a little example here, and let's see here. Let's draw this and kind of show what's going on here. All right, so for example, one of the uses of a dip switch is you want to have something that sets some bits or something, right? Okay, so let's pretend that we know about microcontrollers, and we want 4 different bits, and they're going to control 4 flags that do something. Don't know what they do, but we need to build that into the hardware. Okay, so we go out and we get a 4-bit dip switch. 1, 2, 3, and 4. And my little switches are getting progressively thinner, unfortunately. Okay, cool. And let's draw the little switches in white here. Okay, and all of them are in this down position, let's say, just for fun. Kind of draw this instead of drawing it abstractly. Okay. All right. And let's say that when they're up, they're on. When they're down, they're off. So up is on and down is off. Okay. So we'll kind of put an arrow like that, and this represents on and this represents off. Okay. Now we want to send 4 signals to a microcontroller, right? And we're going to learn about this a little bit more later, but we want to send a 1 or a 0. Let's say we have a 5-volt system. So we want to send a 1 or a 0. So we want to send 5 volts or 0 volts to something that would read it on some input pins. Okay. So one way to do that is like this. So let's take each one of these. Now, when these things turn on, it's going to connect whatever. So first, let's go down here. All right. And so whatever's down here, and then here's the switches coming out. So whatever's down here, when I turn the switch on, it's going to connect it. So basically the switch is going to connect this to this, right? This to this, this to this, and this to this when I close the switch and move it up. All right, so we all understand that. Okay, so let's do this. Let's take all of these, we'll tie them all together, and we'll tie them all to ground, okay, which is a 0 and which is 0 volts. All right, a 0 digitally is our representation. Okay, now we've got these signal lines coming out. All right, and so now what we can do is we can take these, and these can go to our microcontroller or a microprocessor, or whatever we want that we need these signals for. All right, so let's just draw these little signals, kind of look like little flags is one way to do it. All right. And again, once we start designing some circuits with a circuit maker, we'll see where these kind of symbols kind of come from. And I'm kind of running out of room here, I think. Kind of messed myself up by making this so high, but that'll be okay. All right, and so now let's also label some numbers here. So let's call this switch 0. So this is kind of like S0. We'll call this one switch 1. We'll call this one switch 2. We'll call this one switch 3. Right? Or if you're like me and you like to count and think in binary, right? Let's think in binary. This would be like S0, this would be like S1, this would be like S2, and this would be like S3, right? Because the first bit is 0 down here, right? We go from right to left. Okay, now let's take a look here. And so over here, this is the S0 signal, this is the S1 signal, this is the S2 signal, and this is the S3 signal. Now, what do we want to do? So if I turn one of these on, it's going to connect to ground here. So let's say we connect S1 and we turn it on. We move this up. All right, we do that and we get a connection. Ground is here. S1 will be grounded. Great, perfect. But when I put it back down, S1 is just floating, literally floating. There is nothing connected to this. So what we need to do is we need to pull this up. All right, so what we're going to do is add what's called a pull-up resistor. All right, and what I'm going to do to make this a little bit easier to see is I'm going to use a different color. I'm going to use yellow. All right, so I'm going to just make a dot here, and I'm going to put a little resistor like this, and then I'm going to put a little dot here and put a little resistor here like this. Again, do it here, go all the way up, little resistor like that. Again here, all the way up. And the point is, I want to make sure you realize these wires only touch or connect at these nodes where these dots are. All right, then I'm going to connect every single one of these up here, and I'm going to connect these to our power, which we typically call V sub CC, which in this case we're going to use plus 5 volts. All right, and each one of these resistors, we could set them for whatever, but we're going to set them all for 10K ohms. Okay, 10K, 10K, and 10K. Now, when each one of these switches is off, we're going to get this 10K pull-up resistor, all right? Pull-up resistor. We're going to get this 10K pull-up resistor pulling up on the signal, and as far as S0, S1, S2, S3, it's going to see basically 5 volts through a 10K, and it'll see a digital 1, all right? So now we've got kind of this design where when you have all the switches off, what you're going to see is 1, 1, 1, 1, or you're going to see plus 5, plus 5, plus 5, plus 5. All right, and that's what you're going to see on all these outputs. Now, the value of the pull-up resistor is going to determine what the amount of current is or how hard these signals are pulled up. All right, so now let's zoom into one of these and kind of simplify the circuit. So let's zoom into one. So just one of these, if we were to draw it, looks like this. So we have V sub CC here, which is our plus 5 volts. Then we've got a resistor like this. All right, and then we're going to take this right here, and I'm going to call this, we're just going to call this, we'll just call this output for now, right? And that is like one of these things up here, right? That's the output, okay? So output S, we'll just generalize it to output S. And then here's our resistor, which we're saying is like 10K. Okay, that's this part of the circuit. Now we've got a switch in here. So what's the switch do? So the switch kind of looks like this, all right? Kind of looks like this, and then it goes to ground. All right, and let's put a little armature here because it's not a momentary switch, right? It's going to stay when you close it. It's going to stay. So we're going to use something that looks like this. All right. Okay, let's do some calculations here. All right. So when the switch is open, what's going to happen at output S here? We are going to. This is not in the circuit right here. This is not here. It's gone. Right? Not there. All right, because it's an open switch. So now when we don't have the switch on, we're going to basically have a 10K connected to 5 volts, and then that's going to be that. So now say that this is connected to some digital input, right? Some digital input pad, right? GPIO, right? Which again, general purpose IO, we don't really know what this is, and we're not really going to study microcontrollers or anything in this class, but we can talk about them. So this would be a GPIO pin, maybe like on on Arduino or a PIC processor or an ARM processor or whatever. And now, if we have it in read mode, we would be able to read what this signal is. And so because these inputs take very, very little current, so let's say that, and most of them take no current at all because they're CMOS circuits, but let's say that it requires 1 microampere of current it needs to flow through here. All right, so it's going to basically sink or pull 1 microamp of current, because we don't know what the impedance is on this side, but we know that it's going to need 1 microamp to kind of pull down here. So 1 microamp, and then we've got this 10K resistor here. So let's figure out what's going on here. So we've got 5 volts over here on the left. The question is, what do we have on this node if we pull 1 microamp? Okay, well, let's get back to Ohm's law here. So V equals I times R. All right, so we want to compute what V is. So we know what I is, which is 1 microamp. All right, 1 microamp times R, which is 10K ohms. All right, and get out your handy calculator. You always need to have your calculator with you. All right, 1x minus 6 times 10x3, and that's 0.01. So I'm just going to leave it like that. So this is 0.01 volts. In other words, at this node, well, if we had 5 volts here, right, and we dropped 0.01, then that means we have 4.99 volts here. In other words, we've got a 1 here, right, and we've got a 1 all day long. If this thing were to drop to maybe 2.5 volts, then it would start thinking it's a 0. Well, actually 1 volt, it would probably think it's a 0, but 4.99, that's good. Now, what happens when we close this? So now when we close this, and I'm going to draw it in red, when we close this switch, now what's going to happen is, well, this input here, right, is directly connected to this ground. So that's that. So no matter how you slice it, you are now connected to ground. All right. So there's a 0 volt there, end of story. That's it. And that's going to end up being a digital 0. Okay. But did we do anything bad? Right? Is anything bad going to happen? Well, let's take a look. So we've got a 5 volt supply. We've got a 10K resistor down to ground. Aha. This is where things get a little interesting. So now we've actually got a circuit and we've got a current flow. So what's going to happen? We're going to get a current that's going to go like this to ground, right? And I'm going to call that I, and we'll call that I closed. So in that case, we've got this current I closed. So that means when you close the switch, you're going to start burning current. You're going to get a 0 on your input. Good, but we're burning current. And the question is, can we tolerate burning that current? Well, let's find out. Let's use Ohm's law. So V equals I times R. What do we want to know? We want to know what I is. So I is V divided by R, right? So V divided by R equals this I that we're trying to find, I closed, right? Okay, V in this case is 5 volts. R in this case is 10 k ohm equals, get our calculator out, 5 divided by 10, x3 equals 500 microamperes. 500 microamperes, or 0.5, that is a horrible 5, milliamperes, depending what you want to keep your units in. All right, so 0.5 milliamperes, that doesn't sound like much, but if you're doing a battery operated system, right, and you have 8 or 16 dip switches to control something, right, well, 8 or 16, that's 16 of them would end up, 16 times 0.5 is 8. That would be 8 milliamps. Call it 10 milliamps. 10 milliamps you're burning on your battery just for your toggle switches, right? So 10 milliamps, right? And so that's bad. So then what you need to do is you need to start increasing the size of this pull-up resistor. Make it 22K, make it 100K. You can't do too much though, because if you keep making it bigger and bigger, you'll burn less current when it's closed, but then what's going to happen is you're not going to be able to maintain, see this 1 microampere is required to drive this input pin to a 1. You need to see what this current is here, right? And maybe it's a fraction of that, but you still need to have enough current to drive that input pin. And it may need milliamps to drive the input pin if it's a TTL kind of circuit. If it's a CMOS circuit, it'll almost need nothing, all right? And typically it will need nothing because it's a voltage which is all it needs. So anyway, so these are what pull-ups are for. And so you use pull-ups to pull signals up, and you pull them up so that you can have them in a stable position, a stable state, and then you might use one of these little switches. So that's kind of an application of the dip switch, and we could build that, but it's too simple. Let's not even mess with it. All right, so let's go back to the material. All right, and what we just did is basically this. All right, so this was a 4-bit configuration of flags or something. And then here was the equivalent circuit, the eye open, the eye closed, right? And this is what was kind of going on here, right? And just kind of some analysis. You can read through that if you want. Okay, here's another interesting switch. This is called a rotary switch, and this is super old school. And, you know, I don't know that there's a lot of things that'll have rotary switches on it these days. Some appliances, lots of appliances, you'll have knobs that you can turn. Obviously, your washer and dryer, if it's not completely digital, has rotary switches on it. They're actually pretty complicated inside, but the idea is the same. So the idea is you just want to have something that you rotate around to a fixed number of different positions, maybe 4, 8, 10, 16, 20. There can be many, many positions on a rotary switch. And these, again, are pretty robust and pretty bulky and designed for high current, high voltage applications, not digital electronics, right? So you're going to see these in appliances, typically in machines, all right? Old TV sets, things like that. And then, you know, here's kind of an application that you might think to make. I'm sure you've seen in the store video switchers, kind of old-fashioned video switchers, where basically you have maybe 2 or 4 cables, AV cables, and then you have one input, and then you want to take that one input and route it to one of those 4. Right? You could use something like a rotary switch. Now, you'd have to be a little bit careful because there's more than one signal in a video signal, but the idea is sound. So you might have a video signal here, and then you might have a 1, 2, 3, 4, 5 position rotary switch, and then you could send video to each one of these. If they all had kind of a common ground, you could use the common ground and just send the video. The problem with doing this kind of stuff is these switches tend to be a little bit noisy. When you switch them, the mechanical, you know, they have to rotate, they have to stop, they have to settle, and that kind of messes up signals. But once they're stable, you know, it's pretty good. So if it's low and if it's low voltage and low current, right, you're not going to damage the switch. Now, if you have a switch that has a lot of current going through it, or high voltage, what happens is as you move the switch, whether it's a rotary switch or a slide switch, that switch there's a bunch of current going through it, right? And then as you move that switch or change positions, what's going to happen is you're going to get arcs, right? So the moment that switch stops making contact, if you were to zoom in at the atomic level and start looking at nanometers, right, you would see like a little arc occur because the air itself, right, becomes a conductor, and there's current going through there, and you know, right at the last nano picosecond, a little arc occurs as it releases the switch. Same thing when the switches make contact. There's an arcing, and that's why switches over time, you see they get all charred and carbonized, and they don't conduct anymore, and you got to clean them. That's exactly what's happening. So if you're running high current, high voltages through switches, over time they will fail. All right, and then this is just talking about different kind of switches, right? So switches don't necessarily have to be mechanical. They can use the Hall effect, right, which is you know, based on using magnetic fields. So a magnetic field can move an armature, right? That's one thing. Another thing that you can use is if you know, put electrons into current into a magnetic field, right? The electrons will be pulled to one side, so you can generate a voltage. That's kind of the Hall effect. So you can actually generate a voltage in a wire transversely, and then measure things that way. So that's another thing. Mercury switches, you've probably seen these. I don't have one with me. As a matter of fact, I do have a mercury switch. Let me show you a mercury switch. Okay, so here is a mercury switch. So how crazy is this? And I actually have one. So there's actually mercury in here. So this is mercury, which is a metal that is kind of liquid at room temperature, and it's conductive. And there's a lot of switches that are made out of this, and what they're used for, and a lot of machines still have these. So again, appliances, washer, dryer machines, things of that nature. And what they're used a lot of times for is for motion detection. So this is a really before accelerometers and all that, people just use simple mercury switches. So you can see there's 3 conductors here, and let's zoom in a bit and focus on that, and I'll put it down. So there's 3 conductors, and you can see the top one and the middle one, right? So the middle one is kind of common. So then there's the top one, the middle one, and the one on the bottom. So when the ball of mercury is down here, then we make contact with the top 2. And when it's at the down at this end, you can see there's the conductors exposed there. All right, so then we make contact with the outer two. So anyway, when it's down here, we've got contact with the outer one in the middle, and then when it's here, we're going to make contact with the outer one and the other outer one. All right, so it's got two different modes. So, for example, what you could do is say that you've got some device, a machine, and it's on level ground. On level ground, we can't really tell what's going on. So what you do here is you would put this at, say, 2 degrees. There's, like, let's just say that's 2 to 3 degrees. So it's at 2 to 3 degrees, and this is level. And now, if the machine is rotated beyond, 2 degrees, what's going to happen? So the machine, it's rotated, and there it goes. That switch goes. Then another way that this thing might be used is you could put this like 45 degrees, and then if it's turned back and forth, we can do that. Or if it's continuously done this move back and forth cyclically, we can detect that. So anyway, that's really cool. This stuff is very, very poisonous. Mercury is very, very poisonous. You want to be careful using anything like this and having it around. But anyway, these switches still exist, and there are many, many machines. And they're only really dangerous because they're inside of this blown glass. If they were in something safer, that would be a lot better. But anyway, so let's go ahead and let's actually build a quick little circuit and check this out with the meter. Okay, so let's go over to the other camera and let's build something. Okay, so we're over here at the other camera, and so I've got my mercury switch. So let's just do a quick and dirty circuit here. So let's see, what do we want to do? How about let's do something, excuse me, that when the switch turns on, it turns on an LED. How about that? That'll be cool. All right, so let's go back to the computer, to the screencast, and let's draw the circuit that we're going to build here real quick. All right, so let's go do that. Okay, so we're back here on the computer, and let's go ahead and let's get rid of all this. Okay, so we're going to make a little mercury switch LED controller, so this will be kind of cool. So how about, let's see here. So let's go ahead and let's say that we have a 5 volt power source. So we'll say that this is plus 5 volts. Let's put that through a resistor, all right? And we'll put that through a 100 ohm current limiting resistor. Then we're going to have our switch here. And the way this switch works is it's got 3 different leads here, all right? And so what we're going to do is we're just going to use 2 of them, all right? And well, we could, if we wanted to, we could have 2 different current paths and we could go red and green. Let's do that. Let's do that. That'll be more fun. Okay, so what we're going to do is we are going to represent it kind of like this. So here's this center, and what's going to happen is this thing, which is kind of this mercury, can be in either of these positions. So this one's kind of the common, and we're going to call this position 1, and we'll call this position 2. All right, now, so when it's in position 1, we're going to go down here and we're going to go to an LED, and this will go to ground. All right, and we'll make that one a red LED. So there's the red one. All right, and then when it's in this position, we'll go down here, we'll go down to another LED, and we'll go to ground, and this one will be a green LED. All right, so no matter what, if it's between these things and neither are connected, then neither of the LEDs will turn on. So one will say if the mercury switch is kind of in this position here, right? And we could, let's just label this, we'll just say this is the X end and the Y end, or is it in this position, right here, where this is the X end and this is the Y end. So here's the circuit that we want to build. All right, so just kind of put that in your brain. All right, and let's go ahead and let's build this. Okay, so let's go back to the bench. Okay, so we're back on the bench here. So first thing, let's connect our power supply, which I've got my bench power supply over there, and it's not on. It's just on 5 volts and holding. All right, so we got that. Okay, so now up at the top, let's zoom in a little bit for you. All right, that's better. Let me stop the camera from moving around. All right, so from the top rail, let's bring in power. So here's power from the top rail, and we're going to bring it in right here. All right, then we're going to have a switch here in the middle someplace, and then we're going to have our LEDs. So let's deal with our LEDs. All right, and then we're going to have a 100 ohm resistor current limiter. So let's find that. Brown, black, brown. So there it is right there. There's our brown, black, brown. All right. So that's going to come in and go right there. And let's get our camera to cooperate with us. All right, cool. All right, so there's our power coming in. And now we've got our switch, and then we're going to have two circuits here. And going to our LEDs, all right? So, and then our LEDs are going to go to ground. So what I'm going to do is I'm going to put each LED across the middle here. So there's one LED, and again, you know, these LEDs, let's look at the zoomed camera here. Remember, these things are polarized. Typically that large side there on the left is the ground, but sometimes not. And another way to tell is the flat side. So the flat side is typically ground or the cathode, right? The cathode. So we're going to put that there. All right, good. Let's actually zoom in a little bit more, I think we can do. Okay, now let's take both of those and connect those cathodes to ground, which is over here, keeping our wires nice and neat. Neat, neat, neat. Always trying to be as neat as possible, even though it's hard. I'm you know, obviously always rushing here with you because these videos are very long, but we got to do them. Okay, so there's our circuit right there. So now we can kind of hot wire this. We can just take this wire here. We can turn the power on. All right, power's on. We got 5 volts. And now if I connect it to the top LED, it should turn on. Okay, and we connect it to the right LED here, or bottom one. And that turns on. Okay, good. So everything's okay. So let's turn the power off. Now, mercury is not going to explode if we don't put some crazy amount of current through it and all that, which we are not going to do. So we need to find the common. And we looked at this. We looked at this thing, and we noticed that the center is common, and then the center is common. And let's see here. And we get a connection from the. Let's see here. So this actually, we get a connection from the center and the right. And then when we're up here, we get a connection from the right and this one. So in this case, it's actually this one that's common. So you got to be careful. You can trick yourself with these things. This one's common, and then these two are the two different switch positions. All right. So just going to plug those in there, kind of bend these wires out. And you can see you got to be very gentle here. There's no strain relief right here. I just have these soldered. What I really need to do is put something around here, maybe some hot glue, and then maybe some shrink tubing to make this safe. But I haven't played with this in a long time, so that's why it's just kind of like this. Okay, so there we go right there. And because this is in 3D, this is hard for you to see, because if I rotate this up, it's really hard for you to see. See, it's coming straight up. So you're just going to have to kind of bear with it, and I'll kind of tell you what I'm doing. You'll be able to see what's happening with the gravity here. Okay, all right, so let's go ahead and let's turn the power on. So we're going to turn the power on. We got everything in here. Okay, all right, turning the power on. There we go. All right, so we got the green one. So that must be the bottom one, which it is. Now if we go down here, there's the red one. And now if we go in the middle where there's nothing, if we can even do it, which is really hard, and so this is like a video game, right? If I can barely, you got to be pretty coordinated. But you see, there you go. So if you could, so there you go. Isn't that cool? And then in the middle, it'll do it, but it's nearly impossible to get in the middle. So that would be a great carnival game. So there it is. There's a little kind of game or whatever. And then again, you know, if this thing's sitting here and it gets jerked, right, or whatever, and that's exactly what these things are. Now, watch this also. That's another little interesting thing. This is, you know, it's this viscous material, right? But it moves up and down. It's elastic, right? So watch when it hits here, it's going to bounce a few times. Did you see that? I don't know if you can see it. There we go. You see that flickering, that bouncing, and then it settles, right? So it makes a connection and then it settles, right? How cool is that? So anyway, so that is a mercury switch, and that's what mercury switches do. All right. Okay, let's go back to the screencast. Okay, so so that was that, and then a reed switch. turns on and off application of magnetic field that affects an internal permanent magnet inside of the switch. This isn't always true. A reed switch is just kind of it's a switch that can kind of bend. A lot of times they are they are magnetic, but pressure could open it up or close it or some other force, but a lot of times they're magnetic. So typically there's something that bends and deflects, and then pressure switches are exactly that. The pressure, either pressure or vacuum, will turn a switch and throw it, just so you can detect different things. So anything you want to measure or detect, you can do with someone makes a switch to do that, right? Okay. And all right, and so now we're to potentiometers again. So what I'm going to do, we've gone pretty long in this video, so we're going to pause here. We've already looked at potentiometers, so we're just going to skim past those in the next video and then get to the next major section. So anyway, why don't you finish up now, stop the video, and I will meet you in the next lecture. Bye. All right, well, welcome back, and we are continuing with material. So we are going to talk about potentiometers again. We've already talked about these, and we've actually used them in a couple previous lectures and experiments, but we're just going to take another quick look and do one more experiment, and then we're going to wrap that up, and then we're going to move into capacitors, inductors, and filters, and a lot of other stuff that we need to get to. But this is kind of some of the last of the mechanical kind of switchy kind of component lectures. So let's just get through it, and then we'll separate out and go into the capacitors and inductors. All right, so on the screen, you see the symbol for potentiometer, and a potentiometer is simply a variable resistor. It's a resistor that we can mechanically change the value of, and some different mechanical configurations. So this is a kind of a little rectangular cube, and this is very small. This is probably 5 millimeter by 10 millimeter by 10 millimeter. Same with this. These are about 7 millimeter in diameter, very small. Then these are a little bit bigger. So these are maybe 2.5 centimeters in diameter, maybe an inch in diameter. And these would be for appliances that you want to control something, a radio, a TV set. And typically these smaller ones are used in electronics on a board that a user will probably never touch or play with. So we're going to go and take a look at some in a second and do a couple experiments. But first, let's kind of review what the kind of abstract design is of a potentiometer. So we've got some kind of semi-resistive or resistive material that the potentiometer is made out of. So if this is a linear version, right, and these are just circular versions, right, they're a disc instead of something that's a long rectangle like this. In any event, so let's say that this material has, 1K ohm per inch or 1K ohm per centimeter, whatever, some kind of amount of resistance per length. And we were to cut off a certain length of it, and that length is the total length here, x1 plus x2 would be the total length, and say that resistance is some total resistance. Now, if we then connect something to one end of it, a contact, and then to the other end of it, that resistance will never change. That'll always be what it is. But now if we take a metal contact or a metal slide or something that's a very good conductor, it could be even made out of a conductive plastic, right? And we take that and we make contact someplace between the two endpoints, we basically have a variable resistor, all right? And so the resistance from point 1 to point 2 in this case would be the distance x1, whatever units those are, times the resistance RE, the equivalent resistance per unit length. And the same thing, R2, 3, the resistance between point 2 and 3 would simply be the length x2 times the resistance per length. So it's a very simple, just what you would think. No big deal. And then again, we're just going through the notes here and just some little equations which you can just kind of derive if you just look at it. It's kind of common sense. All right, so what I want to do is I want to kind of do this voltage divider circuit again and kind of show you this. And now that we know a little bit more, we know why this is a bad idea, and for most cases. So we're going to use a potentiometer and we're going to make a voltage divider out of it. So we can put in some voltage, whatever that is, 5 volts, 12 volts, 9 volts, whatever, and we can split that into whatever we want over the potentiometer. The problem, of course, is, and we remember we talked about this, is that ultimately whatever the resistance is of this voltage divider, that has some kind of, it's got its resistance or impedance. And then if we put a load on it here at V out, if that load is small compared to the resistance of this voltage divider, it will change the resistance dramatically and alter the voltage. So for example, in this case, just looking at the example we have here, we have a 5K potentiometer and we've got 2.5K, 2.5K on the top and the bottom. So we got it right in the middle. If we were to put a 100K load on here, that would be 100 to 5K. So it's 20 times greater, right? So that would alter the bottom resistor very little when you put them in parallel. But if we were to put a 1K load or a 100 ohm load, that would change that dramatically. And then the voltage divider action wouldn't work anymore. So let's take a quick look at some potentiometers and let's rebuild this circuit just to review. And we're actually going to put an LED on here so you can kind of see that and see what's going on. So let's go over to the bench cameras and let's build the circuit and go from there. So what we need is we need a power supply, a potentiometer, and then we're going to take the voltage off the center tap. Now, what I want to add to this, and let's go to our screen drawing program. So what I want to add to this is something like this. I thought this would be kind of cool. So we'll have our power supply, all right? And again, I'm drawing these things, so I'm drawing this as a battery, right? So that's a battery symbol, right? Even though we're using a bench power supply. If we really want to be correct, which we really want to be correct, we would put plus and minus. That would be kind of a bench power supply, or that would be an independent voltage source, not a battery. But I'm just kind of using these interchangeably. So bottom line is it's a voltage source. Okay, and so we're going to, this is going to be plus, this is going to be minus, and we're going to set this from, say 5 to 12 volts, and it's just going to be set and fixed. Now we're going to have a voltage divider here, but what we're going to do is we're going to have a potentiometer. The symbol for potentiometer kind of looks like this. It's kind of a resistor with an arrow in between, and then it's got these three contacts here. And there's probably some formal name of these things, but typically they might be labeled, 1, 2, and 3. And then the center contact, that's definitely the wiper, right? So that's the thing that can change. So that's the wiper. All right, the center contact, and that actually moves mechanically somehow inside of there and changes the resistance. So when we have it all the way up, then let's say for example this potentiometer was a 10K potentiometer. And if we had the wiper all the way to the top, then the top part from the top resistance from 1 to 2 would be 0 ohms, and then the bottom from 2 to 3 would be 10K ohms. So it always has to split between these two things. So keep that in mind. And a lot of times when you put these potentiometers in circuits, you'll end up putting them in backwards. So you'll turn it to the right, and the resistance of the leg that you're looking at goes up instead of down. And so just test it and be careful. Okay, so this is going to be our output right here, and we don't know if it's going to be 10K. That's just an example. But so now we're going to take this as our output, all right, and we're going to call that V out, all right. And over here, this whole thing here, this is kind of ground again, right? So we're going to kind of have this over here, so that's V out, and then we're going to put a load here, whatever our load is. In our case, we're going to put let's go ahead and we'll put a resistor. So let's put a 330 ohm resistor here, and then let's go ahead and let's put a LED here. All right, a light emitting diode here, and we'll just get one with some cool color, maybe green, maybe not. And remember, this is the anode plus, and this is the cathode negative. And so what we're going to do is first we'll set the circuit up to the left. We'll check and make sure that we can modulate the voltage. And then now we already know that we've got a 330 ohm resistor here, and we've got this LED here. So whatever this potentiometer is, we really do want it to be a very low value potentiometer, like 100 ohms or 500 ohms, because if it's really big, the second we put this load on it, it's going to change this voltage a lot. And we're going to look at that. All right, but here's a circuit which will give us a variable voltage. All right, so this will give us a variable voltage at V out, right? All right, using a potentiometer. Okay, so let's go over to the bench and let's build this. Okay, so the first thing, let's take a look. Let's take a look at some of these potentiometers real quick before we go building anything. And we've taken a look at these before, but I wanted to show you them again. So this is a potentiometer, and one thing is the value is right on there, 200K ohms, and we could measure that. So that means it's always 200K from the outside to the outside. Then on the inside, it's going to be proportional to whatever the rotation is of the knob, and whatever the 200K will be divided between these two and between these two, right? Okay, so now one thing is a lot of them will have kind of a graphic on top or symbols or some kind of a cutout, and so there's an arrow there. And now notice, so now I've got this thing all the way, it won't turn anymore clockwise. So I'm going to turn it counterclockwise and right about there. So that it's about 180 degrees. It's about a half turn. So that's not very accurate. In other words, 180 degrees to cover 200K of resistance. So, you know, basically every degree is a K, right? That's a lot. So if I want something more accurate, you can get a multi-turn potentiometer where you turn it many, many times. So every little turn is very accurate and you can adjust the resistance, okay? So there's one right there. Here's another one. This is just a flatter profile. Again, this is 100K, and let's see what it does. So there's the little detent, and I'll put it all the way. So again, you know, this is a little bit more than a half turn. So I can go a little bit more, maybe 5 degrees, and I can go maybe 5 degrees. So that's probably 190 degrees, something like that. But again, not very accurate. Now here's another one. So this is, you've probably seen this a lot, and this one you need a screwdriver, and you put the screwdriver in there and turn that. And this one right here, maybe, you know, 1 turn, 2 turns, 3 turns. Let's get a screwdriver and let's find out. All right, so I've got a Phillips screwdriver here, and I'm gonna pop it in here if this will fit. If not, I'll have to get a smaller one. That'll do. All right, so let's first turn it all the way. All right, so there we are. And all right, so now I'm gonna turn it clockwise slowly. So there's 180. Yeah, it's maybe 200 degrees. So again, not very accurate. You know, these are kind of gross. You can't adjust them very well. Now here's another one that's kind of interesting. So Heliotrim and Beckman Instruments, that's a big manufacturer of components. And this one now, you can't see inside there, but there you go, maybe. You see that? And let me see if I can get the camera to cooperate with this. Not really. Let me see if I can darken it. No. Lighten it. No. There. But anyway, you can see there's a Phillips head in there that you can turn now. So now this might be mounted on something very important, and you don't want anything touching it. So you have to, you know, you have to put a screwdriver inside there and adjust it. That way, you know nothing is getting messed with. So this would be on a front panel probably, and you wouldn't be able to adjust it unless you actually put something in there. Whereas these guys, they could just be sitting on a circuit board, and you could bump into that and then change that value. So a lot of times in circuit boards, what you'll see is a little bit of epoxy or glue, like red or blue or black. After these things are adjusted and set, someone will put some glue down, and then it'll kind of keep in that position. All right. Okay. So now that we've kind of looked at those, let's go to the bench camera and let's build something. Okay. So we're over here. We've got our circuit board. We've got all our parts. And we want to get in the habit of having our parts kind of all set up so we can work and everything. So, you know, I'll just zoom out here real quick so you can kind of see. And you can see I've got kind of everything already there. I've got resistors, LEDs, switches, wires, everything all set up. I've got some voltmeters and multimeters over here. Okay, so the first thing is we need to get a value that's going to be reasonable. So I have these nice 500 ohm potentiometers. So from Jamco, which is another online distributor, kind of an older one, and they actually have a store that you could walk into. Well, they probably don't anymore, but they used to back in Silicon Valley, and you could actually walk in there and go check stuff out. So that was a lot of fun. All right, so we've got their potentiometer right here, and let's zoom in here. So this is a 500 ohm potentiometer. And let me see if I can get it to kind of we're not, there we go. Can you see that? 501. All right, so that's 5 and 0 and then times 10, so that's 500 ohms. All right, and and again, this one is adjustable with a screwdriver. And another thing you want to have are lots of little tiny little screwdrivers and whatnot. So I can put this in here and I can adjust it and turn it. And that looks like it's only a half turn also. So half turn. Now we've got our 3 leads. Okay, so the first thing is let's just always check, just do, you know what, maybe that was printed wrong, right? Who knows? Let's just make sure it's 500 ohms. So 500 from the left to the right. All right, so that's what we're going to check. So let's get out our meter. We got our meter here, and we're going to put this in ohms, and we'll put it up to 2K ohms. And let's see if we can get this all on the camera here. All right, so I've got my meter. It's on 2K ohm range because I am assuming this is a 500 ohm. So we're going to put this on here and check its resistance. Again, everything is always very difficult under this camera like this, but we figure it out. All right, so let's see if you can see that. I think so. And let me hold this. And we got the 2 outside leads. And get it to touch it. There we go. And you can see there 0.495K. That's what that means, 0.495 or 500 ohms. Okay, so that's good. All right, so we believe that. That's good. We're happy. So now let's go build our circuit. So the circuit we're going to build is we're going to bring in power right into the potentiometer, and then we're going to branch off of it. And we are going to then take that and put it through an LED. All right, so the first thing I'm going to do is I'm going to place this in here. Now, when you're doing this, kind of keep an eye on where you put those, right? So you can kind of remember, right? And because otherwise a little bit hard, so I'm going to back it out. Okay, so what I know is, looking at this, I know, I get something good to point with, sort of. So I know that this is like the number 1 lead, that would be the number 3, that would be the number 2 in the wiper. So I'll kind of keep that, and then from the rear I can get to them as well. Okay, so let's bring power in. You're going to bring power into the left half here. So here is power. We're going to put it just right up top, nice and clean. Okay, then we're going to go ahead and we are going to take the ground. Let's find a good wire for that. And this one's a little bit long, but it will have to suffice. This is going to go to ground. Okay. All right, so we got that now. All right, so now if we were to turn this on and we were to move this around, we would see a voltage at the wiper. So now let's take the wiper and let's separate the wiper so that it's someplace else. So here's the wiper, right? That's in the front or back, same place. So here's the wiper, and I'm going to put that right there. Okay, now what I'm going to do is I'm going to put something I can probe this with. So I'm going to put that right there, and then I'm going to put another wire to ground, and then we're going to put our meter on that. Okay, we're going to put one of our meters. So let's get this one here. This is in voltage, DC, and I'm going to back the camera out just a little bit for you so you can kind of see what's going on here. Okay, and kind of go like that. Let me sit that still. All right, so now what we're going to do is we're going to put the meter in here. Cool. Okay, we're going to get our, and we got this thing like that, right? So just connecting the meter, just the way to connect the meter. All right, we got the meter, and the meter's just reading nothingness right now. There's no power, so let's go ahead. And now, one thing when you play with potentiometers, set them in the middle when you fire this thing up so that, you know, at least whatever you're doing is in the middle. So it's not all the way to one extent or the other. Okay, now we're going to turn this on. Okay, now I'm putting 5 volts into the system here. So you can see it's saying 2.7 volts. All right, so now as I turn this, we're going to get more or less voltage depending on which way I turn it and which way the geometry is and all that. So I'm going to turn it to the right, and you can see we're getting a lower voltage, lower voltage. So what's that telling us? That's telling us that the from the wiper to ground is getting smaller, and from the wiper to plus is getting larger, right? So there you go. And then I'll turn it to the left, and we can get that whole thing there. Okay, so that's exactly what we want. So I'm going to put it back in the dead center, 2.5 volts-ish. All right, so 2.5. Okay, and now let's turn the power up a little bit. Let's just go ahead and turn the power up to, say, let's turn it up to 6 volts. And let's be careful now. And why we want to be careful is this. We've got 6 volts here, and we got this potentiometer, which is 2 resistors, right? So now we want to be careful because the current is flowing through the potentiometer, right? So the potentiometer is always 500 ohms, all right? So if we've got 6 volts divided by 500 ohms is, put it in our calculator, that's 12 milliamps, all right? But we want to be careful because what we can do is once we put a load on this and we basically put a load on 1/2 of the potentiometer, we could change the resistance a lot because we're shorting the resistance out. So here's the scenario. Say we put the potentiometer on 1 ohm on one leg, and then we short out the other leg with a load that's even less than 1 ohm. Now we're going to have 1 ohm of resistance, and we're going to have the 6 volts. Obviously, we're going to have 6 amps. So you can burn these out. So be very careful, you know, how much voltage, how much current, and pay attention. So sometimes what people will do is so that the potentiometer can never become a dead short on one side is they'll put a current limiting resistor, maybe 1, 5, 10 ohms, 100 ohms, whatever, on the legs so that no matter what, you can never completely turn it to 0 resistance. So just a trick or a technique so that you know nothing gets damaged. All right, so now let's add our, we've got it at 3 volts, which is half, and it's still in the center. And so now let's go ahead and let's add our LED. So I'm just going to turn the power off while we muck with this. All right. Okay, so let's put this right back here. All right, let's go ahead and let's get a green LED. Here's a green LED on the zoom camera. And remember the flat side, there we go. So that's the cathode, that big L shape, and then you can see there's a flat side. So that's the cathode, so always keep that in mind. Usually it's the cathode, sometimes it's not. You got to be careful. Now, however, what we want to do here is we want to take the output. So this is the output node right here. That's the voltage divider. And we want to put that through a current limiting resistor and then through the LED and then to ground. But we're also going to add a little switch so I can turn this on and off and toggle it to show you how the voltage changes once we put the load on. And we've done this before, but we're going to do it again. All right, and so we need a 330 ohms. That's a brown, orange, brown. Sorry, orange, brown, 3, 3, and then brown times 100. So that's 330 ohms right there. All right, so let's go ahead and let's put this together. And let's see here. So let's take our current limiting resistor and we will put it, how about this? Let's do this. Let's take the output node here and we'll put it on this side here. All right, and then we'll put our current limiting resistor here. And then we will put our switch here, or maybe how about so you can see it, how about that? All right, and then we're going to put our LED to ground here. Okay, so there we go. So there's the entire circuit. Okay, and let's zoom out so we can get the meter in the picture here. All right, I'll move this over a little bit. All right, so now what we're looking for here is we are going to turn the power on. We've got it at 6 volts. And so right now when I turn the power on, there's no load because the switch is not closed. So we should get 3 volts because we left the potentiometer still in the middle of its travel, right, of its rotational travel. All right, so I'm going to turn it on. There we go. And you can see it's 3 volts. Okay, so now if I were to turn this, and again, you got to kind of hold this. So if I were to turn this, I can turn the voltage up, I can turn the voltage down. All right, so we're going to put this at 3 volts, just where it was a second ago. All right, now, so the question is, what's going to happen when I add this to the circuit? So let's think about this. So the total resistance of the voltage divider is 500 ohms. Right now it's split 250, 250 ohms, right? Now, we've got a voltage of 3 volts, and we're going to add an impedance or resistance of 330 ohms, and then whatever the dynamic resistance of this LED is once it's on, right? Whatever it ends up being. So we've got 330 plus whatever this ends up being, maybe it's going to end up 400 ohms total. So we're going to put that 400 into parallel with the output of the potentiometer. Let's take a quick look at that back on the screen on the computer to make sure we're all on the same page. Okay, so think about this. So now what we're doing right now is we're adding this part of the circuit right here, right? And so we're going to add this in, and then what we've done is we've, of course, we've put a switch in here, right? So we put a switch in here, right here, and that's going to allow us to kind of switch this thing in and switch this thing out, right? So here's a switch like this. And then what we've said is, instead of this being 10K, this is 500 ohms, and we've got this 330. So the LED is going to have some resistance once this thing is forward biased, and it's going to have some resistance that it ends up looking like to the circuit, right? And we're saying maybe it's 50 ohms, maybe it's 20 ohms. We'd have to check it and do it and figure it out. But for now, let's just say it's 70 ohms. So the total resistance of all of this, let's just call it approximately equal to 400 ohms. If we've got that 400 ohms in parallel with this, right? So now when we have this in the center, when this wiper's in the center, what are we going to get? We're going to get 250 ohms up top and 250 ohms in the bottom. That's going to give us our voltage divider action, right? So we're going to have 250 ohms in parallel with 400 ohms. The question is, we don't want that 250 to change much. So is it going to change much? Well, let's do it. What's 250 ohms in parallel with 400? Remember the formula? It's the product, 250 times 400 over, and this is R parallel, or which is equivalent to R parallel, right? Two lines, over the product over the sum. All right, plus 400. Okay, let's grab our calculator. Where'd our calculator go? Over here. So 250 times 400 equals divided by 250 plus 400. Another thing, and that's 153 ohms, 153 ohms. All right, 153 ohms equals 153 ohms. Another thing, everybody, if you don't use a calculator a lot, if you're in school right now, high school, junior high, college, whatever, you're used to using a calculator. If you haven't used them in a while, remember the calculators do things in the order of operation. So be careful as you're entering things in, and don't be afraid to use the parentheses. So that's what they're for. So when I did this, for example, if you do 250 times 400, then you say divided by 250 plus 400, you got to be careful. You get the wrong answer. Depending on when it finishes the calculation. So what you can do to be safe is just do 250 times 400, say equals. Okay, done. Now we got 100,000. Divided by, now put a left parenthesis, now 250 plus 400. Now obviously we can do that in our head. And then right parenthesis, now equals, we get our 153. So be careful. Do your calculations twice on your calculator. I can't tell you how many times people make consistent mistakes on their calculator, but they're small enough where they don't notice it. Maybe it's 200 ohms instead of 150 ohms. And the circuit still works, or whatever they're doing still works, but it's wrong. Okay, so we got 153 ohms here, right? So the point is, now we've got 153 ohms. We've actually modified what this voltage divider is doing. So instead of it being 250 ohm, it's 250 153 ohms, right? So the voltage is going to change. So let's go see what it changes to, and then let's calculate and see if it's correct. No, let's calculate it right now. So we've got a 250 ohm and a 153. So what we really have here is an equivalent circuit. So let's do this real quick. Let's do our 6 volts. Okay, so we got an equivalent circuit here, 6 volts, and what do we have? We've got this situation here. So this resistor is 250 ohms, but this one, because we put a load across it, we messed it up, and now this whole thing is 153 ohms, right? So what's the current going in the circuit? So the current going in the circuit is 6 divided by the total resistance, right? So 6 divided by 250 plus 153, 250 plus 153 equals 14 milliamps, okay, approximately. So this is 14 milliamps. Now, what's going to be the voltage drop over this node right here, which is our V out node, right? This is the same thing as this up here. So before it was half the voltage, 3 volts, but what is it now? So now we've got 14 milliamps, so we can take the current times the resistance times 153 ohms. What do we get? 2.2 volts, 2.2 volts. So that means when we add this LED load to this particular potentiometer at this particular voltage of 6 volts, right, we're going to end up modifying the circuit and putting such a heavy load on it, our voltage is going to change. It's going to drop down to 2.2-ish. So let's go see if that's what happens. Okay, we're over here on the bench, and we've got our meter, we've got everything, we've got the potentiometer set to the middle, and we're expecting about 2.2 volts when we drop this down. So now hopefully it'll be enough to turn on the LED, I don't know. So we'll modify that and do it again. But anyway, all right, so here I go. You can see what this is showing. So I'm gonna, can I press this without covering everything? Yeah. So here we go, we're gonna press the button and we're gonna see what happens. All right, so I press the button and we get 2.7 volts. So, uh, so what happened? So what's happened is that the impedance of this LED is much greater than what we kind of assumed, right? 70 ohms. So it's just bigger, and so it's modified the circuit much less, right? So if we were to actually compute the current here, we could compute what the total resistance is of this leg, the 330 plus this, right? And then we could backtrack and then recompute and redo our calculation and correct it. All right, but nonetheless, 2.7 volts, and so we know that the LED is on, and so that's all good. So that's that. All right. So now we went from 3 to 2.7, so it's not bad. So that's not bad. It's not too bad. All right. Let's do something. Let's do something else. So now let's change the voltage and let's make it a little bit higher. All right. So let's go to 3.6, that's fine. Now I'm going to press it, and again, it's going to drop, but let's see what it does. And it dropped to 3.2. That time it dropped about 0.4. All right, so with the load on it, right, it's dropping, right, but it's not too bad because the LED is acting like a larger impedance than we had anticipated. Now, if we want to put less of a load on it, what can we do? We can increase this resistor. Right now that's 330 ohms, right? So we can just make that bigger. Now that means we're not going to get as much current flow, but at least we won't modify the circuit as much. So let's go ahead and do that. Let's go ahead and let's put a 1K ohm resistor in there, 1K ohm. So 1K ohm is a brown, black, red. Let's see if we can find that, brown, black, red. There we go. Let's look on the zoom camera here. Brown, black, red, there it is. All right, so I'm just going to pop this one out here. I'm just leaving the power on. Just be careful here. Okay, brown, black, red, there we go. All right, so now I've got our 3.6, 3.7 volts on the potentiometer. Now when I press this, we're going to expect even less modification of that voltage, right? And we're not going to be as bright, but we're going to modify that voltage even less because the load is now at least 3 times larger. All right, so there we go. And the LED is still on. It's not bad. But now look, we went from 3.7 down to 3.5, only 0.2. So that's not bad. So we improve that a lot. So now we're not loading it. So with our simple little voltage divider here based on a potentiometer, and as long as the load is a large load or low current load, right, large impedance, we can kind of get away with this if we need to. So the takeaway here is if you have a circuit where you need to generate a voltage, you can use a potentiometer, generate the voltage. Just make sure you don't put a big load on it because you're going to modify what that voltage is. But if you just need a voltage reference, that's one way to do it. There's better ways to do it, but that's one way to do it if you want to do it simple and cheap and just be done with it. Of course, you can do it with diodes. You can do it with Zener diodes, right? You can do it with other devices. You can do it with things called voltage references. You can do it with a regulator. There's all kinds of ways to do it. But this is a super simple, cheap way, and you could do it with 2 resistors also. Okay. All right. So let's go back to the computer. Okay, so we're back here and let's see, where are we here? All right, so we did this experiment. This is cool. We kind of went through that. And again, you can go through these notes at your leisure and read through this and all that. All right, so we are on capacitor circuits now. So what we're going to do is we're going to talk about capacitor circuits. We're going to talk about charging, discharging, some filters, a bunch of different things. We're going to talk about inductors. Then we're going to talk about phasor diagrams and complex impedance. We're going to talk about a lot of things in these next sections. So I'm going to wrap it up here, and I want you to finish up and then meet me back in the next lecture, and then we're going to start in on capacitors. Okay, so I'll see you then. Bye. All right, welcome back, and we are continuing the material. We are going to be talking about capacitors, inductors, and a bunch of other stuff. So probably in this lecture, we'll kind of hopefully get through the capacitor material. But our goal is to do a couple things. Again, the most important thing about what we're trying to learn is we want to learn fundamentals. We don't want to go into all the math and worry about that too much, but we want to get some intuition for how things work. That's really important. And so that even if we go through the math and you don't get it the first time, it doesn't matter because I just want you to see the material and just kind of have an idea that something works a certain way. You can always read more, dig in more later, but intuition is important. So we want to go over these things as many times as as we can in different sections of the lectures and lessons. So we're going to start with capacitors today, and in this lecture. But the goal is we want to talk about capacitors, inductors, we want to talk about their transient response, what that even means, and then we want to talk about filters. And then after all that, then we're going to get into some more semiconductor stuff. All right, so anyway, get out your notebooks and try and take some notes along. Of course, you can read these notes that come with the lectures out of my book, excerpts from my book, as much as you want. So there's more information in there. We're just going to kind of skim through things. All right. Okay, so let's start off. And so one of the first equations here, and we've seen this before, I equals C times dV dt. So what this means is the current in a capacitor equals the capacitance in farads times the change in voltage with respect to the change in time. So if you have a change in voltage and some change in time times the capacitance, that would be the current. So for example, let's say, and let's go over here to our drawing program. So we've got this modeling equation for a capacitor. So we've got capacitor, oops, and my pen is not doing what I want it to do. There we go. Capacitor modeling equations. All right, so the first one that we just saw says that I equals C times dV dt. All right, so current, and what's this measured in? This is measured in amps. And again, when we're doing circuit analysis, we're not going to use these equations. This is basically a differential equation. Well, this isn't a differential equation, sort of. But we're not going to have to use calculus and whatnot. But we just want to see where the derivations are. Even if you don't understand calculus, I'll kind of walk you through it. And then ultimately, we're going to come up with some higher level techniques later on in another lecture after we kind of get through this. And then I'm going to show you ways to work with this stuff. So anyway, I is in amps, right? And C is the capacitance, and this is in farads. All right. And C is also coulombs, right? Charge is measured in coulombs, but in this case, it's the capacitance. V, dV, right, is the change in voltage. So just a small change in voltage, right, in the way that this is written. So small change in voltage. So we'll just say, small change in voltage. All right, and dt is, again, a small change in time. All right, now this is calculus, and dV dt is these are differentials, and the whole idea is as the dV gets smaller and smaller, and as dt gets smaller and smaller, the kind of approximation of this at the limit becomes exact. So we don't really need to know what that means but we can use this as long as we kind of keep in mind that the larger the dV and dt is, basically what that's doing is it's kind of drawing lines, and whatever's happening in between this time here, we're just approximating it with a line, when in fact there could be all kinds of little changes. So you have to be careful. All right. So anyway, that's why we want the time to be very small. All right. So anyway, but let's do a little example just with this right here. Okay. So let's say, for example, let's figure out what the current is. All right. And let's say that we have a capacitor. All right, and we've got a capacitor, and let's say that we've got, and let's draw this capacitor here. So we've got a capacitor, all right, and some current is occurring in this circuit, all right. So we've got some current in the circuit. I'm going to draw this like this. This is a current is occurring in this circuit, I, all right. And here's our capacitor, and plus to minus, and it's got some capacitance C. So here's kind of something that might be going on. And then we say, all right, the capacitor, let's say, is 100 microfarads. And then let's say the change in voltage, so we we measure, right? We could measure, and remember, this is just an example. We could measure what the change in voltage is, the dV. So let's say that the dV was, say, let's say it's 1 volt. So let's say dV equals 1 volt. Then let's say that the time that that changed over, the dt, let's say that that was 1 microsecond, okay? All right, so now we've got our capacitance, C equals 100 microfarads, we've got dV, we've got dt. We can use this modeling equation to solve for this, right? So we can figure out I. In this case, it's you know, lowercase I, but I, if we want, we can just make that uppercase. All right, I tend to mix these things. All right, so I equals C times dV dt. So that equals 100 microfarads times dV, which is 1 volt, that's easy enough, times dt, which is 1 microsecond. All right, now a couple things here. When this is all multiplied and done, it's the units are going to be amps, current, all right? So one thing we could do, we've got micro up and top, we've got micro down and bottom, we've got microfarads and microseconds, right? We can cancel out the micros if that's okay with you. So let's cancel out micros, all right? And now we can just take a look at this. 100 times 1 divided by 1 is 100, right? So the answer is I equals 100 amps. That's surprising, isn't that? 100 amps. And now these values here I kind of pulled out because these are, you know, reasonable values. But this is the kind of currents that can be generated in capacitor circuits if there is a change in voltage and a change in time. And so that's why this is something that occurs when you have capacitors. If there's no resistance in the circuits, you will get enormous amounts of what are called inrush currents. Inrush. And what that is when this capacitor is completely discharged, the second that you apply power to a circuit, the capacitor immediately starts charging. And at that time equals 0, right, we get this enormous amount of current flowing, right? And then the current starts dying off and fading away as the capacitor charges. And we're going to look at that modeling in a moment. But right at that beginning, you can have amps of current, hundreds of amps sometimes. It's crazy, actually. So in this little thing right here, we see that if we have a situation where the voltage just changes 1 volt in 1 microsecond, right? And we have a 100 microfarad capacitor, that's going to draw 100 amps of current. This is why when you turn on some of your appliances and things like this, they have large capacitors inside of them, and they pull so much current from your house line voltage, from your house lines, that current trips your breakers. And that's why, you know, you might have the hair dryer on and this and that, you turn something else, it just pops it. And I have this problem all the time, you know, things, you got so much equipment, things will just go. And the reason why is that inrush current, you know, it shoots up and then it may, you know, it comes back down and stabilizes, but that peak is enough to throw the breaker, all right? And a breaker is, of course, something that when there's too much current in your home with your AC outlets, it opens up the circuit so that nothing is damaged. But anyway, so this is just a little example where we just use one of the modeling equations to kind of look at something. So I equals C dV dt. This is a law, and we can use this to do things with. Okay, so just keep that in mind. All right, let's move to something else. All right, and again, I like to use the material here in the book just as a rough guideline to see if there's anything interesting here. All right, one thing again, the symbols for capacitors. When you see a bar and kind of a half moon, typically that's polarized, meaning it has an orientation. It has a plus and a minus, so be careful of that. Electrolytic capacitors are polarized, right? Ceramic capacitors are not polarized. And if you put a polarized capacitor in the wrong direction, it could explode, damage it, a number of things. And then if a capacitor is not polarized, you'll just have two bars, right? All right, so we've seen that. All right, now what we're looking at here is kind of what we were just talking about. We've got a current source, we've got some I sub C here, and then it's charging this capacitor. And this is an electrolytic capacitor or a polarized capacitor, just charging. So current, it's charging, And as it charges, charge is going to accumulate on the plus plate, and negative charge is going to accumulate on the minus plate until the capacitor is fully charged, and then no more current will flow. Then in discharging, then what we do is we get rid of this current source or voltage source or power source, and then we would have a load, and then now the capacitor starts discharging because it was positive on one plate. We're going to get a conventional current this way, and it's going to flow through the load, right? So the capacitor is going to discharge. This event, charging and discharging, is actually quite interesting, and we're going to look at that and look at the modeling of that. All right. Now, so where do we kind of get this from? Well, we just learned that I equals C dV dt, and we've seen this before, I believe. I'm pretty sure we did. Now, again, forget if you don't know calculus, and even if you know calculus, you probably forgot it. So anyway, what we can do here is we can take this I equals C dV dt, and then we can take dt and we can put it over here on the left side, multiply both sides by dt. And then you have I dt equals C dV. Now we can integrate both sides. And all integration really means is to sum up. So we're going to sum up both sides with very, very small, tiny little sums. Tiny, tiny, tiny. And again, if you don't know calculus, no big deal. But we're summing up I and we're summing up C. And what we can do is we can solve this equation. And when we're done playing around with this, right, and kind of moving it around, then what we end up is we have voltage as a function of time equals some initial condition, the initial voltage on the capacitor, plus 1 over C times the integral from 0 to t of I dt. So, so this means if you know what the current is, right, or the function of the current, and you want to figure out what the voltage is on the capacitor, as a function of time, and you know what the initial voltage is on the capacitor, maybe it's 0, then you just simply say V sub 0, right, the initial condition, say it's 5 volts, plus 1 over C, whatever the capacitance is, 1 over 100 microfarads from our other example. And we want to figure out what the current is in, say, 1 second. We would integrate from 0 to t equals 1 second, and then whatever I is. All right, and then if you do the integral and know how to do that, then you would come up with an answer. But we're just going to leave this here and just kind of know this is kind of how this is derived. So we just have this differential model here, and then we come up with this kind of integral for what the voltage is. All right, that's all we really cared about. All right, I just wanted to show you that. And I don't need to derive this and so forth. All right, again, we're just going to kind of skim through this material. We've talked about electrolytics. These are bulky, big capacitors. They're good in kind of where you need like a very large capacitance and you don't care how accurate it is. You usually used in power supplies for filtering and just large bulk capacitance. But they're they're leaky, they're poor, they're not really good high quality capacitors. So if you need a capacitance value that stays the same, say in a filter design or something like that, you're not going to use an electrolytic capacitor. You're going to use a ceramic capacitor or something else. And then tantalum capacitors are a little bit better. They're more stable. And they have what's called low ESR, equivalent series resistance. So this is something that I want to talk to you about. It talks about it right here. And let's kind of get to this point here. And let's go back here, and I want to show you something here. If we look at a capacitor, and if you look at a capacitor model, an ideal capacitor basically is a capacitor, right? That's an ideal capacitor. But in real life, the capacitor itself has some inductance, right, on its leads. So there's actually an inductor here on its leads. And then also there's also some series resistance in the capacitor. And internally, right, there's some series resistance inside of the capacitor because it's made out of wire and whatnot. And then so we've got kind of an R and a C and an L here. And then there can even be some other parts to this model, but in general, you've got kind of an R and a C and an L, and so the capacitor really is not ideal. We'd like these components to be, there's a bug flying, we'd like these R's and these L's to be 0, but they're really not. But one thing that can be quite large is this R, and this is this series equivalent resistance. And this can be a milliohms to ohms. So if this thing is ohms, right, and you've got a big capacitor in a circuit, and you're expecting this thing to be ideal, and you have a 10 ohm series resistance, that's going to severely limit your current that can go through, not through the capacitor, but that can charge the capacitor. All right, so the ESR, equivalent series resistance, can become very, very important when you're designing a circuit and you're assuming that the capacitor is ideal. So you need to look that up, or look at the kind of capacitor, the chemistry of the capacitor, the architecture of the capacitor, and make sure that the ESR is what you need, or you'll get a capacitor that has an ESR that you want. And another thing when talking about capacitors is frequency stability. The capacitor, for example, you'll see charts, and down here is F frequency. All right, and then here is capacitance C on the vertical axis. Let's say that we had a 10 microfarad capacitor. All right, so let's say that this is a 10 microfarad right here. Now, let's say that this is 1 megahertz, right? And we're just making this up. All right, and so we want something that's frequency stable. So maybe at 10, at 0 hertz down here, this thing is 10 microfarads, as it should be. But as we get closer and closer and closer and closer and closer to 1 megahertz here, the capacitance starts dropping down in this case for this particular capacitor. So by the time we get to 1 megahertz, maybe it's only, maybe it's 1 microfarad. So that's not going to be useful if you're going to be using your circuit at 1 megahertz. So you also have to look at the frequency stability, you have to look at the temperature stability, you have to look at, as you put current through it and so forth. So all these things can affect the capacitance. So keep all that in mind, all right? They're not ideal. We're going to do computations as they're ideal, but when you start using them, you're going to start to see your calculations and what happens are not the same. Okay. All right, so this figure right here is an interesting depiction, and what this shows is that capacitors block DC, and because they block DC, we can filter out DC on a capacitor. And so what this is showing here on the left, we're showing time, and we've got some sinusoidal signal, and then on the right, we're saying that we're taking that and putting it through a capacitor, and then what's happening is we're filtering. So this is a filtering operation. Now DC has a frequency of 0 hertz, right? So we can use a capacitor here as in this case, this is being used as a high-pass filter. So the capacitor will only pass AC. So DC, it gets blocked. So what it does is it removes this DC offset, okay? So this is a really important operation, and this is done in a lot of radio equipment, amplifiers, and so forth, because what happens is the signal may have a DC offset as it comes in or as it's being generated, and we want to remove that DC offset and just have the AC signal. For example, let's go back and draw something here. All right, so let's see here. Let's say, for example, that we have some kind of audio amplifier. So let's say that we have some kind of signal coming in here. We've got some kind of signal, all right? And let's say that that signal goes into some kind of amplifier, all right? And this is usually use a triangle kind of as an amplifier or a gain stage, right? And let's say when this thing comes out, it is amplified, but let's say that the amplified signal is and let's draw a graph here. So here's time here, all right, and here's voltage here, right? And so let's say that this one, here's 0 volts here, all right? So this one is, it's got no DC component, all right? It has no DC component. So this is just an AC signal, and its reference is 0 volts. So that's good. So it's going positive and it's going negative. And here's 0 here. But let's say that after this is amplified, for whatever reason, this particular amplifier ends up putting the signal, say, right here, and then it amplifies the signal, and I'm just, trying to draw this like it looks over there, but it's amplified, and it's got some gain, and say the gain maybe in this case is, 3 maybe? So this is times 3 gain. All right, so we got the gain that we wanted, but now we have a problem. And the problem is during this gaining operation in this particular amplifier, we've actually added a DC offset to our signal. All right, and the problem with this DC offset is that no matter what, wherever we send the signal, it's always going to have this DC component, and then this AC is riding upon this DC. So what we really want in many cases is it to be about 0 volts, right? So we want to remove this DC offset. So what we can do is we can take the output here, all right, and we just simply put it through a capacitor. And of course, the size of the capacitor matters, but typically a large capacitor, all right, a large capacitor. So this might be anywhere from 10 to 220 microfarads, all right. Now what's going to happen is when we look at the output here, what's going to happen is this signal now is going to, and I'm going to kind of draw this graph here again. Matter of fact, let's draw it like this. All right. And what we're going to see is we're going to see the signal will be, all right, like that. And actually, of course, this would be 0 and this would be time moving forward over here, and then this is voltage over here plus, and then this is voltage minus here, right? So, but the point is that this removes the DC component, and the reason why is because DC current cannot get through a capacitor, and we already looked at that. Why? Because if we look at this real slowly in time, as the signal goes high or as the signal goes low, current starts flowing through the wire and charge accumulates on one plate and then the opposite charge on the other plate. Then as the voltage switches, then the charge moves off and accumulates in the other direction. But current never passes through the capacitor. So if we zoom in here, we are never going to see electrons moving, over it, or holes moving the other direction ever, ever, ever. Now, in reality, they actually do, because they leak through there, and we don't want that. So they actually make it through there, and that's leakage current. But in the ideal model, there's never a current. So they block DC. Capacitors block DC. All right. So this is a very useful property of capacitors. And then this is kind of what the filtering basis that we're going to look at in a bit is based on. But this is kind of a fun thing. And what you'll see is a lot of times, so if you're playing with Arduinos or Raspberry Pis or microcontrollers, one thing that you'll see a lot of is you'll see an amplifier, and there's some really old amplifiers. One's called the LM386, and this is just an IC, and this thing is probably from the 70s. And some guy copied it at some point and put it out on internet, and now you'll see this thing everywhere. But this is really old, it's really crude, and there's way better chips than the LM386 to do audio amplification, but nevertheless, people use it. Anyway, you put an audio signal in here, all right? And so there's your signal in, and then you get an output signal here, which is amplified, all right? Except it's got a DC component on it. And so to remove that DC component, what you'll see on these schematics, when you see these LM386 schematics, is you'll see a big capacitor here. All right, and it'll be like 220 microfarads or something. And that's to block the DC to give you an AC signal. Then that nice AC signal will then go into a speaker. All right. That'll go into a speaker. And like I said, once we learn more about capacitors, inductors, and a few more components, we're getting through this. We got a couple more sections. We're going to start building things at a high level, and then doing schematic entry. So it's going to be a lot of fun. But we got to learn the basics. Got to learn the fundamentals. Now, let's go back. Let's go back to our document here. All right, and what I want to do is let's actually do an experiment right now where we create a signal, we'll put a DC offset, and then we'll block it with a capacitor, and then we'll see that DC offset go away. So that'll be cool. Let's do that. Before we do that, let's real quick, since I brought it up, I want to, yeah, here we go. Let's just Google real quick. So let's Google for LM386. All right. And you can see here if you just, lots of things will come up. And if you go to TI, for example, Here you can actually buy one. So this is a wide VN low power audio amplifier with internal gain. And then if we were to take a look at the data sheet for it here, and lots of companies will make the same chip. All right, if we were to take a look at the data sheet, you can see the internal schematic of it. And you can see how simple it is, right? It's just a couple inputs and an output and then some controls here, right? And then again, the data sheet shows you all the specifications of it. You kind of scroll through here, and then you know, you can look at all this stuff, just distortion versus frequency and so on and so forth. And then it has applications, and most IC manufacturers on their data sheets, if it's a good company, will actually put a bunch of applications. So you can see right here, amplifier gain equals 20 with minimum parts. So what do we got? So here's where the input is, VN, so that would be your input signal. And then they've got the negative input of this. This is kind of an operational amplifier is what it actually is, and we'll talk about those later. But anyway, it's got the negative or inverting input to ground. And then the positive input is to a potentiometer. So see this 10K? They're using the 10K as a volume control. Here's the signal in. So whatever the signal in, they can pot it, right, up and down with this potentiometer. That goes into the non-inverting input. And then check it out. They've got this right here. This capacitor right here is kind of a stability and a filtering capacitor. But here is that big bulk 250 microfarad. Of course, no one would ever use a 250. They would just use a 220 or a 330. And let me segue to something real quick. A long time ago, when you know, electronics first became electronics and things were being manufactured, there were only so many components that were made and on hand, and they had certain values. And because these were the only components that were on hand, electrical engineers started designing around these values. And so it's almost like kind of this history of electrical engineering and electronics, and kind of this tribal knowledge, and designs use these certain values. Even though we have every value imaginable now, what you will see is, instead of a 200 ohm resistor, which would make sense, right, because it's a nice even number, you'll see a 220. Instead of a 300, you'll see a 330, right? Instead of a 2 microfarad capacitor, you'll see a 2.2 microfarad capacitor. And the reason why is because when they manufactured them, they only had certain values they would manufacture. They would just end up being certain values, and engineers would get those. So that the only thing you had to work with was 330 ohm, 1K ohm, 10K ohm, 22K ohm resistor, a 10 microfarad, a 2.2 microfarad, a 3.3 microfarad, a 220 microfarad. You see, you didn't have all these other values, you just had those. So when you see designs, you're going to see these numbers, you're like, 220, where did he get that? It would be much nicer if it was an even number or whatever, but the reason why is we'll design around those values. And typically when you're doing design, electrical engineering design, circuit design, you design within a half order or an order of magnitude tolerance. In other words, if you're a really good engineer, if the values of components vary a lot, right, within, you know, 10, 20, 30, 50%, the circuit will still work, right, if you're a good engineer. So a lot of times it doesn't really matter. And plus the tolerance is typically 5 or 10% anyway. So that 10K resistor has got plus or minus 500 to a K ohm anyway. But anyway, that's why you'll see some of these funky values, 250 microfarad. I have literally in my entire life never seen a 250 microfarad capacitor. I'm sure you could buy one, you could buy a million of them, but typically you'll see people use a 220 microfarad, or they'll put it up to the next value, which would be 330. Those are the common weird values. Anyway, so here's the schematics. And you could build any of these things, and a lot of times these application notes have mistakes or omissions, or they're making assumptions that you know what you're doing and you know how to hook stuff up and do all that. So you got to be careful, because a lot of times they'll just show part of the circuit, but they won't show bypass capacitors or this or that, and you'll kind of hook it up and it doesn't work right, and you're wondering why. And the reason why is because you didn't add some other things they're assuming you know how to do. Anyway, so that's the LM386. Okay, cool. All right, so let's get back to this. And why don't we, let's keep going. And instead of stopping and starting in another lecture, let's do this one experiment right now, and let's do a DC blocking experiment. And then I think we will get into, we'll talk about series and parallel capacitors in a moment. That'll be easy. That'll take just a minute. Yeah, and we'll do the charging and discharging in another lecture. Okay, so let's kind of look at what we're going to do here. All right, so all we're going to do is we're going to make a circuit. We're going to use a signal generator, and we're going to pump a signal through a capacitor, and we are going to remove the DC offset. So what we're going to do, let's just erase all this. Okay, and let's see here. Let's get green. Okay, so what we're going to do is we're going to take our signal generator, and this could be anything. This could be a piece of hardware that generates a signal. It could be an audio signal. You know, and maybe later what we'll do is we'll actually take an audio signal from the computer, and I'll take that and plug it into something, and we'll filter it and do that. That'll be fun. We'll do some of that. But right now we're just going to use the signal generator, right? So signal generator. Okay, and you remember this just generates a signal. It has 2 channels, and we're going to put a signal out. All right, and then the signal generator allows us to do a couple things. We can put out, you know, sine wave. We can put out, you know, square waves. We can put out triangle waves. You can put out anything you want. You can put out completely arbitrary waves, arbitrary, anything. And we can control their frequency, and we control their amplitude. We can control their DC offset, and that's what we're going to do. So what we're going to do is we're going to just put out something. And that is a horrible sine wave. We're going to put out a sine wave, okay? And as a matter of fact, let's make that red so you can see it through all my other chicken scratch. Okay, put out a sine wave. And so down here is time, right? Okay, and up here is voltage. This is voltage, V. All right, and this is 0 volts here, right? 0 volts right there. So clearly there's some DC offset here, right? Some DC offset. Okay. And what we're going to do is we're going to actually control that DC offset, and we'll put this out, you know, we could put out, you know, 1 kilohertz, you know, up to, you know, megahertz, whatever. The signal generator, my signal generator, the Rigel DG4102 that I have will go up to, I think it's 200 megahertz. Yeah, 200 megahertz. It'll go high. Anyway, so we're going to do this. So here comes the signal out here of our signal generator. So there's our signal generator. Then what we're going to do is we're going to take that, and we are simply going to look at this with the oscope. So then over here, we're going to have our oscilloscope, right? And this device, of course, basically takes a voltage in, right? It's got, you know, 2 or 4 channels. These are the channels, right? And then it draws on the screen whatever the voltage is that it sees as a function of time. Voltage is a function of time that it sees here. So if we take this and we plug this into one of these channels, right? There's channel 1, channel 2, channel 3, channel 4. Then what we're going to do is we're going to see the signal on the oscilloscope. So with no capacitor, with no anything, we're just going to what we send out is what we should see in. Okay. Now we're going to then come into the circuit, and then we're going to break it open. So let's erase this, and we'll show this. We're going to come here, and we're going to open this up. And then what we're going to do is we are going to put a capacitor. And let's draw that in a different color. How about that? Draw our little capacitor right there. Cool. And that's it. And then we're going to make this capacitor some value like, you know, 100 to 220 microfarads. And then what you'll notice is we're going to lose this DC offset. So over on the oscilloscope, the DC offset will go away. All right, so we're just going to build this little circuit right now, and just kind of as a warm-up for what we're going to be doing next in some of the filtering experiments and all that. All right, so let's get over to the bench and let's go take a look at that. Okay, so we're over here on the bench, and we're going to get our oscilloscope, and we're going to send out a signal from the signal generator, and we're going to put it into the oscilloscope so we can see what's kind of happening and get that going. All right, so the first thing that I want to do is let's go ahead and let's get the camera on everything here so we can take a look at what's going on. We're not going to really need much circuitry. Yeah, we actually are. So you know what? So the first thing let's do is let's just get a capacitor into our circuit board in preparation for the experiment. But first we'll send it straight in and straight out. All right, so let's do that. So first thing is, this is the power, and we don't need this. So let's remove the power. We're going to move that over there. All right, now I'm going to get, so I've got the signal generator. So once again, let's kind of take a look at this stuff. Okay, so there's the oscilloscope. All right, so that's sitting there, and that's what we're going to view things on. And there's our signal generator, and that's what we're going to generate the signal on. All right, so let's see if we can get both of these in view at the same time so we can kind of see what's going on. All right. Okay, so I think that's good. We've got both the oscilloscope and the signal generators that we can see things. All right, so now we've got our little circuit board here, so let's kind of get something going here. All right, so what I'm going to do first is this is the output of channel 1 of the signal generator. All right, so we're going to hook this into our circuit board, and this is going to be our input. Now, to make this easy, what I'm going to do is I'm going to put the input over here on the right side. All right, so we're going to kind of flip this around. So this is going to be our input. So we'll put ground down here at the bottom, and we'll just move these little posts. So we're going to put ground here. We'll put plus up here. Okay, good. All right, so we got that. Now, the signal from the plus side, and remember this is going to be an AC type signal, right? But we can still have a ground and a plus just as references. So from the plus side, I'm going to come in here like this, and we're going to take it like that. And then now what we're going to do is we're going to take the signal out, and we need to put another post. And what we're going to do is we're going to put the oscilloscope. We'll put the oscilloscope here because we want it semi-close. The longer these cables are, the longer these leads are, there's inductance in them. So that's where we'll have ground. And then we're going to have the output of our little circuit. We'll have our output of our little circuit will be, let's say, right here. Okay, actually, let's make it right here. Okay, so we need another wire. And this will all make sense in a second, I promise. I know right now it looks confusing. Okay. All right, so we're going to put our capacitor, and as a matter of fact, let's put this up here. We'll put our capacitor here someplace, and then, so the capacitor is going to go across there. So then there would be the output, and then this is going to go here, like this. All right, let's get a little bit longer one there, even though shorter is better, but it's stretching a little bit. So let's put it right there. That's good. Okay. And again, I don't want to build circuits beforehand. I want you to see how I do it. I want you to see the thought process because it's important, because otherwise, you just kind of do things and maybe they won't work. But I like you to see what's going on. All right, so this is really, really simple. Okay, so looking back at the signal generator, so here's the signal generator. All right, and we've got channel 1 here, and that's what we're going to use. So right now it's at 40 kilohertz. So first, let me go change this. And I'm going to lower this down to 1 kilohertz. All right, then it's at 20 volts peak to peak. I don't want that. So we're going to drop this down, and we're going to put this at, say, let's start off with 1 volt just for a second. And then we got to play with the DC offset and all this, right? So now, if you look at this, it's got a high of 500 millivolts and a low of minus 500 millivolts, all right? So now what we need to do is we need to offset this. So we need to push this up. So first, let's put the amplitude, let's actually put the amplitude at 5 volts. All right, and again, if we press this amplitude button, it's centered around 0. And you can see the waveform right there is centered around 0, right? It actually shows you the waveform. Now what we want to do is let's go ahead and let's put an offset. So let's raise this 2.5 volts, okay? So 1, 2, all right, and 0.5. All right, so now you see the waveform has got this kind of offset. Now if we go look at the amplitude here, the high is now 5 volts and the low is 0 volts. And the reason why is we push this waveform up. So it's got a DC offset of 2.5. It's still an AC signal with a 5 volt peak to peak with a 2.5 volt positive peak and a negative 2.5 volt negative peak. except it's got a DC offset, so it's never going to get negative. It's always going to be a positive signal, and hence that's what our problem will be that we're trying to solve. Okay, so we got that. It's at 1 kilohertz. So the second I press the button here, that will turn that on. Hopefully you can see everything here. All right, so now let's get our oscilloscope. So let's look at our oscilloscope. We've got 2 channels right here, and the cables are just kind of on the back here, so they're not in our way. So I'm grabbing this first cable here, all right, and then now if we look back on the bench here, we see our circuit board, and here's our probe. Again, what do these things look like? You can take that off. There's a little probe tip in there, real sharp. You know, I poked myself with that a lot, and then you pull this back and you can grab onto things, and then here's the ground. All right, now also, this is the setting. This is the impedance setting, either 1 times or 10 times. We're going to be looking at a fairly small signal, so we'll put it on 1 times, all right? And now what we're going to do is we're going to connect this to the ground, which is right here, okay? And then we're going to connect this to there. All right, now, so the first thing that we want to do is we're going to turn on the signal generator, and let's go back to the first thing that we're going to do is we're going to turn on the signal generator, and then we're going to look at the signal on the oscilloscope, right? So we're going to kind of do all these things at once here and kind of go back and forth on the cameras. All right, so now let's look at our circuit right here. Now, so we're missing something right now. We don't have anything connecting the input to the output, right? So when we turn on the signal generator, so let's go ahead and turn on the signal generator. So watch me do that on the other camera. So we turn it on. The signal generator is on. Little light there and little output there. So that's on. But we see nothing on the oscilloscope, and we shouldn't because there's air connecting this. That's exactly right. So we'll turn off the signal generator. That's what we expect. Now what we'll do is, coming back to the camera here showing our circuit, we're just going to put a piece of wire here, and this is going to be our little connector. Maybe that's a little bit too long. Let's use a shorter one. All right, let's use a shorter one so it's not too inductive. Okay, so now we've got our little piece of wire, and we're just going to connect this thing over here, just like that. Okay, now when I turn on the signal generator, we should see the signal on the oscilloscope. So let's do it. Here we go. Okay, now something just happened on the oscilloscope. Now, what do we need to do? We need to adjust the oscilloscope so that it can see the signal properly. So right now we've got a 1 kilohertz signal. And what we need to do is we need to adjust the sweep rate of the oscilloscope, and that's what this knob does right here. So I'm going to adjust this. Okay. All right. So now it's saying there's 400 microseconds per horizontal division. All right. And we can, adjust that like we like. Now here's the voltage per vertical division, and right now it's at 200 millivolts per vertical division. So we can. Okay, now, so there's a problem, and the problem is the probe right now, we set the probe at 1 times, and I bet you the probe, so we'll press this channel 1 here on the oscilloscope, and see the probe is on 10 times. Hopefully you can see that. So we got to adjust that. We got to put it on 1 time so the gain is correct and everything is correct. And see here's another thing. See the coupling? It says DC coupling. We want AC coupling. We want the full AC signal. All right, so we want AC coupling. Well, actually, I'm sorry. We want DC coupling. All right, we want the DC signal. The oscilloscope has a filter and it can remove DC itself, so we want to make sure we don't let that do that. And then we want DC coupling here. All right, there we go. Okay, and so we've got our 5 volts peak to peak, and I'm still not getting what I want here. Did we do something wrong? There we go, 500 millivolts. We have everything working now, so I actually had to pause for a second. The probe here was actually bad. So the mechanical assembly right here, something had loosened up and we weren't getting any signal, so I was kind of going crazy wondering what was going on there. So anyway, we have our circuit, we have our short, all right, and so now let's take a look at what we have here. So on the signal generator, we've got our 5 volt peak to peak with an offset of 2.5 volts. Over on our oscilloscope here, we've got our signal, and we can look at this, And first we can see that here is the reference and it's down here. Here's 0. So the signal is actually riding high, which is good. Now we can go ahead and we can press measure, and the measure button here will kind of measure a bunch of things. We've got to kind of tell it what we want to do here. So let's see here. Let's say modify, and every time I play with this thing, I've got to figure out how it works again. So I think that'll do it, and we hit OK here. Is that doing what I want to do? No. All right, so that's bugging me. So let's just go, and we're going to do cursors, and we'll say cursors, and we want to measure voltage. We want to measure channel 1. So if we look up here, and we go to the top here, and we go to the bottom here, sure enough, it is the 5 volts that it should be from top to bottom. That's what we expect. And then we can see that it's riding in the middle clearly. It's 1 volt per division right now. And if you were to count here, 1, 2, and a half, it's at 2.5 volts, which is what it should be. So again, we could put we can move these cursors here, and we'll put the start cursor on the bottom of the signal. And there we go. And then we can put the end cursor in kind of the middle here. All right, and again, as we move this thing up, it should be at about 2.5, and sure enough, you know, it's at dV is 2.5 volts. So the signal is doing exactly what it should be. So it's riding on top of a DC offset. So there is a DC offset. Now let's just move this signal. We'll move it down to the bottom of the screen here, and watch this little flag, the little number 1 there. Hopefully you can see that. See how it turns red right when that just means I'm just going beyond the screen. And so that's what we're going to call ground right there. And then maybe we can do this so you can kind of see the signal a little bit better. Okay, so now if I increase the frequency on the signal generator, right, we should just see the frequency increase, right? So we should see more waves per time, and we do. All right, and there's 10 kilohertz. All right, but their amplitude is not changing because we're going through a straight wire here, which is what we expect. And we've still got this DC offset sitting here. We're riding on top of, there's ground, and the middle is 2.5 volts. Okay, now let's go ahead and let's put our capacitor in the circuit. We'll drop it back down to 1 kilohertz, and let's put our capacitor in the circuit, and then we're going to see the DC offset go away. All right, so let's do that. So first I'm going to turn off the signal generator. And now we're going to find a capacitor here, and we want to find a large enough capacitor. So let's see here. So here's our little box of capacitors. So I'm just going to move this out of the way here so you can see this real quick here. And let's see what we got here. See if we got a big guy, something big here. Here is 150 microfarad. That might get it done. There's 47, and that's 4.7. Let's see here. There's a 220. So here's a 220 microfarad right there. All right. So we'll go ahead and we'll put that. And now the size of the capacitor, why does it matter? Well, we're going to learn when we talk about filters is the capacitor, along with the resistance of the wires and all that, creates a filter, a low-pass filter, a high-pass filter. And in this case, the size of the capacitor matters. Past a certain point, it won't matter, but what's going to happen is as we change the frequency, we're going to get a filtering action, and we're going to get a high pass filtering action because we're using this capacitor as a high pass filter configuration, which we're going to learn about in the next lecture. So the problem is it's a high pass filter. So depending on the capacitance, as we change the capacitance value, where it starts passing frequencies, what it considers to be high frequency, right, a high frequency, will depend on the capacitance and the resistance of these lines and all that. So that's why we're picking a big capacitor, because I basically want high to be like 1 hertz. Anything greater than DC, I want it to pass, but I want it to block DC. Okay, so we're going to put the capacitor in, and it's polarized, so we're going to kind of be careful here of its orientation. We're going to put the positive side towards the positive terminal here. All right, and we're going to put this in here like so. All right, and so we've got that in there, and now we're going to turn the signal generator on, and what we're looking for is the DC component to be gone. All right, and there you go. So as you can see on the oscilloscope, now we've got 0 here. Now the interesting thing is, let's change the we can change the sweep rate here. Yeah, we can change the sweep rate. And if you look, we're not exactly completely removing that DC component. And the reason why is that there's nothing for the capacitor to discharge into. So right now there's like no impedance. So we're putting charge on the capacitor and we're taking it off, but we're doing it with very high impedances. So there's like nothing for the capacitor to discharge into. And because of that, now normally with an amplifier, there's some output impedance and then there's some impedance into the load, so we can pull that current off of it. But right now it's acting very ideal. So what we're going to do is we're just going to put a teeny tiny bit of resistance in the circuit so that there's something to dissipate some of this charge, all right? And then that will help the situation. And then we'll get this DC offset completely to zero where we want it to, and not kind of floating. It's kind of floating here. It should be dead in the center. All right, so let's go ahead and do that now. All right, so now the whole idea here is we want to put some impedance in the drive side here so that we have something for this thing to discharge and put charge on, put charge off from the signal generator side. So what we're going to do is we've got this lead here coming from the signal generator to the capacitor. We're going to open that up, and we're actually going to put a small resistor, a 10 ohm resistor in this case. This should take care of our problem. All right, so this should get things to work, and make sure everything's good. All right, let me turn this thing on. Okay, so I've turned on the signal generator, and now your view is back to the system. So now you can see the oscilloscope, and sure enough, the DC offset is gone now, and we're dead in the center, which we would expect. So that's exactly what we want. All right, now let's do something. So what we're going to do is on the signal generator, let's change the frequency. So as we change the frequency changes, and the offset stays in the middle, right? So we've removed the DC offset here, all right? No matter what the frequency is, and let's go up to some higher frequencies. We remove the DC offset, and let's go up to some higher let's go up to some higher frequencies, all right? And no matter what, you can see that that is removing it. Now what's starting to happen is we're in megahertz here, and this is still working. We're in megahertz and it's still working, and I can open this up so you can see the waveform. All right, so it's still working. We've still removed that DC offset, so how cool is that? And we're at 5 megahertz, and we could keep going. Then as we go and go and go, different parts of this circuit are going to start acting like low and high pass filters because there's wires and resistors and other things here. Now let's drop this back down to something less crazy. We'll just leave it at say a megahertz. All right, and then so now what I want to show you is I want to change what the offset is, and I want to push the offset up. All right, so let's go over here, and we're at the signal generator, and we've got the offset as 2.5 volts. So the total amplitude is still 5 volts. So it should be 5 volts no matter what. But now we're going to shift what this offset is, and we're going to increase and decrease it in real time to see if this thing, what happens. All right, now watch this. So let's lower it down. So now we're going to lower the offset down, and now notice what's happening here. So as we lower the offset, the signal, and I don't know if you can see this, it's lowering, but then it's slowly creeping back up. See, watch this. I'll lower it. So look right here, all right, and then it's slowly creeping back up, all right. And again, and now I'm going to move it back up, and I'll move it up high. So I'll move it up high. So now you can see it's off center, all right, but it's slowly creeping back down. And the whole point of this is that we just do not have enough impedance here to discharge this capacitor. The capacitor needs some place to discharge. All right, if it doesn't have a place to discharge, then we're putting charge on it, and there's no place to really remove the charge. All right, so what we can do is we can simulate a load on the other end also. So what we can do is we can put, like, let's put a 10K resistor. We'll put a 10K resistor on the output, so back here. So here's the output, and we will put a 10K resistor here. and we'll put that to ground. Let's get a big enough wire. All right, and then this will go to ground. All right, now watch the signal. So so you're watching the oscilloscope right now. And okay, so hold on. Let's change what this offset is again. So we're gonna put the offset down low, okay, and it should recenter itself automatically, but it's moving very, very slow, like so slow you can't even see it because there's no load. Now the moment I add the load, now watch what happens. So you see it moving up quickly now. So now there's something somewhere for this charge to go. So now as I change what this offset is, so I move the offset up and then watch it pull itself back down. And I move the offset down and now it pulls it back up. Okay, now what this also has to do with is the size of this giant capacitor. Because we picked a giant capacitor because we want to block DC and we want to pass AC, right? We picked it so big, right? We picked it so big that anything but DC it passes, and so the capacitor is filling up with charge, and once that charge is there, it takes a long time to get it off this big capacitor, right? If we're willing to tolerate a frequency response where we can pass, say, 10, 20, 100 hertz instead of we want to pass 1 or 2 or 3 hertz, right? We don't care about 1 or 2 or 3 hertz. There's no audio there, right? 100 hertz is like where we kind of want to start doing things. So why don't we change this capacitor, and we're going to lower the capacitor. Now watch what happens. So again, I'm going to go up and down, and you can see how it responds sort of okay. I'm going up, I'm going down. All right, and matter of fact, I'm going to put that offset on volts. There we go. So there's 1 volt, 2 volt up, 2 volt down. All right, now let's change the capacitor and let's make it 1/10. Let's see, do we have a 47? Did we have a 47 there? I think we did. So let's see here. I believe, yeah, here's 47 right here. So let's put this in here. So this is about 1/5, all right? And I'm going to turn off the signal generator. And we're going to put this in here. And this is the last thing we're going to do. And then we'll wrap this up. This one's getting pretty long. All right, so here we go. We're going to put this in this way. All right, so we've got our 47 in there. All right, I'm going to turn on the signal generator and then take a look at the oscilloscope. All right, and you can see the signal generator now. All right, so now we're at -2 volts for the offset, and oops, as I change this, you can see it moves very quickly. Moves very quickly up, very quickly. So it just removes that offset pretty quickly. All right. And that's that. So there we go. So it's basically blocking DC. It's letting the signal get through, and we're using it in this case so that if we had a DC component added to something, we can remove it. All right. So anyway, this is a really crude example. What we really want to show is a filter, and this is very hard to do because we have no resistance here, and we're kind of counting on the resistance of these cables and all that. So this is not doing exactly what we want to do, a little bit hard to get working. I've had to start and stop this a couple times to get this working somewhat okay. But in the next lecture, we're going to start talking about the transient response, and then we'll get into filters, hopefully, and then we're going to do this properly, and everything will make much more sense, okay? So I'll see you in the next lecture. Bye. All right, welcome back to the next lecture. So we're going to talk about, we're planning on talking about charging and discharging of capacitors and then filters and so forth. However, we still have kind of this outstanding topic of capacitors in series and parallel. So I thought what we're going to do is we're going to do a quick lecture, get done with those two kind of subjects, and then we're going to go to the charging and discharging so we don't dilute that lecture with this material. So on the screen right now, you see a depiction in the figure of parallel capacitors. And now the kind of figuring out why capacitors in parallel sum up is that you can kind of do by inspection. So the question is, if you have a capacitor and you put it in parallel with another capacitor and so on, what is the equivalent capacitance, all right? So looking at this figure, we're saying that the equivalent capacitance is simply the sum, C1 plus C2 up to Cn here. All right, and if you look at this equation, C equivalent C1 plus C2 plus dot 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 plus Cn. All right, and the reason why this is, and you can almost do this by inspection, the reason why this is pretty simple. If we just take, so let's go to the drawing program. Let's take a look at this. All right, so let's do the case where we just have kind of two capacitors here. So let's say that we have a voltage source, plus to minus, and it is surprisingly hard to draw a circle on these tablets. All right, so let's say we have a voltage source, and we close this voltage source at some point, and we have this capacitor here. We'll call this C1. It's going to charge up plus to minus. We're going to call that V1. A current is going to flow initially, and current is going to flow initially, and then that current is going to die out once this thing gets completely charged, right? All right, so from the, and here's the plus charge, and we could say that, oh, let's use yellow for the minus charge. And once this is completely charged up, it's just at a steady state, it's done, the capacitor is charged. Now, from the capacitor's point of view at these two nodes here, it simply sees this voltage V over it. And this voltage source is going to supply a current, right? And this current I, which is going to change as a function of time. This current is actually going to start off very high, and then it's going to die out. All right, and we're going to learn that transient response a little bit later. But as far as the capacitor is concerned, it just sees a voltage source, and then it charges, and then that's it. So if we were to look into the circuit, right, if we were to cut the circuit, you know, from here, and we were to look into it, right, here's our little eyeball looking into it. Right, from that point, we just simply see this capacitance C1. Okay, now, if we were to add another capacitor to this circuit, all right, and we call that C2, it too is going to charge plus to minus. We could call that V2. And the moment that we turn this power supply on, you're going to get this I, we'll call this I1 now. And then we're going to get another current, which is going to come through here, like this. And this is I2, right? And so we're going to get this I1 and we're going to get this I2. And now we got to be careful here, because what's really going to happen is when this current leaves here, right? We're going to call that current. So in fact, we might want to, let's do this. So we're going to have these two currents, but let's label them a little bit better. Let's be more precise here. So there we go. So the current, so there's going to be one current going through this branch right here. And in fact, you know what? I don't like this at all. Let's delete this and come back here, and then let's erase this and make this a little bit different to make this clear. So when you just have one capacitor, we just have that one current, and this is going to get a little messed up, but I think we'll survive. All right. Now, okay, so now when we have two, so what's going to happen is this. We're going to get this current, which is going to leave the battery. Then what's going to happen is the current is going to split off like this, much better, and go down here, all right, and then this current is going to continue on, all right, and then back up here. And at this node here, these two currents are going to sum up. So let's name some of these currents. So we're going to call the current leaving the battery, we're going to call that I. We're going to call the current returning to the battery, we're going to call that I. But the current going down this branch, this is going to be called I1 now. And the current going down this branch is going to be called I2 now. All right, so that's a little bit, that's more correct. That is correct. That's what's going on. All right, so the interesting thing here is the capacitors don't know the other capacitor is there. All right, so as far as this capacitor is concerned, it's got a voltage source and it's going to pull as much current as it needs. It's going to charge. It's going to just do its thing. Same with this capacitor. And the reason why is this node right here all has the same voltage, right? Remember, if we can draw a surface over a node, right? So there's one node and the same thing here. Here's another node here, and this will all have the same voltage, right? So those nodes have the same voltage. So from the perspective of C2 and perspective of C1, they simply see, oh, and we got a little typo here. This should be V2, right? This is V1. From C1 and C2, they simply both see this voltage V, and V1 equals V and V2 equals V, and they both these capacitors simply charge up. So again, if we were to look at it, open the circuit up right here where this little yellow dotted line is and look in, we would see the capacitance C1 plus C2. In other words, parallel capacitors sum. All right, so parallel capacitors sum. So in this case, C equivalent equals C1 plus C2. So if we wanted to redraw this circuit and make an equivalent circuit, we simply have this. This is it. And this C equivalent, so we could do it like that. And again, we have, this is our V right here, and plus minus, and then we have our voltage drop over here, which will again be V, and C equivalent will simply equal C1 plus C2. Okay, and that's it. That's all there is to it. So parallel capacitors add up. You just simply add them. And this makes sense too, because if you think of it, we've kind of done it this way. But another way to think of it is just geometrically. We've just got this capacitor. It's a couple parallel plates. We got a distance. We got a dielectric material. And then over here, we just hook up another capacitor to the power supply. The first capacitor doesn't know something else is hooked up. And we've just added more surface area, more parallel plates with their distance and with their dielectric, and the capacitors simply add up. Okay, so that is parallel capacitors. All right, and that's how they add up. Okay, so now let's look at series capacitors and see what they do. All right, so let's go back here for a quick look and see what we're talking about here. So looking at the figure here, we've got C1, C2, C3. We've got some collection of N capacitors, and we put them in series. And we're saying that we want to know what the equivalent capacitance is, C equivalent, if we were just to model this entire thing as just one capacitor. It turns out that 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over Cn. What does this remind you of? Well, that's the equation for parallel resistors, right? Parallel resistors add this way. And also we're going to see that because capacitors and inductors are analogs of each other, so the way that a parallel capacitor adds up is the same as a series inductor. And a parallel inductor will be the same as a series capacitor. The formulas will be the same. All right, so even though we know the solution is this, right, let's see if we can derive this. Okay, so let's see if we can derive this. All right, what the equation is for series. This is actually much more complicated. All right, so let's go to our drawing program and let's derive series capacitance and how this adds up. All right. Okay. All right, so first thing, let's write down some things that we know. Okay, let's write down some things that we know. So let's write down Q equals C times V. So charge equals capacitance times voltage. All right, and we've seen this before. All right, and then what I'd like to do is I'd like to show you a couple things that can be derived from this real quick, just so we have them. All right, now so what's charge? Charge is in coulombs, capacitance is in farads, and voltage is in volts. All right, so we've got coulombs, and it's really easy to get confused here. So let me write these real quick. So this goes down, and these are coulombs, right? And these are in farads, right? And this, of course, is in volts. Okay, so coulombs, farads, volts. but C looks like it might be coulombs, but it's not, right? C is farads because it's capacitance. Q is charge in coulombs, all right? So anyway, it's like working at a big corporation, just acronyms, and you get all confused. All right, so Q equals C times V. All right, so let's take a look at that real quick, and I just want to do something here and just show you something. So Q equals C times V. Let's take the derivative of both sides with respect to time. All right, and again, if you don't know calculus, all we really want to do is we just want to look at the rate change of charge with respect to time, and the rate change of voltage with respect to time. That's what a derivative is. So it's kind of looking at looking at the slope, or how these things change as a function of time. So that's all derivative means, is how it changes as a function of time. So we can take the derivative of both sides, and when we do that, we get dq dt equals c dv dt. Nothing happens to c because it's a constant. Now, so what's interesting about this is dq dt. What is dq dt? Well, that's just current, right? So this is charge per unit time. So coulomb per second is amperes, so that's current. Aha. So that is simply current. And so this is where we get that equation, I equals C dV dt. All right, and so again, you can play around with all these, and it's just like, Ohm's law, right? And we'll just put a little Ohm's law over here. Let's see, what's Ohm's law color? I don't know. So here's Ohm's law again. All right, and so that's just V equals I times R. Right, and we manipulate this around to get things that we want. All right, so again, we can just kind of use these different formulas, and we kind of want to remember them. So you definitely want to remember this capacitor equation right here, and then, probably a good idea to remember this one too. That one, and then of course you need to remember Ohm's law. Okay, now let's go back and let's see if we can derive series capacitance, what the equivalent is. So what we're looking to do is this. So let's take a look here. So what we're looking to do is, and let's just do a simplified version just with two capacitors. So we're looking to do this. So say we have a voltage source, plus to minus. We've got one capacitor. We've got two capacitors. Okay, I'm going to call this one C1. I'm going to call this one C2. All right, and what we're looking to do is we're looking to say, can we simplify this so that it looks like one capacitor from the point of view, again, if we open this up and draw a dotted line here, right, and then we were to look inside, there's our little eyeball looking inside, and now, so we could look at these two nodes right here, for example, and we could just say we're like detaching those two nodes and then attaching them over here. The voltage stays the same. We want to know what C equivalent is, right? And we already know that it's basically going to be, we already know the answer is, it's like they're parallel resistors, the same kind of formula. So it's C1 times C2 over C1 plus C2. But let's see if we can derive that. Okay. All right. So first thing is, just let me kind of redraw this thing here on the left a little bit. Let me just redraw that. It's a little bit messy, and hopefully I'll have enough room to do this. But and again, I like to do everything in real time. I don't like PowerPoints. I don't like faking things and memorizing things. So, and probably I'm going to edit some things out to make this stuff go a little smoother when I'm bobbling all over the place, right, and trying to figure things out. But I think it's just more honest if we kind of just do this stuff together and figure things out, and kind of so you can see the thought process. All right, so here's our circuit right here, and we've got our voltage source. So let's call this, let's just call this, for now, let's call this V. I don't know if I'm going to like that in 5 minutes, but we'll find out. All right, and we've got our two capacitors here, so easy enough. So let's use some different colors here. So how about, let's do this. We'll call this one C1, and we'll call this one C2. And that's a horrible 2. Okay, and then let's also say that we're gonna have V1 here, and we're gonna have V2 here. All right, and they're definitely going to drop plus to minus. We know that much at least. Okay. All right, so now let's just make some kind of assumptions here. So again, when we show this circuit, we instantaneously construct it. In other words, there's really always kind of a switch here. There's always a switch here, right? And we turn that switch on at t equals 0, at time equals 0, right? But you know, I usually assume that it's like instantaneously the circuit appears, you know, like from a teleporter. All right, but we have a switch at t equals 0. We close the switch, and then what happens? So the capacitors will start charging. All right, and so we've got an inrush of current. Remember, we talked about that inrush current and how great that can be, how large it can be. And then after a while, the current is going to stop because these capacitors are going to charge. All right, so now let's just pretend we're capacitors. So the top one is going to charge plus up here. All right, the bottom one is going to charge plus up here. And then the bottom plate is going to charge minus in each one. Okay, so now here is kind of where the interesting things start happening. So once this thing charges and the current stops, let's take a look at the node in the middle here. All right, and so this is kind of cool. All right, and we're just going to call this, I'll just call this VM for voltage middle. All right, so notice this. This is a wire right here. This is a wire connecting these two plates, right? Since it's a wire, it's got zero resistance and infinite conductivity. That means there can be no voltage drop over the wire. So whatever the voltage is at one side here has to be the same voltage at the other side. If that's true, then that charge must be the same. So if it wasn't true, we'd have a potential difference, right? And we'd have a current flow, but we don't. So the negative charge here must equal the positive charge here. So the plate charge on this plate here is the same as this charge here, just equal but opposite in sign. Now, if those are equal, so those two are equal, right? Those two are equal. And so let's just take the top capacitor. So whatever this charge is here, the top charge on this positive plate must be equal to that because that's what a capacitor does. It charges equally, right? The top and bottom plate. All right, same thing with this capacitor. Whatever the charge is here must have equaled out here because as positive charges went on one plate, negative charges had to go on the other plate. Let's repeat. Once these two capacitors charge up, the center voltage is the same. Now it's not zero, right? It's a voltage. It's not zero, but it's the same. Even though there's negative charge here and positive charge here, the voltage is the same, right? But the charge must be equal but opposite, all right? Because it's at equilibrium. All right, so the whole point is that the charge on C1 must be equal to the charge on C2. The charge on C1 must be equal to the charge on C2, all right? So, so we could say little arrows here. So we could say Q1 must equal Q2. I can't make 2's to save my life with this tablet. Okay, Q1 equals Q2. All right, now, so Q1 equals Q2. So now what we want to do is we need to relate charge, voltage, and capacitance back to the source here so that we can figure out what the equivalent capacitance is. We're almost there. Now, what do we have that has charge, capacitance, and voltage? Aha, this thing right here. So this is going to help us out. All right, so now what we're looking for is this thing over here. All right, so this circuit over here is what we're looking for. So we want some C equivalent, and the C equivalent, and I'm going to call this, let me call this the charge on this. I don't want to get, let's call it, yeah, I guess we can call it Q equivalent. All right, Q equivalent is the charge on this. So there's a charge Q equivalent on this, right? And it would be plus, 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 and it would be minus, 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 right? Like that. Okay, so now we're getting very close. We've almost got this. Do we have the right color there? Yeah. Okay, so now let's see if we can write out some equations here that say what's going on here. Okay, so let's start here. Get some room here. All right, and so what's one thing we can write? Well, let's use Kirchhoff's voltage law. So we could start here, right? and we could say that this is a voltage rise and these are voltage drops, and we could sum those up and they equal 0. Or we could do it a little bit quicker, and we could say that V equals V1 plus V2, right? I think we can do that now. V equals V1 plus V2. I think you're comfortable with that, right? Okay, so we've got V equals V1 plus V2. All right, and now what can we do here? So let's see what we got. What do we got? We got Q equals C times V. So how about, can I just put C over here? Can I divide both by C, and then I get V equals Q over C. So I get V equals Q over C. So we're going to take this here, and let's just write one other thing here. So we've got Q equals C times V, right? Therefore, that also means that V must equal Q over C, right? Just moving things around, just like we do with Ohm's law. Okay, so let's use this right here. All right, so we've got V equals V1, so that's going to be Q1 over C, which is just C1, plus Q2 over C2. Okay, so far so good. All right, and now what's this V right here, right? Well, we can write this one also. This is also equivalent to V is never changing. This is the V of the power supply, so that's always V. So that's never changing. So that is going to, over here, this is this Q equivalent. All right, so this is Q equivalent over C equivalent. Okay? Okay, now, oh boy, those Q's, are you kidding me? All right, let's do that again. Q equivalent, no, that's better, over C equivalent. All right, we're getting there, we're almost there, we've almost got it. And I'm sure, you know what, I go really slow because I just want to make sure everyone gets it, but I'm sure all the mathematicians are way ahead of me here and have already figured this out about an hour ago. Okay, all right, so now we've got this right here, and now we're gonna bring this thing home. So let's look at just this part of it here. And so we've got, now take a look what we got here. We've got our resistor formula, our parallel resistor formula, which is what we're saying that series capacitance ends up being. We've got something C1, we've got something over C2, and we've got something over C equivalent. If we could just do something with these things up in the numerator, but we can. Well, Q1 equals Q2. Q1 equals Q2, so these two things are equal, right? However, this is the final gotcha. The Q equivalent also has to equal Q1 and Q2, because from the point of view of when we're looking into this circuit, the charge on each one of these capacitors has to be the same, and it has to be the same as the equivalent charge. In other words, all the numerators are the same. All right, so if they're all the same, we can cancel those out. And then what we end up with is 1 over C equivalent equals 1 over C1 plus 1 over C2. All right, so that is the series combination of capacitors. So that's it. So you basically you add them up like you would do parallel resistors. So you got to do 1 over the inverse. And then if you simplify this, this equals what? C1, so the product over the sum, C1 plus C2, right? That's also equal to C equivalent, okay? All right, so that's it. So that's those two cases right there. And then, you know, the most important thing, you're never going to have to do this. And honestly, in all, you know, rarely, if never, do you ever put capacitors in series. I mean, never. If you need capacitors in series, you would buy the equivalent capacitor, right? So now capacitors could end up in series because one block might connect to another block. That's a possibility. Then you'd want to figure out what's going on. And the same thing with parallel capacitors. However, parallel capacitors do happen a lot, and let me show you why. That's actually important. So let's continue on discussing this a little bit. we're gonna, and again, like I said, I like to kind of show things before we know things, because a lot of times it's an opportunity and we're just not going to be able to go back there. So say, for example, so what I'm saying is rarely are you going to put capacitors in series, uh, in one sub-block of a circuit. If you've got one block connecting to another block, for example, you might have one block in a circuit and there might be an output capacitor here, all right, and that's one block. And then now you might have another block of a circuit, and it might have, its capacitor here as well, right? So you might have this C1, you might have this C2, and then, you're going to connect these things together. That's really the only time that capacitors get connected together in series. If you need, a capacitor, never, ever, ever, ever in my entire life have I said, I need a 20 microfarad capacitor, so why don't I take a 30 microfarad and a 18 microfarad and put them in series, and then I'll get what I want. Never, never, never. You just don't do it. All right. But this case down here does happen a lot. So when you put blocks together, so it is important to kind of know how these might add up. However, on the other hand, we don't really, when we start talking about electronics and signals at this level, we don't even talk about the time domain anymore. We talk about the frequency domain. And what we talk about, and again, I'm getting ahead of myself, but I like to do that so that we can kind of know different things that we don't know. We talk about, we got a signal coming in here, and this does some processing to it, and then we want to take that signal and we will put it into this block, and this thing's going to do some processing, process one, process two, and these capacitors are kind of coupling capacitors to take the signal out and then to get the signal back in. So we look at these capacitors, and then we look at the resistances and impedances in both of these blocks, and we figure out what their frequency responses or their filtering properties. And then, so as we do this, maybe this creates a filter here, and only certain frequencies get through, and then same thing, only certain frequencies get through here. So typically when we're building systems, we think in terms of frequencies and signals. We don't think in terms of transient responses and things charging and discharging, right? Because they're charging and discharging millions or hundreds of thousands or trillions of times a second, so we kind of don't do that. We just think in terms of signals. All right, but that said, let's get back to this example. All right, so up here, what I want to show you is this. So say we have capacitor 1, and let's say that this has some value. So say this capacitor has, let's say 0.01 microfarad. All right, and all right, and so now let's say that this thing is connected right here, and let's say that some noise comes down here. Some noise comes down this line. All right, now capacitors, they like to pass AC, right? They have low impedance to AC signals. So this noise just goes right down here to ground, right? All right, and then, on its merry way is the signal with, less noise, right? And that's good. And so now if we had something downstream here that needed some processing, this capacitor takes some of that noise, will go down there. Why? Because this is a lower resistance path for that noise. But now there might be different bands of the noise, and the one capacitor only gets the job done for one band of frequencies, right? And we're going to learn this when we talk about filters coming soon in probably 2 more lectures. But so what we might want to do is add another capacitor, all right, and like this, and this C2, and maybe this is a 10 microfarad, all right, or maybe it's 1 microfarad. The point is that we have different bands of frequencies here, and so let's say, and here's some blue stuff, right, and let's say that, here's some lower frequencies, and we got the high frequencies here, but the low frequencies kind of made it through. But then guess what? The low frequencies go through here, and now what we're left with is we still got our little bit of noise left there, and then we got our lower frequencies got attenuated also here because they went down like this. This is when you'll start to see capacitors in parallel, all right, for filtering. So what we're looking for here is, here's the interesting thing. You can figure out what the equivalent capacitance is, right? So C equivalent equals what? Just C1 plus C2, right? capacitors in parallel, just add up in series. We're not looking for this. We're looking for something different. So even though the equivalent capacitance is this, because there's two capacitors, there's two paths to ground. So we're going to get two different kind of currents going through here and two different capacitor actions going on and two different filtering systems going on. And what's really happening is we've got kind of two filters here, and the signals are going to go to ground here. So this noise, if that's what we want, will get grounded. And then whatever goes this way will be much less. So a lot of times on power supply designs or power, to chips or this or that, you'll see they say, add a 0.1 or 0.01 microfarad across the power and a 1 or 10 microfarad or more also in parallel, and even something else. Sometimes, you might have 3 or 4 different values. Now, on a microcontroller or a big microprocessor, there are dozens, if not hundreds, of these filtering capacitors on all the power leads, so that every single power lead going into that processor or microcontroller has its power filtered. And then also we'll add inductors later. When we learned about inductors, we'll add inductors into these things as well, and then those also filter out high frequencies as well. So anyway, that's why you might use capacitors in parallel. Typically, you just, if you need a value, just go buy it. You don't put capacitors in parallel to find the value, but if you need the action of the two capacitors in parallel, that's when you would use them. Again, same thing here. If you need the action of two capacitors in series to couple two parts of the circuit and insulate them as you interface them, that's when you would use them in series. But you surely wouldn't say, hey, I need a so-and-so capacitor. I can put these two in series or these two in parallel. You could do it, right? But you would just never do it. All right. So anyway, so that's it. So I think we're good right now. Let's stop here, and then we're going to go into the next lecture, and we're going to talk about charging and discharging of capacitors. And if we get time, we'll start into filters, but maybe we'll break that up into a couple lectures. We'll see what happens. All right. So go ahead and stop, and I will see you in the next lecture. Bye. All right, welcome back, and we are on the next lecture. We are going to be talking about RC circuits. We're going to talk about charging and discharging. And then if we get time, we'll go into low pass and high pass filters, but I think we'll save that for another lecture just to break this up a little bit. All right, so looking on your screen, you're looking at the notes for this lecture, which is still out of this is out of chapter 3 of my book. And right away you can see there's a bit of math down here, a little bit of calculus. Again, this is not a math class, and I don't want to go into this stuff too deeply, but I just want to show it to you just one time, kind of in general, just so you kind of know what's going on and know what you need to do to solve these things if you ever wanted to, and kind of where the formulas come from. So, just as a little, side note here, when you're learning electronics or just anything really, electronics or physics, chemistry, you memorize so many equations and formulas. And if you've never derived them or never understand them, it's just like you've just memorized so many things, and then they're really easy to, unmemorize, right, and forget. So it's nice to kind of derive things a little bit, or at least understand where they come from, so that you could, if given the time and the proper resources, you could derive it, or you kind of know where things come from. So I kind of like to know where things come from and their fundamentals, even if I forget about it. And there was a time, I'm sure, that you learned something that you've completely forgotten. I'm the same way, but at least you learned it once, and it's someplace in there in your brain. If you ever need it, you can kind of go back to it. Electronics is the same way. There's so many formulas, especially when you get into more complicated things like RF theory and that kind of stuff. You just cannot you memorize all these things, and if you don't understand them, it's just like a mishmash. Anyway, so we're going to talk about two really kind of interesting and kind of fun. Once you kind of get the hang of these things, it's actually kind of fun playing with it, because they do exactly what the math says they should do, which is kind of what things do. But in electronics, it's kind of hard to get things to work that way when you're on the bench, because there's so many variables. Anyway, so what we're going to talk about, and what the global plan here is, we're going to talk about charging and discharging of capacitors. And then we're going to talk about low pass, high pass filters, maybe in another lecture. And then we're going to talk about inductors. Again, we're going to talk about energizing and de-energizing. I don't like the word charging because they don't really charge, they energize. And then we're probably going to start talking about phasors and complex impedance. And then we'll go into some more semiconductor stuff. So the whole idea is we got to learn this stuff at least once so we kind of understand what's going on. All right, so we learned that capacitors store charge, and we learned that once they're charged up, there's charge on their plates, and it'll stay there until they're discharged through some kind of load. And so as capacitors are charging and discharging, this is kind of a transient response. They're changing over time, rapidly, transiently, and we want to understand, how that happens and kind of the math behind it. And the reason why that'll let us understand what's happening when we start kind of moving things to a digital domain, and we have clock signals that are square waves, and we'll see these square waves are not square waves. They start bending and deforming. But the reason why is because of capacitance and inductance. And then we'll know why based on our knowledge of transient analysis. So again, you're never, ever probably going to use these formulas when you're designing something. You'll use the final formula sometimes, but you'll never have to derive anything. But it's just nice to know how. And all of these things we've kind of talked about before. All right, so let's get started. So again, you've got these notes and you can go through them slowly and look at other resources, but I just want to go through these things and kind of see what we see here. So, all right, so let's see. All right, Control-Shift-6, that erases this little highlighter. All right, so looking at the screen right now, we're going to talk about the circuit that you see right here. All right, and so this is a kind of a representation of something we would use to be able to kind of charge up a capacitor and then discharge a capacitor, and then kind of look at what's going on. So what you see here is we've got a voltage source, an input VI, and this could actually be a function of time, but right now we're just going to say it's a steady voltage of some value, 5, 6, 9, 12 volts, whatever. All right, and at time right before 0, this switch is in neither position you could think of. Maybe it's just straight up, so it's not connected to either thing. So the capacitor has no charge on it, just sitting there, just waiting for something to happen. All right, so like maybe at time 0, what we do is now we switch the switch here to position 1, and then what's going to happen is we're going to get a current, like that, right? And so what's happening then is we've kind of got this circuit down here in B. The battery or voltage source, the current source, is going to start charging the capacitor through the resistor, and at some time in the future it's going to stop charging. So remember, what's going to happen is there's going to be an initial rush of current, and then this current's going to decrease as the charge accumulates on the plates, and then at some point it's going to stop. We want to know what that looks like, right? We want to know what is the math behind that exactly so that we can write things down and do computations. Okay, so that's one case. Now the other case is over here in figure C. And in that case, now, so the capacitor is charged now. And so now imagine that instantaneously we, flip the switch and we move it over to this position. So now the capacitor, which is charged plus to minus, is going to discharge through the resistor. All right. Now our question is, what does that look like? All right. So that's discharging, and that's C. So B is charging, C is discharging. All right. So those are the cases that we're kind of interested in here, and we want to kind of mathematically model what's going on here. All right. So what I want to do here is we're gonna kind of we are gonna skip this case for right now, and so this is the charging case. We're going to skip this for right now, and we're going to jump to the discharging case, and we're going to kind of work through this because it's a little bit simpler. And then we'll come back to the charging case and then kind of look at what's going on right here. All right. So let's actually go through and look at this this discharging case. All right, and kind of see if we can kind of figure out what this looks like. All right. So let's go ahead and do that. So let's go to our drawing program here. Okay. All right. So let's get a good color here. So get a good color. How about, we always like green, or I do at least. It's nice and bright. Okay, so, and again, this is not a math class, and but we just can't avoid some of these things. We got to do them. Okay, so what we had was, we had a voltage source, right, which could be a battery or something. It's just a static source in this case. It's not changing. And then we had a resistor, and then we had a capacitor, like this. All right, and then we assume that for a very long time this has been on, very long seconds, minutes, hours, whatever is necessary to completely charge the capacitor. So when this thing turned on, there was an initial current, I that went around like this and charged this thing up, and then the capacitor charged up with plus on this side and minus on this side, completely charged, and then there was a voltage developed here, right? So there was a voltage plus to minus developed here. And then there was also a voltage drop, we'll call it VR over here. And then this voltage source, we're kind of calling it VI. So sometimes you'll see VI for V input, or you'll just see it V, or you'll see it VS. All these things are just ways to label these things. All right, so for a very long time, so this is all charged up, and now our capacitor is charged. Now let's imagine that we get rid of this power source here, we short it, and then we let the circuit discharge, okay? So now that's what we're going to do. We're going to discharge the circuit. So now we've got this scenario here where we've got our circuit, and we've got our resistor, and we've got our capacitor again. And I hope I have enough room to do the math. We'll see. All right, we've got R, we've got C, and so now we've still got all the positive charge here. We've got negative charge here. All right, and let's use a couple different colors here. And we'll say that this is, we'll say that we've got a current here. So now it's going to discharge. So the current was going in this direction, in this clockwise direction. Now the current is going to go counterclockwise, right? Because the capacitor is going to discharge. All right, so the capacitor is going to discharge. There's no more battery or source in here. This is what's happening. So we've got this right here. Okay, now the voltage on the capacitor, right? So we could call this, let's just call this, we can call this V, right? And let's put a little node right there. Okay, and then now as this current flows, and we can call this current I, let's call this current I, there's going to be a voltage drop over the resistor, right? Because there's a current, and it's going to drop plus to minus, right? Because the current is going, in this direction, right? Plus to minus, all right? And we could call that if we want, we could call that VR, all right? Okay, so now we kind of have everything. Now, what do we know here? And of course, this is, plus and minus. Remember, the current is going to, go this way. It's going to go counterclockwise now. So it charges up clockwise, and then it discharges counterclockwise. And we're assuming it already charged. That has its modeling equation, but now we're going to do the discharge because it's a little bit easier. All right, so at this point, we've got everything, we're ready to go, and now, so let's start writing some things down. So let's write down some stuff so that we have it, again, so we don't have to wiggle around and try and remember things. All right, so how about, one thing is V equals I times R, right? So that's Ohm's law. All right, and then the other thing is we know that I in a capacitor equals C dV dt. So this is the general equation. This is just one of them. And what's I? That's really dq dt, right? So we could do this in terms of charge if we wanted to, but I like to do things in terms of current. I mean, no one ever works in charge, ever, ever, ever in a million billion years, unless you're doing a physics class or an electrical engineering class. Then you'll do things with charge. But electrical engineers and embedded engineers, the only two quantities are I and V, and then resistance, capacitance, inductance, and all that. But I and V, we don't use charge, so that's kind of silly. All right, so I equals C dV dt. So let's see, can we write some kind of equation to constrain what's going on here and then start solving for it, all right? Okay, so the current coming out of the capacitor is C dV dt, all right? So C dV dt, okay, that's the current going out of the capacitor. And but there's one little detail. I'll get to it in a second. Now, what is the current going through the resistor? Well, I already know what the voltage is. The voltage is this V, the capacitor's voltage, and that's going to be divided by R. So it's simply just V over R. That's it. There's nothing more. V over R. Okay, now there's one little detail here. One little detail that we need to add. So this modeling equation, I equals C dV dt, notice that the current is flowing in this direction and it's flowing down. When that's happening, I equals C dV dt. So if the current is going from plus to minus, I equals C dV dt. But in this case, wait a minute, the current is going up. Even though the charge is in the same place, now current's going to flow back out of this thing. So the currents can't be C dV dt anymore, right? In this particular case, it's got to be minus. There's got to be a minus sign here. All right, we got to flip that. Got to be very careful with that. All right, so we have to take this general equation and consider it in both of these cases. So now this is what we have. So we have this right here. All right, so we've got that right there, and this is what we need to solve for here. Okay. All right, so let me just bring this over here. Let's get a brighter color. All right, so let's bring this over here. So we have minus C dV dt equals V over R. Okay, so this is a differential equation. And so all that means is we've got some function. Now V really means V of t, right? So this is really V of t. It's a function of time, right? V of t. But we're just calling it V right now, so we don't have to write a bunch of sub t's. But it's a function of time. So this is a differential equation. What a differential equation means is that we've got the variable v, which is a function of time, and then we have its derivative. And what the derivative as a function of time means, its slope. So what this says in English is v over r equals, so the function over r divided by r equals the derivative of the function with respect to time times minus c. That's it. It just says they're equal. But what's the derivative? That just means the slope. So it just means the slope. So here's an interesting thing. The function with some constant divider equals itself, right? But the slope of itself with respect to time times some other constant. Okay, so let's simplify this a little bit so that we can kind of see things a little bit better. So let's see here. How about dv dt equals 1 over minus rc times v. All right. So okay, so that's it right there. Okay, so we've got this this function v, and whatever that is, its derivative with respect to time equals 1 over minus rc times v. So this is a differential equation, and if you've done this in school, you know, you get this. If you haven't, this looks kind of circular. It's kind of like the derivative of the function with respect to time equals some constant times the function. That seems kind of impossible, whatever this derivative is, but it really just means the slope of the function equals some constant times the function. There are functions that'll do this, all right? And so, now, when you learn differential equations, you learn different kinds of solutions to these things. You can derive them, but basically you learn that certain classes of functions have certain kinds of general solutions, and the solution for this, I'll tell you, looks like this. So v equals some constant e to the minus t over, and I'm going to use this thing called tau right here, all right? So v equals ae minus e to the minus t over tau. And so this is e, which is just the constant, the mathematical constant e, 2.7 and some change. And that's it. So now if I take the derivative of this right here, so the interesting thing of this function right here, so again, you don't even need to know calculus. So let me show you something real quick, just real quick. Let's say if we have a function of x and the function equals ax to the n, all right? So if we want the derivative of this, say if we wanted df of x with respect to x, so the derivative of this, if you have just a simple polynomial like this, a constant, a variable to the power, is simply the power, you bring it down here, excuse me, You bring the power down here, n, and then times the a, and then x, and then now n minus 1. So that's it. So if someone were to say, hey, what's the derivative of 3x to the fourth, right? What's the derivative of that? If someone said, what's, ddx of 3x to the fourth, you would say, okay, it's 4 times 3, that's 12, x to the 4 minus 1, 3. That's it. That's it. It's not magic. It's just a mathematical function which computes the slope. All right. So this function right here, though, has an interesting property. The exponential function has an interesting property that when you take the derivative, you get the function back just simply with this out in front of it. All right. So in other words, exactly what we want is we want the derivative of something equals the something just with something out in front of it. And that's exactly what this exponential function, when you take the derivative, does. Google it, look up derivative exponential function. You'll see what I mean. All right. So the result is in this form right here. And what we want is we know this. Okay, so now what we want to do is we need to solve for these constants because we're looking for v. We're not looking for dv dt, we're looking for v. So we know that it's of this form. Okay, so what are some things that we do know? Well, we do know at time t equals 0, v equals like its initial condition. And that was the initial charge on it from whenever it was charged up. All right, so that's the same as, so we could say at time equals 0, right? Right when this thing starts off, the charge on it, v, is simply v sub 0, right? That's whatever the initial charge is on the capacitor, all right? So v sub 0. So if it's okay, I'm just going to call that v sub 0, like the initial charge. Okay. And that initial charge, what's that really? That's really going to be this V sub I. Because remember, when this thing gets done charging up, we don't know how exactly it charges up. It does some function. When it's done, it's going to charge to whatever that voltage is. So it's kind of like that V sub I. But we'll just leave it as V sub 0 right now. Okay, so V sub 0 equals A, which is some constant, and then E to the minus at time t equals 0, 0 over tau, right? Which is, this is just e to the 0. Anything to the 0, right, is 1. So this is v sub 0 equals a. All right, so a equals v sub 0. Okay, so this thing here, this guy, is v sub 0. All right, so now we're getting there. So now we know that v equals v sub 0 e to the minus t over tau. Okay, so we're getting someplace now. This tau, how are we going to get this? Okay, so we need to solve for this right now. All right, so let's look back at what we have. So we have that the derivative of our function with respect to time equals 1 over minus RC times V. All right, so can we use this to try and find this tau somehow? All right, so that's what we're going to do right now. So let's do that. Okay, so let's see here. All right, so our function, we can go back with this right here. All right, so this says that the derivative of v with respect to time. So here's our v. So we want the derivative of v with respect to time. So I'm going to differentiate this. So here we go. So let's put v down here equals, and we could put the a there, or we could put the v0. Want to put the v0 since we already figured it out? Why not? Okay. Okay, so now what I need to do is I need to differentiate this thing. All right, so I'm going to differentiate both sides of it. All right, so I'm going to differentiate dv dt equals, all right, and when I'm done, this equation says it's going to be 1 over minus RC times v. All right, so here we go. And so let's differentiate this right here. And when we differentiate this, we're going to get simply this term right here looks kind of messy, but it's just minus 1 over tau. All right. So we're going to get equals v0, and we'll just parenthesize that, minus 1 over tau. Oops. All right. And then we just get this back again, which is just e to the minus t over tau. All right. And so the derivative of this function equals 1 over minus RC times V. This is the derivative of the function. It equals this thing right here. So this has to equal this. So it has to equal 1 over minus RC times V. Now, where is V? V is just this thing right here. So we're looking for V naught e to the minus t over tau. There it is, V naught e to the minus t over tau, right? So now what we can say is V is right back here, right? So it's V naught, V naught. We can leave it like this if we want. We can leave it like this if we want, but let's just go ahead and fill it in. So V naught, and then e to the minus t over tau. Okay, so now if we look at both sides of this, right? So here's the V naught, here's the V naught, here's this e to the minus t over tau. So we can cancel this out with this. We can cancel out V naught with V naught. And then we're left with this right here. And I hope you can see this. I hope the little thing screen over here is not covering it. Anyway, so now we have that 1 over tau equals minus 1 over tau equals 1 over minus RC. So we can get rid of that, we can get rid of that, we can invert it. Tau must equal RC, okay? So tau must equal RC, thank goodness. So that's it. So now finally, if we can find a place to write this, our final equation is V as a function of time equals whatever the initial voltage on the capacitor was when it was charged. We can call that V0, or we can call it V sub 0, e to the minus t over RC. So that's it. So that is the equation that describes what the discharging will look like mathematically. And I know it's just, what a mess, huh? Brutal. And this is the easy way to do it. There's a harder way to do it, which is even more messy. So, but again, once you remember this, it's pretty easy. So this RC is called the time constant. All right, and so I want to talk about some more stuff about that. Let's go back to the notes now, and I want to show you some stuff inside of the notes. So let's go back to the notes. All right, so and again, we're gonna go back to the other case in a second. So let me scroll through this. All right, and okay, so I want you to look at this right here. Let me zoom into this here a little bit. Okay. All right, so this is kind of what we just figured out, right? We just kind of solved this situation here. And this is what the discharge curve looks like. So it's exponential, and basically V equals the initial charge on the capacitor times e to the minus t over RC. So RC is its time constant. All right, and so this is what it looks like. Now, the time constant RC is going to be in both charging and discharging, and this is going to come up in many, many places. In any kind of RC circuit, you're going to see this RC in a lot of places, and this is why it's called tau, all right? And it's going to come up all over the place when we do filters and all that, all right? So now, this is the easy case. So this is when the capacitor discharges. All right, let's look at now when the capacitor charges. So let's go back up and into the notes here, and I want you to see this figure in a second. We're going to talk about that in a minute. All right, but I want to talk about the, I want to talk about this right here, this figure right up here. Okay. All right, so again, in the charging, we make this connection, and we've got an RC circuit, and the capacitor is going to charge. Now, this is the math. If you run through this and you solve this, and this is a little bit more complex because it's not just constant times the exponential, there's a constant plus a constant times the exponential. But when you do all the solutions, then you find this. So here is the charging. So V equals VI times 1 minus e to the minus t over RC. All right. So I don't expect you to memorize that right now, but keep that in your mind for a second. And what I want to do is I want to go to our drawing program, and let's take a look at what's going on here a little bit. All right, so, oops. All right, so let's first let's pick a color here. Okay, So let's do our RC discharging here, right? So we've got, RC discharging. All right, and we know that that looks something like this. All right, we've got some initial voltage, we're going to call it VI, right? And it's going to discharge like this, okay? And so this right here, this axis is voltage, and this axis, of course, here is time t. All right, and the thing that models this is, and then this curve right here is v as a function of time equals, what does it equal? It equals vi times e to the minus t over tau, or which is, RC. Okay, so that is discharging. All right, now charging. So now RC charging. And the only reason we did these backwards is because it's a lot easier to do the discharging math. RC charging looks like this. Looks like this. So it looks like down here again, this is time t, and this is voltage here, voltage V. All right, and again, this is 0 in both axes. Okay, so RC charging looks like this. And we have this exponential curve that gets asymptotic, and that is, okay, that's horrible. Let me do that again. Okay. All right. And so this curve is asymptotic, is the term, and what that means is it never, ever, 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 ever reaches this in reality, except at infinity, right? But it gets closer and closer and closer and closer. And what is that point that it gets up to? Well, that's just VI, right? That's that initial voltage that it's going to charge up to, and then it's going to discharge. So what do we have here? And actually, the charging curve, we can just put the discharging curve right on it. So if we charge the thing up and then we discharge it, right, it's going to look like this, and then discharge, right? So it's going to charge and then discharge. Okay, so that's the charging, and then what does that look like mathematically? So that looks like V sub t equals, and this one's a little bit, it's really not that hard if you think about it. It's V sub I times 1 minus e to the minus t over RC. All right, so they're very, very similar. They're very, very similar. They're just kind of analogs of each other. In one case, you're discharging, and then this, when you memorize these, sometimes it's hard. You kind of think this one kind of feels like a discharging because there's a minus in here. Well, let's see what happens. So at t equals 0, what does this one look like? At t equals 0, this term, the exponential, is e to the 0, so it's 1. So at t equals 0, we have vi, all right? So is that right? So here's t equals 0 here, right? And sure enough, we have vi. That's the initial voltage. That's the battery or the whatever's charging it up. Okay. At t equals 0 here, let's see if this is right. So this term right here, when t equals 0, this goes to 0. So e to the 0 is 1. 1 minus 1 is 0. 0 times vi is 0. So at t equals 0, which is right here, right? Again, we have a voltage of 0 volts. So that makes sense. Now let's imagine that t goes to infinity. All right. So let's do that for a second, if that's okay. So let's do t goes to infinity. So as t goes to infinity, what does this really look like right here? So what it really looks like is this. So this is equals vi, and then 1 minus e. All right. So this is e to the minus t over RC, right? So let's just for a second, let's pretend that RC equals 1, all right? And the product equals 1. It's not going to matter at infinity, right? Because infinity is going to be bigger or small, 1 over infinity will be smaller than anything. So let's just pretend RC is 1. So if RC equals 1, so when RC equals 1, just to make this easier, we have 1 minus e to the minus t, okay? All right. But what is that really, right? So that's really 1 minus 1 over e to the t, okay, right? Anything to a negative power is just 1 over that to the positive power. Okay, so as t keeps getting larger and larger, right, e to that gets larger and larger and larger, and as it gets larger and larger and larger, 100, a million, a billion, a trillion, a quadrillion, a septillion, and on and on and on, this term goes to 0, right? So this is going to 0. As this term goes to 0, what do we get? Well, we just get this 1 here times VI. We get 1 minus 0, so we just get 1 times VI. So at infinity, and here's time moving towards infinity, and so see this over here, this is kind of, moving towards infinity here. As we go towards infinity, then the voltage, V of t, goes to V sub I, and sure enough it does. Asymptotically though, because it can never reach it until it reaches infinity. So that's it. But now here's the other thing that I wanted to bring your attention to. So I want to find over here a figure that kind of shows this for you. And let's see if I can find it, then I'll move it over here. I want to show you. So we talked about that RC time constant, right? And that's going to show up everywhere. All right. Take a look at this right here. So in this figure right here, you see this is a charging. And as we're charging, if you do the math, if you let t equal RC, in other words, if the time that you allow this thing to charge equals R times C, so you would get minus R times C over R times C. That would just be minus 1. So you would get 1 over e to the 1, right? And so if you got 1 over e to the 1, let's do the math. So 1 over e to the 1, so let's just do e to the 1. So we'll do shift e to the 1, which will just be 2.7 and some change, right? Okay, and now if we invert that, right? If we invert that, we get 0.36. 1 minus 0.36, right? Minus 1 is, 1 minus 0.36, right? 1 minus 0.36 is approximately 0.64. So it's about 63% actually. So the whole point is that when the time equals 1 RC time, when the time t equals 1 tau or 1 RC, you're already going to be charged to 63% of the total value, because this term here turns into 0.63. All right. So because there's an exponential here, this term very, very quickly diminishes, and because it's a 1 over term, right? Because it's to a negative power, it diminishes very quickly. And as it diminishes very quickly, this whole thing goes to 0, and then this goes to 1. So in about 1, 2, 3, 4, 5 RC times, in about 5 RC times, you're practically 99.999% charged up. And that's kind of what this is showing. So here's t equals RC, or t equals tau. At 5 RC times, and this is this little tip right here, at 5 RC times, for all practical purposes, the capacitor is charged or it's discharged. All right, so 5 RC times. And then if you were to plug in and do the math here, which we can do, so let's actually go to the let's go back to the board, and let's take a look at that. So let's see if we let something charge up for 5 RC times, what will it be charged? All right, and then let's actually do this with a circuit. All right, just to make this more interesting. Okay. Okay, so let's do a charging circuit. All right, so here we go. Let's do a charging circuit. So let's say that we have a battery. All right, and we have a resistor. And let's make this 1K. And let's make this capacitor. And this is R, and this is C. And let's make this capacitor, let's make it 2.2 microfarads. All right, we don't want to make it too simple. All right. This battery, it's a 9-volt battery, let's say, 9-volt battery. So when we turn this circuit on, the second that we connect this, right, we connect it, boom, what's going to happen? This thing is current is going to start rushing out. All right, and we're going to get this current I. We're going to start charging up this capacitor. right? Plus to minus. And if we look at this curve, the curve is going to look like this over here. Here's time, T, and then up here is voltage, V, all right, and then here's the origin here, all right, and then as this thing charges up, it's going to, do this kind of thing, right? And it's going to asymptotically go to, what's it going to go to? It's going to go to here, right? And this is the 9 volts, all right? And so the question is, what's it kind of doing in the middle? Well, we know exactly what it's doing in the middle, right? Because we know what the modeling equation is. So what's the modeling equation? The modeling equation for this is for charging, right? Is what? And so let's put something here. So we'll call this plus to a minus. We're going to call this V sub t, okay? So V sub t equals the initial voltage here, right? Which is 9 volts. So 9 volts, 1 minus e to the minus t over tau, which is RC, right? So that's 1K times 2.2 microfarad, 2.2 microfarad, right? That is the equation that will describe what's going on here. So let's clean this up a little bit. So we've got V sub t, and I'm just going to take away the voltage here, the V, and just leave it as a 9, okay? 1 minus e to the minus t over, now let's figure this out. Let's get our calculator, right? So we've got 1K times 2.2 micro equals 2.2 times 10 to the minus 3. All right, but that's in the bottom, so I'll leave it there for now. So down in the bottom here, we've got 2.2 times 10 to the minus 3. All right, that is our tau. So tau equals 2.2 times 10 to the minus 3 seconds. All right, so what this says is that, and so this is our RC time, this is tau. At 1 tau, so if we go here and say that this is like, that's 1, and that's 2, and then that's 3, and that's 4, and that's 5. So if we say that each one of these is 1, this is a millisecond, right? 10 to the minus third. So if this was 1 millisecond, and this was 2 millisecond, and this was 3 millisecond, 4 millisecond, and so forth, right? Then right here at like 2.2, right here, so at 2.2, that's 1 RC time. If we come up here, right, to here, then this should be at roughly 63%. And I haven't drawn this correctly, but this will roughly be 63% times the 9 volts, right? So 0.63 times 9 volts equals 5.67. So again, I have horribly drawn this to scale, but this would be 5.67 volts at 1 RC time. That's what's going on. Now, so the question is, we want to know at 5 RC times, what is the voltage? So let's do that. So we want to say at 5 RC times, what's going on? All right, so let's do this. So we have V sub t equals, all right, and then we've got 9, and then we've got 1 minus e to the minus t, but t now is going to be 5 RC, 5 times RC, over, and now we're just going to leave this as RC, right, like that. Well, the RC's cancel out, so it's just e to the minus 5. So this is equals 9 times 1 minus e to the minus 5th. Okay, so let's do that with our calculator. Okay, all right, so what we have here is 9, 1 minus, and then this is really 1 over e to the 5, right? E to the 5th. All right, so when we do that, we get 9 times 1 minus, and then we'll do e to the 5th here, e to the 5th, and then we'll invert that. And then just to show you how small this number is, we will say, let's do this. So this number here is 0.0067 ... and something else. So this is 9 times this, and this is practically 0, so it's just 9 times 1, so it equals 9 volts. In other words, at 5 RC, this is so small, right? This is, really what, 6.7 times 10 to the minus 3, right? This is so small, it's infinitesimal. At 5 RC times, we are like 99.9999% fully charged. All right, so that's it. So at 5 RC times, you're fully charged. All right, so that's the rule. And then the same thing happens with discharging. So now, if we were then to get rid of this battery and short the battery, so if we came here and we shorted the battery, then it would start discharging, and then basically as this thing charges, wherever we are here in time, it would then start its discharging, right? And then this discharging in 5 RC times would be all the way to 0. So that's it. So anyway, so that's RC charging and discharging, and this is why. And then one last little thing. So I think yeah, we have time. Let's go ahead and let's go on the bench, and we're going to do a simple little experiment. And what we're going to do is this. We're going to synthesize what happens with cables. All right, so now, so one thing is that you may have, learned about or seen, or in some context, is, so here's time here, and here is voltage here. And say you have a square wave, and you put a square wave down a cable, and you have this nice, beautiful, whoa, all right, unless Andre draws it, you have this nice, beautiful square wave, which represents a signal or some bits or data, whatever, and the signal gets really, really distorted. The reason why it's getting distorted is because there's R and C in the cable, resistance and capacitance through the cable. And it distorts the signal because it's charging up capacitance, right, and then discharging. So what does this signal turn into? It turns into this. What it turns into is we charge like this, and then we, discharge like this. And then we charge like this, and then we discharge like this. So the square wave turns into this bizarre sawtooth shark jaws looking thing. And the reason why is because there's RC charging and discharging, and this comes from the impedance or resistance of the cable and other electronics that are connected to it. This is why when you run things down cables, you want to have low capacitance and no capacitance and no resistance, because you want these signals to end up down the cable the way that they started. Otherwise, you get this distortion. What does that cause? All right, so let's zoom into this real quick. So what that causes is this effect. It causes this to happen. So if we look at the square wave here, so here was the nice square wave to begin with, right? Okay, and now it kind of looks like this. All right, and then it kind of looks like this. So normally the electronics, whatever circuit was getting, so it used to see this nice sharp, rising edge, so it would transition really quick. But now, because this thing is struggling to get up here, there's time is occurring in here. So what happens is the circuitry, maybe before at this time here, call it time 1, it transitioned to a 1, but now this thing's struggling, and finally here at maybe position 2, it toggles to a 1. So things start getting skewed, right? And time starts getting delayed. And the same thing here. Now it just instantaneously used to drop, but now it's still a 1, a 1, a 1, a 1, a 1, a 1. Okay, now it's a 0. Right, so it becomes a 0 here at this time here, this time 3, and we really wanted it to become a 0 right there. So anyway, this is why capacitance and resistance inside of your cables is a bad thing. All right, so you got to watch out for that. Okay, so let's go ahead. We're going to go over to the bench, and we're going to do a little experiment to show how we can deform a square wave signal inside of a circuit by putting some resistance and capacitance. So this will be kind of a quick little fun way to end this lecture with an experiment, which we always like to do. So meet me over at the bench, and let's do that. All right, so normally I like to put things together while you're watching, but getting this analog stuff to work sometimes is kind of finicky, and it just kind of wastes a lot of time. So it's not really important in this case. So what we have set up is if you take a look at the equipment screen here. So over here we've got the oscilloscope. The top line is going to be the input. The bottom line is going to be the output. So we're going to see the original wave and then the distorted wave on the bottom. Over here we've got the signal generator and we're going to be putting out a square wave. Right now we've got it set for 5 volts and it's at 1 kilohertz, but we're going to change that. Okay, now back to our circuit. So let's take a look at our circuit. So the whole idea here is the signal's coming in on the red line, and then this is ground all down here. So the oscilloscope grounds for the probes, and then the signal generator ground. So this probe right here, the top probe, is the signal coming in that we're watching. That'll be the yellow one. And then the signal's going to come in. Forget this top resistor right here. Just ignore that. And then it's going to come in, and we're going to have some resistance. And right now I think I have that as 1K, brown, black, red, 1K. And then we're going to have some capacitance going to ground, and that'll be kind of our RC charging circuit. So we're taking the output from the capacitor node itself. All right, then that's going to travel along this, and then we're going to get the output right here. So this simulates a circuit trace that would be on a circuit board. Now, there's inductance in this circuit, but we're not going to worry about the inductance because the frequencies are low enough where it's not going to come into play, and we don't know yet about how to model the inductance. But there's distributed capacitance, resistance, and inductance. So everything distorts everything depending on the frequency, all right? So right now we'll just pretend the inductance isn't there. The whole point of the experiment is we're going to show that if we take a nice square wave and we send it into a a black box or some components, and those components have distributed resistance and capacitance, we're going to distort that waveform. All right, so that's what our goal is to see that effect. Now, right now, there is no capacitor going to ground, so we do not have the capacitive component of the circuit. So we're just going to do a couple different runs, and then we're going to add capacitors, and we're going to see how the different capacitance affects things, okay? All right, so what I'm going to do is, since we don't need to look at the circuit's not changing, we're going to change the view and we're going to look at the equipment so we can see what's going on. All right, so now we're looking at the equipment. All right, so the first thing that I'm going to do is I'm going to turn on the signal generator. All right, and as you can see, the top wave is the input and the bottom wave is the output through the distributed system with resistance and capacitance, except we have no capacitance right now, so just resistance. So the only capacitance we have is basically in the oscilloscope lines and the wires and that kind of thing, so it should be very, very little, all right? So we should be able to run this frequency up and have no problem. So right now we're at 1 kilohertz. So keep an eye on things, the 1 kilohertz signal right here, and keep an eye on the oscilloscope. So what we're looking for is distortion of the bottom wave. All right, so I'm going to start turning this up, and we're at 10 kilohertz, and then I'll crank up the frequency here so you can see. So everything still looks good. All right, so now we'll go on to the 10s and 30, and we're going to keep going. All right, and there's 200 kilohertz. Everything still looks good. All right, and let's keep going. And now we're to a megahertz, and now I'm going to get on the megahertz adjustment. Now, I don't know if you can see this, but we're starting to see some distortion here. And sometimes getting the oscilloscope to lock into things is a challenge here. So let's see if we can get the oscilloscope to cooperate with us a little bit better here. We'll do an auto set. Give that a second. Okay, and we'll put this up. Do this and okay, turn that down. Okay, good enough. Okay, okay. All right, so you can see we're starting to get a little bit of distortion. So this is, from capacitance and inductance that are just in the lines, and also this resistance that we've added in here. But it still looks not bad, and we're at 1 megahertz. All right, so let's keep going. 2 megahertz, 3 megahertz, and so forth. And you see at 6 megahertz here, we've got a triangular wave on the bottom. The top wave is still okay. We're seeing some little bits of ringing and whatnot in the top, but the bottom wave is definitely distorting. And there's 5 megahertz, and then you go up to 10 megahertz, and now I've got this triangle. So what's happening? There's a lot of things going on here, inductance and whatnot, that's causing this to occur, and that's why we're having what are called transmission line effects and different things. And so now let's back off of it now, all right? So let's back off of it to where it wasn't happening. So let's back off of it back into kilohertz. So at 100 kilohertz, we're pretty safe. And you can see if we open this up, and you can see right here on the oscilloscope, we can see that little edge there. That's an RC charging edge. There's some capacitance there, right? But if we, zoom out, we can't really tell. Okay, now let's add some capacitance into it and let's see what happens. So we're going to start off with 47 picofarads, a teeny tiny capacitor. So let's go back to look at the circuit here, and we're going to add this in. All right, so now imagine we have a little bit of capacitive load. And all right, now back to the oscilloscope. Let's turn the frequency up here. All right, so 100, 200, 400, 500 kilohertz. Let's open this up. And again, we're seeing this effect, and at a megahertz, we're seeing the effect. It's pretty much similar to what it was. Let's pull the capacitor out in real time and let's see what happens. All right, so did you see that? So the capacitor is definitely causing more distortion. So there's with the capacitor, with no capacitor. And this is a tiny, this is picofarads. This is 10 to the minus 12th farads. There is nothing here, but you can see it's, really affecting that quite a bit. And if we go up to even a higher frequency, let's go up to 5 megahertz. So there's 5 megahertz. All right, with the capacitor, that waveform is just, it's brutalized, right? It is brutalized. And let's take the capacitor out. All right, there's with the capacitor out. And with the capacitor out, it got some semblance of a square wave, right? We can see the charging and the discharging, right? You can see the charging and the discharging, beautiful, right? And now let's put that capacitor back in. This little picofarad, you can look at it, it's totally triangular and it's attenuated as well. Because what's happening here is there's filtering going on. We've created a filter, and we've created an RC filter as well. And we're going to learn about that, but I wanted you to see this in action. Now, let's get back to where we should be okay. So at about 500, at about 100 kilohertz, if we back off this, our square wave more or less looks like a square wave. So we're at 100 kilohertz right now, and we're back to normal, even with the capacitor. So we're going to take it out. But let's add some more capacitance. Instead of picofarads, let's put microfarads. And now watch how bad this gets. So now we've got, this is a 0.1 microfarad capacitor I'm going to add in here, all right, 0.1 microfarad. And right now we're at 100 kilohertz. Now watch this. So down on the board, I put it in. So now I've got 0.1, oops, put it in the wrong place. There we go. All right, so I've got 0.1 microfarad, and now look what happened to our signal. There is no signal. So two things have happened. We've not only have we RC charged, we're doing RC charging, but we've attenuated the signal enormously. So what I'm going to do here is I'm going to put this on AC coupling, which is going to cause more distortion because then there's a filter inside. But I'm going to amplify this so you can see this a little bit. All right, and forget about those noise, those spikes going up. We're at 100 kilohertz, and we now have this complete triangular wave. And now the amplitude, look at the second channel, it's 100 millivolts. So we had a 2 volt on the yellow, so 2 volts per division. So we've got a nice 5 volt signal, and now we're only getting 100 millivolts out. It has just been completely attenuated and distorted. Now, but we're at 100 kilohertz. What happens if we go to a higher frequency? Will it get better? It doesn't look like it, right? It's getting worse and lower and all that. Okay, let's go to a lower frequency now. So let's go to a lower frequency. Now we're at 100 kilohertz. Now 90, 80, 70, 60, 50, 40. Now look, the signal's getting bigger. Okay, now it's getting happy, right? It's getting really big. So now we can turn our amplification down. We can do this. Okay, now we've got 500 millivolts per division on the bottom, so it's getting better. We're at 10 kilohertz. And now look, I'm going lower frequency. I'm 5 kilohertz, 4 kilohertz. I'm at 1 kilohertz. Now we're getting in business. All right, and let me do that. So now look what's happened here. So we've got a 1 kilohertz signal, and if we zoom out a little bit, it's not too bad. We're seeing definite RC charging. The scale is almost the same, so the attenuation is going away. So we're seeing the charge and the discharge, the charge and the discharge, but we're not seeing, but because we're not doing it too fast, it has time to charge and time to discharge. But as we increase the frequency, that charging and discharging, it doesn't have time. So it just, it starts and it stops, starts and it stops. And that's why it's attenuating and deforming so much as you see it there. We're at 10 kilohertz and the signal is completely gone, right? Okay, now let's go down to less than 1,000. And there's 900 hertz, 800, 700, 500, and 400, and 100. We're at 100 hertz. So at 100 hertz, and let's get rid of the AC filter, and let's put it back to DC on channel 2. All right, so now 100 hertz, we have our signal and it can survive. So 100, at 200, at 300, it's okay. And then it starts, getting obliterated at 1 kilohertz. So the reason why is because we've got this capacitance and resistance on here, and we're creating a filter, which we're going to learn about. But we can see this RC charging. And so what's the point? The point is, in the first case, we had a capacitance of 47 picofarads, which is, when you start looking at chips, you'll see that they have input capacitance of picofarad range. In other words, they're going to have very little effect, picofarads. But if you start putting microfarads, right, even microfarads or nanofarads, you are going to put a lot of capacitance on these lines, and you're going to start to see these deformations in your signals, all right? So that was just 0.1 microfarads. Now, can we help it by decreasing the resistance in the signal line? Yeah, sure. So the RC time, it's R times C. So we've got this horrible signal right now at 1 kilohertz. Can we fix that by changing this the 1K? So can we increase the drive, and would that help us a little bit? Yeah, sure. So let's increase the drive. So let's go back to the circuit, and let's put a 100 ohm. So we've got a 100 ohm, brown, black, red. And I'm going to pull out the 1K, so signal's gone. Remember what that looked like. And I'm going to put the 100 ohm here. All right, and now look at that. So now that's not bad. That looks pretty good, right? And so now let's go up in frequency. So 1 kilohertz, 2 kilohertz, and now at about 5 kilohertz, we're at the same place we just were with the 1K. We're at the amount of distortion, but now we're at 5 kilohertz instead of 1 kilohertz. So now we've increased our frequency that we can send signals out without, them being too deformed, right? And then of course, if we keep going up to 10, now we've got our triangle wave, and maybe our electronics can tolerate this, but what they're not going to like is continued attenuation. And then notice what's happening. There's a DC offset here, so we're staying way up high. We're never going down low because we just